हेलो आ गया। लाइव हो जाएगी। हेलो
चेक कर लीजिए ना। हेलो टेस्टिंग, हेलो 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 हेलो। आर कैट में आप सभी का स्वागत है। तो आपके माइक कहाँ वहाँ होंगे ना? नहीं, माइक
हेलो हेलो हेलो। Hello, hello, mic check. Hello, hello, hello. Podium mic check, check. Hello, hello.
Hello, hello, hello.
The Raja Ramanna Center for Advanced Technology, a constituent unit of DAE, has India's only two synchrotron radiation sources, Indus 1 and Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. There are 19 operational beamlines, among which 2 beamlines were commissioned in the last 3 years. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation, the Center for Advanced Technology, a constituent unit of DAE, has India's only two synchrotron radiation sources, Indus 1 and Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. There are 19 operational beamlines, among which 2 beamlines were commissioned in the last 3 years. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation at Indus 2, 3 insertion devices have been commissioned in the last 3 years and the related beamlines are being constructed. The total number of user experiments have been increasing steadily and was 639 in 2016. Raja Ramanna Centre for Advanced Technology, a constituent unit of DAE, has India's only two synchrotron radiation sources, Indus 1 and Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. There are 19 operational beamlines, among which 2 beamlines were commissioned in the last 3 years. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation at Indus 2, 3 insertion devices have been commissioned in the last 3 years and the related beamlines are being constructed. The total number of user experiments have been increasing steadily and was 639 in 2016. The Raja Ramanna Centre for Advanced Technology, a constituent unit of DAE, has India's only two synchrotron radiation sources, Indus 1 and Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. There are 19 operational beamlines, among which 2 beamlines were commissioned in the last 3 years. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation at Indus 2, 3 insertion devices have been commissioned in the last 3 years and the related beamlines are being constructed. The total number of user experiments have been increasing steadily and was 639 in 2016. The Raja Ramanna Centre for
She Oncodiagnoscope. Oral cancer is the third.
Check. Hello. Hello.
Sheetal Vahak Yantra. Shivai is an economical and eco-friendly liquid nitrogen-based transportable refrigerated container for perishable items. Sheetal Vahak Yantra. Shivai is an economical and eco-friendly liquid nitrogen-based transportable refrigerated container for perishable items like fruits and vegetables of farmers, pharmaceuticals, dairy products, etc. It can be transported on any carrier like train or truck or built on any chassis of vehicle. It is designed to withstand rough roads without maintenance problems. Shivai has successfully completed 1000 km of road trial. This development will enable farmers to transport produce without quality degradation. Sheetal Vahak Yantra. Shivai is an economical and eco-friendly liquid nitrogen-based transportable refrigerated container for perishable items like fruits and vegetables of farmers, pharmaceuticals, dairy products, etc. It can be transported on any carrier like train or truck or built on any chassis of vehicle. It is designed to withstand rough roads without maintenance problems. Shivai has successfully completed 1000 km of road trial. This development will enable farmers to transport produce without quality degradation. Sheetal Vahak Yantra.
Good afternoon. On behalf of the organizing team of the 10th Engineers Conclave 2023, myself, Dr. Mangesh Borge of RRCAT, Indore, along with Dr. Ram Janay Chaudhary from UGC DAE CSR, welcome all distinguished dignitaries, guests, and participants to this inaugural function. The Conclave EC 2023 is being organized by Indian National Academy of Engineering jointly with UGC DAE Consortium for Scientific Research in association with Department of Atomic Energy, Raja Ramanna Center for Advanced Technology, Devi Ahilya Vishwavidyalaya Indore, and Indian Institute of Technology Indore are the partner institutes for this event. We are honored to have Professor M. Jagdish Kumar, Chairman, University Grants Commission, as the chief guest for the inaugural function. Welcome, sir. I also welcome our distinguished guest, Dr. Anil Kakodkar, Chancellor, Homi Bhabha National Institute, Mumbai, Member, Atomic Energy Commission, and Chairman, Rajiv Gandhi Science and Technology Commission, Government of Maharashtra, and Dr. K.N. Vyas, former Chairman, Atomic Energy Commission, and former Secretary, Department of Atomic Energy. Greetings also to Professor Indranil Manna, President, INAE, and co-chair of EC 2023. Professor Amlan J. Pal, Director, UGC DAE CSR, and also the co-chair of EC 2023. To grace the occasion, amongst us, we also have Dr. Sanak Mishra, former President, INAE, Professor Sivaji Chakravarti, Vice President, INAE, Dr. Ajay Mathur, Director General, International Solar Alliance, Professor Kamachi Mudali, Vice Chancellor, HBNI, and Professor Renu Jain, Vice Chancellor, DAVV, and other esteemed dignitaries. I now request Dr. Shankar V. Nakhe, Director RRCAT Indore, and the overall coordinator of the event to escort Professor M. Jagdish Kumar, Dr. Anil Kakodkar, Dr. K.N. Vyas, Professor Indranil Manna, and Professor Amlan J. Pal to the dais, please. Thank you.
आरआर कैट के होमी भाभा सभागार में उपस्थित पूरे भारतवर्ष से आए सम्माननीय शिक्षाविद, वैज्ञानिकगण, इंजीनियर्स, शोधार्थी और मित्रों, आप सबको हमारा सादर नमस्कार। हमारे देश की एक अनूठी परंपरा रही है कि किसी भी शुभ कार्य को प्रारंभ करने से पहले हम दीप का प्रज्वलित करते हैं इस आशा के साथ, या यूं कहें कि इस विश्वास के साथ कि ज्ञान का दीप हमारे अज्ञानता के अंधकार का हरण करेगा और इस शुभ्रता के वातावरण में किसी भी कार्य के कुशल से संपादन हो, इसकी आधारशिला रखेगा। इसी भाव को रखते हुए मैं मंच पर विराजित सभी गणमान्य गुरुजनों से निवेदन करूंगा कि वो दीप का प्रज्वलित करें।
Thank you. I now request Dr. Nakhe to please welcome our chief guest, Professor M. Jagdish Kumar, with a floral bouquet. I request Professor Pal to greet our distinguished guest, Dr. Anil Kakotkar, with a bouquet, please. May I request Dr. Nakhe to offer floral bouquet to distinguished guest, Dr. K.N. Vyas, please. Thank you. My request to Professor Pal to please greet Professor Indralil Manna with a bouquet, please.
इससे पहले कि मैं प्रोफेसर अमलान जी पाल जी को स्वागत भाषण के लिए अनुरोध करूं, एक संक्षिप्त परिचय। प्रोफेसर अमलान जी पाल वर्तमान में वैज्ञानिक अनुसंधान संकुल के निदेशक हैं। वह इंडियन एसोसिएशन फॉर कल्टीवेशन ऑफ साइंस कोलकाता में प्रोफेसर और जेसी बोस नेशनल फेलो भी हैं। वह भारत के तीनों विज्ञान अकादमियों और भारतीय राष्ट्रीय इंजीनियरिंग अकादमी के फेलो हैं। अब मैं हमारे सम्मानित निदेशक प्रोफेसर अमलान जी पाल जी को अनुरोध करूंगा कि वो आकर के स्वागत भाषण दें।
This will touch?
Yes, please on.
Yeah, thank you, Dr. Ramchanan. Good afternoon and namaskar to everyone. Professor Manna, Professor Jagdish Kumar ji, respected Dr. Kakotkar, Dr. Vyas ji, Dr. Nakhe, dignitaries of the dais, Madam Renu Jain, Professor Joshi, and other distinguished guests, vice presidents, past presidents of Indian National Academy of Engineering, distinguished fellows of the academy, and esteemed delegates from the industries, and academicians and colleagues from the UGC CSR, RRCAT, Devi Ahilya Vishwavidyalaya, IIT Indore, students, ladies and gentlemen, again namaskar and greetings. I would like to first thank Professor Indralil Manna, the Vice Chancellor of BIT Mesra and the President of INE, and his team from INE for considering Indore to be the city to host 10th edition of Engineer Conclave. As you may know that Indore, which is not even a state capital, has grown as an academic hub with the presence of academic organizations like IIT, IIM, and of course RRCAT, Devi Ahilya Vishwavidyalaya, and other institutes in the region. And the interesting thing of Indore is that we have a presence of large number of industries, engineering industries in the region. And these engineering industries have become the backbone of engineering academic organization in the region. So in that sense, the city has become quite apt for organizing this engineers conclave. I, on behalf of the whole organizing team of UGC CSR, RRCAT, Devi Ahilya Vishwavidyalaya, and IIT Indore, and also on my personal behalf, I extend all my greetings and welcome all the delegates who have come all the way from different cities of India to this 10th edition of Engineers Conclave 2023. I am sure that you will have a pleasant stay in this India's cleanest city. That's 6 times in a row, and of course, fruitful deliberations. About the institute which I represent, that is in UGCDA Consortium for Scientific Research, which is the co-host of this event, I must state that UGCDA CSR, even though smaller in size, we have placed our footprint in research across India. I must also state that we are not just another research organization or research institute. We have a definite mandate to play, and I am proud to say that we are fulfilling that mandate. And our mandate is to support research, scientific research and engineering research at universities. And that's in bold, this phrase. That is, we are here, UGC CSR, to support science and engineering research in Indian universities. A large number of researchers from less endowed institutes and state universities are availing the support of high-end research facilities at UGC CSR. And when they complete their education, research, they become academician, often join industries, and when they do that, we feel proud that our institute, that is UGC CSR, have left some footprints towards the development and growth of the country. I request you to spend some time in front of the poster that we have placed outside the hall. You will find the details of our research activities and the high-end facilities that we have at UGC CSR. With the financial support from UGC, thank you, Professor Jagdish Kumarji, we have and we are fulfilling the mandate of supporting scientific and engineering research that is being carried out across different universities. This IUC system, what is commonly known as IUC system, that is inter-university centers, have proved to be quite effective in Indian research. We must recognize the vision in forming the IUC system as a whole, and for specifically for UGC CSR is the year 1989 by Professor Yashpal and Professor Dr. M.R. Srinivasan, who was the AEC chairman during 1987 to 1990, sorry. So they started this through this MOU, this UGC CSR, with 3 centers at Indore, Mumbai, and Kolkata, and with the head office being in this city. The institute reshaped and evolved definitely over the years and was renamed as UGC Consortium for Scientific Research in the year 2003. That's exactly 20 years back. And so that why it was done, this reshaping, the renaming rather, so that we can house a range of high-end scientific instruments, equipments to support research that can be carried out at the institute at UGC CSR. And we must also thank the personality who is present here today, Dr. Anil Kakotkar. He was the chairman of Atomic Energy Commission in 2003 when this institute was renamed. And Professor Arun Nibgarkar was the chairman of UGC at that time. And in these 20 years, we still respect your vision, sir, Dr. Anil Kakotkar, that we are still working in the same manner. That incidentally, Dr. Kakotkar is now the chairman of our governing board, and with the full-fledged support from Professor Jagdish Kumarji, chairman UGC, Dr. Vaz, Dr. Mahanti, we are certain that we will be able to expand further and broaden the increasing need of university research today and in future years, because the need of research is changing every day. If you look at back in 20 years time, so now the demand from the universities are different. So we need to also reshape and rethink that how we should provide support to university research. I want to take this opportunity to approach the dignitaries from industries who are present in this ingenious conclave. My appeal here is that you please support university research, maybe possibly through UGC CSR. I am sure that the chairman of our governing board, Dr. Anil Kakotkar, and Professor Jagdish Kumarji, chairman of UGC, will support my appeal to industries, because my appeal is based on the Anushandhan National Research Foundation, through which India as a country has started a new journey in research.
We all know that out of 50,000 crore that is planned for the next 5 years, 36,000 crores will come from non-government sources, that is from industries and philanthropists. So, as we should all agree that support from universities, support from industries is the need of the hour to research, to sustain research. So if we can provide proper training to the manpower, to the students at the universities, the students in turn will become highly skilled manpower, and they will in turn give the country industries, and the country will grow for the growth of the Indian industries. I sincerely hope that the dignitaries here, especially from the industries, will consider supporting university research. Your expenditure towards university research will not be just an expenditure. It will be a means to create your asset in the future. Before I close, I thank all the dignitaries for accepting our invitation to come to Indore. Especially thanks to Professor Jagdish Kumarji for agreeing to be the chief guest. I must also thank Nakeji for agreeing to join hands with us so that, and his team members, so that we can make this event totally an Indorian event. As we all say that it's now this engineer conclave has become a true example of true collaboration and cooperation, because as we all know that united we stand. Thank you, Jai Hind and Namaskar again.
आपके स्वागत भाषण के लिए धन्यवाद महोदय। मेरा यह सौभाग्य है कि अध्यक्षीय संबोधन के लिए मैं आप लोगों के समक्ष प्रोफेसर इंद्रनील मन्ना जी का संक्षिप्त परिचय रखूं। विश्वास मानिए संक्षिप्त ही होगा, क्योंकि मेरे में धृष्टता या ये क्षमता नहीं है कि इनके संपूर्ण उपलब्धियों को आप लोगों के सामने अपने शब्दों में रखूं। INAE के अध्यक्ष प्रोफेसर मन्ना वर्तमान में BIT मिश्रा रांची के कुलपति हैं। प्रोफेसर मन्ना ने 1984 में IIT कानपुर से एमटेक की डिग्री और 1990 में IIT खड़गपुर से डॉक्टरेट की उपाधि प्राप्त की। वह एक शिक्षाविद और शोधकर्ता हैं। फेस ट्रांसफॉर्मेशन, नैनो लिक्विड, लेजर, प्लाज्मा इंजीनियरिंग के क्षेत्र में इनका बहुत महत्वपूर्ण योगदान है और वैज्ञानिक समुदाय का गहरा ध्यान गया है। वह जर्मनी में DAAD और हम्बल फेलो भी थे। उन्होंने 300 से अधिक पीयर रिव्यूड प्रकाशन लिखे हैं और 30 डॉक्टरेट थीसिस का मार्गदर्शन किया है। वह 2010 से 2012 तक CGCRI कोलकाता और IIT कानपुर के निदेशक के रूप में 2012 से 2017 तक कार्य किया। उनके उत्कृष्ट शोध कार्यों और योगदान के लिए उन्हें कई पुरस्कार और उपाधियों से सम्मानित किया गया है। कुछ उदाहरण के लिए उन्हें MRSI मेडल 2000, बिनानी गोल्ड मेडल 1999, GD बिरला गोल्ड मेडल 2008, युवा वैज्ञानिक के लिए इंसा मेडल 1992 में प्राप्त हुआ इत्यादि। वह भारत के तीनों विज्ञान अकादमियों और भारतीय राष्ट्रीय इंजीनियरिंग अकादमी के फेलो हैं। इसके अतिरिक्त वह JC बोस फेलो हैं, फेलो द वर्ल्ड एकेडमी ऑफ साइंसेज, सदस्य फेलो एशिया पैसिफिक एकेडमी ऑफ मटेरियल्स, फेलो ऑफ इलेक्ट्रॉन माइक्रोस्कोपी सोसाइटी ऑफ इंडिया, इंडियन सिरेमिक सोसाइटी, लाइफ फेलो ऑफ इंडियन इंस्टीट्यूट ऑफ मेटल्स कोलकाता। वह कई उद्योग अनुसंधान एवं विकास के अनुसंधान बोर्डों के सदस्य रहे हैं। 2015 से 20 के दौरान वह MHRD की प्रौद्योगिकी विकास पहल इम्प्रिंट के राष्ट्रीय समन्वयक बने। प्रोफेसर मन्ना अभी INAE के अध्यक्ष के रूप में ट्रांसलेशनल रिसर्च, इनोवेशन और नई तकनीकी के द्वारा भारत की इंजीनियरिंग और तकनीकी की आत्मनिर्भरता को बढ़ावा देने के लिए प्रयत्नशील हैं और INAE को एक राष्ट्रीय एजेंसी बनाने में लगन से लगे हुए हैं। अब मैं प्रोफेसर मन्ना जी से निवेदन करूंगा कि वो कृपया आएं और अध्यक्षीय संबोधन।
बहुत धन्यवाद श्रीमान। Professor Jagdish Kumar, Chairman UGC and Fellow of INE, today's Chief Guest, Dr. Kakotkar, former President of INE, former Chairman AEC, Mr. Ken Vyas, also former Chairman AEC, Dr. Shankar Nathe, Director of RRCAT, Professor Amlan Pal, the co-organizers, the co-chairman, and the director of the IUC, Professor Renu Jain, Vice Chancellor, DAVV, Dr. Suhas Joshi, Director, IIT Indore, also our co-organizers, dignitaries seated off the dais, colleagues from RRCAT Indore, fellows and awardees of the Academy, ladies and gentlemen. You probably are aware that Indian National Academy of Engineering, founded in 1987, is the only engineering academy that works as a peer group for the profession of engineering in this country. So we have a history of 36 years plus, and we were fortunate to be steered in the past by the likes of Dr. Kakotkar, late Dr. Abdul Kalam, Dr. Arunachalam, Professor Rama Rao, and entire who's who of the country in the engineering profession. In our history of 36 plus years, and that too in a country of, say, 1.4 billion or 145 crore people, we have, as on today, on roll only 920 fellows elected and 99 fellows from abroad. So it only conveys one thing, that Indian National Academy, since inception, has been extremely quality conscious. Unlike some of the institutions or other organizations, one cannot be a fellow of INE by simply paying a subscription or applying oneself. Only through nominations one can be considered, and it goes through a three-stage, very rigorous peer reviewing process. And every year we end up electing only about 30 plus out of about 300 plus nominations we consider. So the success rate is about 10%, at times even less. We are an academy which embraces all age group of people associated with the engineering profession, starting from the budding engineers who are studying in engineering institutions. We select some of them for their best thesis or project recognition at both undergraduate, postgraduate, even at the doctoral level. We recognize the entrepreneurs and innovators. We select young engineers and embrace them in our fold until the age of 45 as young associates. We run a very prestigious fellowship called APJ Abdul Kalam Fellowship, which is exactly for translational research. We all are aware that engineering is all about translation of fundamentals into practice for societal benefit. And for that reason, in order to promote that exercise, we have introduced, thanks to the funding, generous funding from the Department of Science and Technology, a fellowship called Kalam Fellowship, which is granted only for those who, through a very rigorous process of scrutiny, provides evidences that they have some innovation in the making, and within 3 years they'll be able to produce enough results to earn the confidence of the community. It is very much similar in terms of privileges as J.C. Bose Fellowship, but this fellowship is with a difference. It's only for one term, and that too in 3+2, 5 years divided into 2 parts. And only those who are able to showcase the promise can go until the end of the fellowship. So until now, we have hardly 30 plus professionals in the country who have been awarded Kalam Fellowship. We draw our strength from the 3 main quarters of engineering profession, namely the industry, the R&D organizations, and academic institutions. We are very keen to restore balance or come up with a better parity in terms of gender, proportion, and also the ones who are from industry. So we have taken some very affirmative action so that INE in the future will have near equal representation from industry, and will have many more representation from the women. Among various other activities, INE maintains consultative committees with the major government departments, including TST, CSIR, DRDO, Atomic Energy, Space Organization, including the Office of the Principal Scientific Advisor, ACRP, AICT. Incidentally, last April, we went and met the Chairman UGC, today's chief guest, and made a similar request that INE in its fold has about 48% of the fellows are elected from academia, and they're all very eminent experts in by their own right in their fields. So we would be very keen to help UGC come up with a very effective implementation of NEP 2020 and beyond. Of course, I hope that we'll be in a position to offer our expertise and support to UGC in the future. INE takes up specific projects of societal and industrial importance. For example, with DST funding, we carried out exercise on a pilot project on safe laboratory practices and disposal of laboratory waste. We also form expert groups to deliberate on very specific topics like engineering interventions for disaster mitigation, similarly technology foresight and management. We have come up with very specific recommendations on the landscape of advanced structural materials and also on civil infrastructure, including usage of low-cost building materials. We pleaded with the Government of India, the appropriate quarters, to launch a major initiative on development of regional transport aircraft. In fact, we tied up with CSIR and offered to create a detailed project report so that India can produce narrow body or 70 to 90 seater aircrafts within the country. We made several representations. We don't know exactly what's going to happen, but this is just an example I want to present before you as to what INE wishes to do, is to foresee where lies the opportunity, which is how India should move towards self-reliance, which is what our Honorable Prime Minister often reminds us, and where INE can make a difference with its intellectual capital, expertise available in various quarters, move ahead in that direction. Last year before, 2020, let me just tell you that year-long, INE has a series of functions. 5 of them specifically starts with April 20, our Foundation Day. Then we observe National Frontiers of Engineering alongside. We also organize innovations in manufacturing practices, where we invite the scholars and students of engineering institutions to come and showcase their models. Then we hold the Youth Conclave, Engineers Conclave, what we are doing here, and finally the annual convention. So the year before, the Foundation Day function was held in Delhi on a very specific topic of implementation of national education policy. And incidentally, Professor Jagdish Kumar as Chairman UGC was present, so was Chairman AICT. But the most important thing, the meeting was chaired by none other than Dr. Kasturi Rangan, also our former President INE, and the principal architect of NEP 2020. Before we met, we had 5 satellite events in 5 different places, North, East, South, and Central, chaired in each place by one of the directors of an IIT or a former director of IIT or IISc. And they were given to deliberate upon 3 specific questions. So on 15 such questions, we submitted our recommendations to the Ministry of Education, the Secretary of Higher Education, who acknowledged and then obviously promised that if time comes, he would take specific help from INE. This is the 10th edition of our Engineers Conclave. In fact, we started in 2013, and in all these years, we have been celebrating Engineers Conclave with a common format that we select two specific themes, one chosen by the host institution. For example, in this case, RRCAT and IUC together came up with a proposal to hold discussions on engineering and technology for clean and green India at 2047. This is very appropriate because after all, we are in Indore, the city. As you come out of the airport, you immediately, what catches your attention is the cleanest city in the country for successive years. And obviously, it's very appropriate on our part also to make sure we are all aware that there are issues, not just waste disposal or recycling. We have issues with environment, with water, with various other components of sustainability. And incidentally, this is the week where the countrywide we are celebrating Swachhata Abhiyan. So it is quite appropriate that we are deliberating on this one as one of the topics. The other one is on laser technology, which is what RRCAT is famous for. And in the morning, some of us were very fortunate. Dr. Nakhe showed us around the major developments that are taking place in RRCAT, not just in laser technology. There are various other very important technologies which are emerging, and it's going to make a huge difference in terms of engineering progress of the country. So 2013, we deliberated on production and manufacturing in aerospace, engineering intervention in the Sundarbans. 2014, second edition, we talked about emerging space applications and technologies for hilly regions, and so on and so forth. Let me spare this reading out the entire list. Every time we choose two topics and we just don't deliberate, we come up with very specific actionable recommendations. And this is how INE wants to make a difference to the country. We are all aware that India is a mighty economic force, the fifth largest in terms of the nominal GDP. And we are eyeing with nearly double-digit growth rate, or at least 6 to 8% growth rate. We are eyeing that very soon will be the fourth and eventually even third largest economy in the world. But on the other hand, if we are realistic and truly patriotic, we cannot miss the fact that there are issues related to energy consumption per capita, road area available per capita, or say income per capita, and so on and so forth. All of these interventions, all of these parameters wise, India needs to do a lot better. And India has all the potential to do that. And majority of them, whether it's energy or water or environment or transportation or connectivity, even digital intervention, security, almost all of them requires a huge intervention from engineering and technology. So this is where INE and Engineers Conclave both have a lot to offer to the country. And please remember that we are not just a group of engineers, we are a professional peer group devoted to the cause of engineering. So it is entirely for the profession and the society. So let me also tell you that how do we make a difference or wish to make a difference? All of us are aware that during 21 March until 22 August 15th, the country celebrated 75-week-long of Azadi Ka Amrit Mahotsav, 75th anniversary of India's independence. The government tasked various organizations to come up with various documents or functions, events, and so on. INE celebrated, of course, in multiple ways, but also came up with two very important compendia, one on women engineers of India, the other one on landmark achievements of engineering since independence. And this is a volume which is available at a very meager price, and INE is circulating them, has taken the responsibility of distributing them. And this is a document which, in our opinion, will be always referred to for two very important reasons in the country. Empowerment of women folks, bring them to the mainstream professions in a much more effective way. And the other one is to let the country realize that while we continue to do excellent science, the country absolutely requires engineering intervention. And there are very bright examples where the engineering community in the country has made us proud. So these should serve as a reason to inspire the future generations to devote to engineering. In fact, Amlan was talking about the need for training the youngsters, and I fully agree that all the academies have a major role in inspiring the younger generations to take up challenging projects and prove that we are comparable to the rest of the world in terms of our power of innovation and enterprise. INE also happens to be the representative of the country in the international forum called Council of Academies of Engineering and Technological Sciences, CATES. There are about 31 or 32 member countries. INE is one of them. Incidentally, 2015 probably the international meeting was held in New Delhi, but it goes to different countries by turn. So INE does play a very important role. Until recently, INE has been a very active member in the Energy Forum. Dr. Ajay Mathur is here, and Ms. Chaturvedi and many others were very important, very actively involved in formulating the policy. At the moment, INE is the chair of a working group on engineering education. So it shows that INE is considered as an effective organ, not only within the country, even in the international forum. So we would like to make bigger strides in the future. And at the moment, we are confronted with certain challenges which we wish to overcome in foreseeable future and emerge as even stronger. For that reason, we are mandated, or we are destined to create our self-sufficiency, both autonomy, both in terms of functionality, even financially. While that happens, we don't want to move away from our core mandate, which is to promote the profession of engineering in the best possible way. Before I end, I would like to thank Dr. Nakhe and all the colleagues of RRCAT for being a gracious host. And we absolutely are delighted and very fortunate to have two former chairmen, Atomic Energy, Secretary Atomic Energy and Chairman AEC, sitting on the dais and guiding us with this particular event, annual event of INE. I hope that at the end, the two specific topics that I mentioned on laser technology, on clean and green India, will come up with actionable recommendations which will definitely make the country more self-sufficient in the future. Thank you very much. Jai Hind.
आपके अध्यक्षीय संबोधन के लिए अनेक अनेक धन्यवाद महोदय। अब मैं राजा रमन्ना सेंटर फॉर एडवांस टेक्नोलॉजी के सम्मानित निदेशक आदरणीय डॉक्टर शंकर वी नाखे जी से अनुरोध करूंगा कि वो प्रोफेसर मन्ना जी को स्मृति चिन्ह भेंट करें।
Dr. K.N. Vyas has graced the function as our distinguished guest. Dr. Vyas is a mechanical engineering graduate from MS University Vadodara and graduate of 22nd batch of BRC Training School. Joining the department in 1979, he commenced his career with forays into the nuclear reactor fuel designs. He developed programs to carry out performance analysis of nuclear fuels, which modeled fuel design aspects like irradiation swelling, fission gas generation and release, pellet-clad interaction, etc. The insight gained by these studies has led to the design of the 7x7 cluster of BWR fuel having superior performance characteristics. As a fuel design engineer, he provided key inputs to fuel manufacturing units like atomic fuels division and nuclear fuel complex. Dr. Vyas has played an important role in indigenization of special materials as well as several fabrication and test equipments used in fuel fabrication. His expertise was useful in evolving the design of test blanket module and associated systems for the ITER project. He has played a key role in several strategic projects. Dr. Vyas was director of Bhabha Atomic Research Center, BRC, during 2016 to 2019, and chairman Atomic Energy Commission and secretary Department of Atomic Energy during the tenure 2018 to 2023. Dr. K.N. Vyas has received several prestigious awards, including Indian Nuclear Society Outstanding Service Award, Homi Bhabha Science and Technology Award, and the Dr. N. Kondal Rao Memorial Award. His team is recipient of several DAE Group Achievement Award for the outstanding contribution in the field of design and development of critical reactor system equipments, as well as successful erection and commissioning of various reactor systems. Dr. Vyas is a fellow of Indian National Academy of Engineering. With this, sir, may I request you to please address the gathering.
Respected dignitaries on the dais, Professor Jagdish Kumar, Chairman UGC and Chief Guest of today's function, Dr. Kakodkar Sir, Chancellor HBNI, Member Atomic Energy Commission, Chairman Rajiv Gandhi Science and Technology Commission, Government Maharashtra, and former Chairman AEC and Secretary DAE. Professor Indranil Manna, President INE, Professor AJ Pal, Co-Chair of Engineers Conclave 2023, Dr. S.V. Nakhe, Director RRCAT and overall coordinator for this conclave, distinguished colleagues from the academia, Vice Chancellor of DAVV and Director IIT and other colleagues, distinguished fellows of the academy, colleagues from DAE, ladies and gentlemen. I am very much grateful to the INE for the invitation. The conclave is a place where best of the engineers meet. We have extremely prominent speakers both on the dais as well as for the technical sessions. Hence, I would like to very briefly mention a few relatively new engineering challenges completed at Department of Atomic Energy. These are multidisciplinary activities, and I hope that the distinguished participants of the conclave will find these interesting. I would start with the activity in which the host institute, that is RRCAT, along with other partner institutes is playing a significant role. And this is related to Project LIGO, or Laser Interferometer Gravitational Wave Observatory. As is well known, this is an example in extreme engineering. The observatory has an ability to detect the differential motion of the Earth due to interaction with the gravitational wave, and the distortion which is to be measured is of the order of 10 to the power minus 19 meters. As the name implies, this is achieved by interferometers powered by laser systems housed in tubes having very high level of vacuum. I feel that it is appropriate that the key technical aspects of LIGO are discussed by RRCAT experts. However, I would like to mention some of the unique design and detailed engineering carried out by DCSEN. This is the service organization of Department of Atomic Energy. As we all are aware, LIGO utilizes two L-shaped arms, each having a length of 4 kilometers. To ensure accuracy of the measurement, it is necessary that finished floor level of both the arms should have a laser straightness. This means for a 4-kilometer length, the mid station, which is at the distance of 2 kilometers, it gets raised by about 0.314 meters because of Earth's curvature. Now, to ensure laser straightness, this finished floor level of the beam enclosure needs to be suitably corrected to take care of the level difference. And I feel this is a novel challenge in the field of civil engineering. In addition, the site at Hingoli is selected so that the observatory is in a seismically stable zone. The site is also away from regular traffic. However, to ensure minimum noise, laser vacuum equipment area building is constructed on about 750 millimeter thick RCC isolated slab. Care is taken to avoid transmission of induced vibration from adjacent buildings, including building vibrations due to wind load. In one of the last thing I would like to mention about this LIGO is the project requires a very special HVAC system, that is heating and ventilation system, to preclude errors in measurement. Temperature in the large size building is to be maintained within 23 plus or minus 1 degree Celsius. In addition to maintaining the building at a positive pressure, the ventilation system has terminal HEPA filters to reduce dust levels, and to eliminate smallest magnitude vibration, circular ducts are adopted with double wall acoustic insulation. So what I would like to mention is, to get extreme engineering projects going, you need, even in the routine type of activities, also a large amount of care. And we hope that right now it is in the stage of detailing, and we hope that we will be able to make this LIGO observatory at the highest possible, in best possible manner. I would like to come to the second R&D institute, which is also which is BRC, which is the first institute of Department of Atomic Energy. I would like to mention two important projects. The first one is demonstration of thermochemical water splitting via iodine sulfur process at a pilot scale. This has involved extensive R&D in catalysis, kinetics, corrosion studies for selection of suitable material of construction, membrane reactors, membrane electrode assembly, and in addition to that, heat transfer and parametric optimization. The material selection has involved checking suitability and finally deciding use of tantalum, hastelloy, silicon carbide as structural materials, and development of Fe2O3 based catalyst. This has required extensive bench scale studies. I personally do not have an expertise to explain the process, which is based on Bunsen reaction, but it is worth mentioning that the splitting of highly corrosive sulfuric acid at 850 degrees Celsius is one of the biggest challenges which has been taken care of as a part of material selection. Additional creditable achievement is the demonstration of the fact that in the closed loop, which has three different sections, net consumption of iodine, sulfur, and excess water is zero. So the scientists have been able to demonstrate that. I would like to mention here that the capacity is very low, which is very modest, 150 NLPH of hydrogen production. But to the best of our knowledge, all over the world, there are very few plants which have capacity which is exceeding this. I come to another achievement of BRC, which is commissioning of LEHIPA, which stands for Low Energy High Intensity Proton Accelerator, to the design energy of 20 MeV with a peak current intensity of around 2 milliamperes. LEHIPA, this is the largest intensity, this is the highest intensity proton accelerator in the country. It has been designed indigenously and components have been developed by Indian industry, and many of them are MSMEs. These includes major subsystems like 4-meter long radio frequency quadrupole, 12-meter long drift tube linac, and this development has required precision machining of copper within a tolerance about 20 microns and accurate alignment within about hundreds of microns. In addition, ECR ion source, beam diagnostics, low-level RF system, etc. have also been developed. This technological expertise has been demonstrated, and it will serve department and country for future programs such as accelerator-driven reactor system, proton synchrotron for cancer therapy, spallation neutron source, production of radioisotope using accelerators, etc. Now I'll come to the last one. This is an activity related to Institute Variable Energy Cyclotron Center at Kolkata. VECC was tasked to make a 30 MeV medical cyclotron. The order was placed on a foreign supplier. However, due to construction delays, the supplier had demanded correctly so, increased remuneration to complete the erection and commissioning part of it. The amount was significantly high, and Dr. Shekhar Basu, the then chairman AEC, tasked VECC to take up this activity. Based on the knowledge base available with VECC, the task was initiated. This included erection of large size magnets, achieving vertical and azimuthal alignment within a precision of better than 100 microns, integration of various cyclotron systems, integration of services like low conductivity water system, power supply, control system, etc. VECC was also required to write complex control system software in-house as OEM software was not available. I would like to bring to your kind notice that this is an extremely complex work, specifically as no elaborate documentation was available with the team at VECC. So integration and error-free completion of the work by VECC demonstrate the capability of multidisciplinary engineering at VECC. This work was started during COVID, and today the medical cyclotron at Kolkata provides affordable radiopharmaceuticals to the eastern part of the country. This is the only cyclotron in India with 30 MeV energy, and hence large number of radioisotopes for medical use like thallium-201, gallium-67, iodine-123 are being produced in the country for the first time. And there is one more, I would say, advantage of this, that this has given confidence to VECC to undertake similar medical cyclotrons, and this project is under implementation to make our own indigenous medical cyclotron. So as I end, after mentioning a few one of its type examples, in the field of technology, I would like to mention that in my personal opinion, this is reflecting what Professor Manna also said, that to become third largest economy in the world, as desired by the Honorable PM, engineers of the country will need to play a significant role. This is primarily to achieve increased industrialization and indigenization. And I feel these are vital for increase in GDP. I wish all the colleagues present here the very best of luck so that they are able to put in maximum possible efforts and take India forward. Thank you very much, and Jai Hind.
Thank you very much, sir, for providing briefly about the latest achievement of the Department of Atomic Energy in the extreme engineering projects carried out at the institutes like RRCAT, BRC, and VECC. Those are related with lasers and accelerators, and the projects like LIGO, LEHIPA, and medical cyclotron. Thank you. I now request Professor Manna to present memento to Dr. Vyas, please. Thank you. We are honored to have Dr. Anil Kakodkar as the distinguished guest. Dr. Kakodkar obtained his BE in Mechanical Engineering from Bombay University in 1963 and MSc in Experimental Stress Analysis from Nottingham University in 1969. He joined Bhabha Atomic Research Center in 1964, became the director of BRC in the year 1996, and was the chairman of Atomic Energy Commission and secretary to the Government of India Department of Atomic Energy during the years 2000 to 2009. He was DAE Homi Bhabha Chair Professor during 2010 to 2015 and INAE Satish Dhawan Chair of Engineering Eminence during 2015 to 2017. Currently, he is the Chancellor of Homi Bhabha National Institute and AICT Distinguished Chair Professor. Dr. Kakodkar has worked for the development of atomic energy programs in India throughout his professional life. Focus of his work has been on the self-reliant development of nuclear reactor systems to address the Indian program requirements. Utilization of the vast thorium resources for energy production has received special attention under Dr. Kakodkar's leadership. He has created roadmap for shaping the third stage of Indian nuclear power program. Dr. Kakodkar has been a key contributor to India's strategic programs. He was among the few chosen ones involved in the first successful peaceful nuclear explosion experiment that India conducted in 1974 at Pokhran, and later he played a key role in the series of successful nuclear tests conducted during May 1998, again at Pokhran. India has also demonstrated nuclear submarine power pack technology under Dr. Kakodkar's leadership. The deployment of technologies for better quality of life of our people has received considerable boost under Dr. Kakodkar's leadership. Besides energy, these cover radiation processing of food and agro products, agriculture with emphasis on oilseed and pulses, healthcare, particularly related to cancer, urban and rural waste management, and desalination of water. Dr. Kakodkar has played a leadership role in establishing several institutes of higher learning, which include HBNI, NICERS, and DAE Mumbai University, CBS, to name a few. Dr. Kakodkar presently devotes his time primarily on the issues related to energy, education, and societal developments. Dr. Kakodkar is recipient of several professional and civilian awards, including all three Padma awards, Padma Shri, Padma Bhushan, and Padma Vibhushan. With this, sir, may I now request you to please address the gathering.
Professor Jagdish Kumar, Chairman UGC and Chief Guest of today's function. Professor Indranil Manna, President INAE. Shri Sanak Mishra, former President INAE. Fellows of Indian National Academy of Engineering present here. Dr. K.N. Vyas, former Chairman, Atomic Energy Commission. Dr. Nakhe, Director of Raja Ramanna Center for Advanced Technology and our host for this INAE Engineers Conclave 2023. Professor Pal, Director of UGC DAE Consortium for Scientific Research. Professor Joshi, Director IIT Indore. Professor Renu Jain, Vice Chancellor Devi Shri Ahilyabai University here at Indore. My dear friend Dr. Kamachi Mudali, Vice Chancellor Homi Bhabha National Institute. Dr. Ajay Mathur, Director General International Solar Alliance, and who is going to deliver the first plenary session just after this inaugural event. Colleagues from Raja Ramanna Center who are present here, colleagues from IIT Indore, colleagues from Devi Shri Ahilya University, distinguished invitees, ladies and gentlemen. I think INE has been holding this engineering conclaves year after year with a specific purpose, which our President, Professor Manna, has already elaborated. In that context, as we heard from Professor Pal, I think Indore does offer a special ambience. Uh, the host institutions that we see around, uh, RRCAT, Consortium for Scientific Research, IIT Indore, Devi Shri Ahilyabai University. And there are, of course, many other important educational and academic institutions in and around Indore. And so, and also Indore has a significant presence in terms of doing some high precision, high quality engineering. You have an industrial area very close by from here. So I think it's a right environment where we, as members and as fellows of academy, uh, should look for kind of nourishing this into a new ambience, new ecosystem that is so important for advanced India or the India in a leadership position globally. Uh, and I think collectively the institutions present here can make it happen. Uh, and I think it's coming together like this is very important. And you have two important themes as per the tradition of holding the conclave, engineers conclave. One essentially chosen by the host institution and one chosen by INAE, and both these things, as we heard from Professor Manna, are important for future of India. So I think we have an important task to realize at, uh, at this conclave. It looks to me that going forward, of course, India emphasis on manufacturing has been there because that has become the main, of course, the main prime mover of our economy is service sector. Sometimes you have to have reason for providing service too. And in that context, I think manufacture and agriculture to me are core and they should catch up. But between the two, obviously, manufacturing is more dominant contributor uh, to the economy of the country. Now, if you look at the trend, if you look at the way things are shaping up in advanced countries, gone are the days when you have this traditional manufacturing where you get manufacturing technology from somebody and then you keep on using that year after year for the whole life of that industry for that matter. Now, that's still a large component of manufacturing framework within the country, but it's becoming increasingly non-competitive. Now, if you look at what's happening in advanced countries, they are all moving towards what may call the research intensive industry. You know, if you see all the upcoming areas, frontline areas, they are all essentially the research led industries. You begin with AI, ML, which has become buzzword, darling of all young people. Everybody wants to look at that. But the question is, are we in the forefront? And there are new frontline industries uh, in the area of, call it genetics, call it cyber security, and you can name a dozen more. And these are actually, of course, there is research going on in academic environment, industry environment, but it seems to me that there is parallel, equally important and equally advanced research going on in industry. Because for them, their competitiveness is strongly dependent on the research component, which happens right within the industrial environment. And of course, they're very strongly linked, strongly connected with the universities and academic environment. And those are the industries which are actually advancing the economy of respective countries at a very fast pace. I think we have to catch on. that culture is yet to be seeded in our country. And that is, to me, what is happening around the kind of institutions that are represented here. We just heard what is happening at RRCAT and BARC from Dr. Vyas. Now, and many of them are actually getting transferred into industrial domain. For example, contributions done for RRCAT is the place where for Large Hadron Collider, a lot of industrially produced items were made. That is, the knowledge provided by BRC, RRCAT, but the work done in industry, cutting edge work, and that's what was supplied to Large Hadron Collider at CERN, which led to this major invention of Higgs boson, but of course there are many other things on standard model which are being experimented. So the point is, we must recognize the shape of things to come, because otherwise we may feel that we have done great. We are doing great. But if we don't recognize the waves of new things coming forward, we'll suddenly find ourselves lagging behind. And that is the important objective that we need to keep before us. So the question is, I just want to put forward a suggestion, and this did come because when this INE proposal, as Professor Pal said, was talked about in the governing board of the Consortium for Scientific Research, this thought did come around that there are attempts being made. Bangalore is already a knowledge city or a knowledge corridor or a knowledge hub. Pune is taking shape like that. I think why not Indore? Indore is also another place where this can happen. So Indore knowledge hub, can we imagine that? And it becomes the source for advanced knowledge-based disruptive innovation. Can we drive that model here? And I'm sure the presentations made during after this and the subsequent days, I think several interesting ideas will be thrown apart. Rather than working on them as individuals, can we say that we can complete the whole spectrum of research at one end and the industrial delivery at the other end, and do everything that is required to bridge that spectrum? And if you do that, I think that is the key to take India forward, or India being one of the leading nations of the world. So I want to, with that broad kind of idea, I want to talk about energy, because clean and green India is one of the missions, and Dr. West did talk about the other LIGO and the medical cyclotron. But energy is the important, and of course we look forward to hearing from Dr. Ajay Mathur about this energy transition. But I think, can I get the slide? I had sent some slide. So I do slide projector. So to me, the way I see the energy situation or the future energy requirements of our country, I find the whole thing very, very challenging. Yeah. Okay. Yeah. Okay. Fine. Good. So now, I just want to draw your attention to this challenge before the country, and I think it involves science, it involves technology of different kind, And above all, it requires engineering because you have to deliver this on scale. And this scale are mind-boggling. Now, to me, the current energy consumption, and I'm talking about not just electricity, total overall energy consumption is around 6,500 terawatt hours per year. Every year we are currently consuming that kind of energy. Now, how much energy we need to produce? And you, I think I'm sure all of you are familiar with this correlation, Human Development Index versus the energy being used. And you go only up to, this Plato at the top. These are all advanced countries. And once you reach that Human Development Index, which is the maximum, you can't cross one. One is the ideal higher limit. So you must have energy consumption or availability on per capita terms somewhere up to this point, because beyond that it is all wasteful. But at least up to this point you must reach, and that point is around 2,400 kilogram oil equivalent per capita. Now this transition that we expect, one of the feature would be there will be very heavy electrification. Solar energy, it can produce electricity, it can also produce high temperature heat, but it's producing more of electricity. Wind, same thing. Nuclear, same thing. Hydro, again, same thing. So all these clean energies, they're essentially, so availability of energy is going to be primarily in the form of electricity. Now, electricity system will become very large. That's one challenge. But the important thing is it will give you a lot of efficiency. And so whatever can happen or what is happening today at 2,400 kilogram oil equivalent per capita, I think in future you may not require so much of energy. Now, of course, one can have opinions, but let's say that one can reach this Human Development Index, even if you reach something like 1,400 kilogram oil equivalent per capita. So we need to reach there, multiply that with our population and convert the units to terawatt hours. Now that will come to around 28,000 terawatt hours per year. So if you have access to that level of energy, then you can expect to reach Human Development Index of 0.995 or comparable with advanced countries of the world. And that should be our aspiration, ambition. Now there is no other way of reaching there if you don't reach there. Now how do you get this to 2,000 or 28,000? Now Dr. Mathur is here and he will tell us in more detail, but Professor Sukhatme had published a very interesting and very detailed paper some years back. And even if you account for that, numbers might have changed or something. It looks to me that the total renewable energy potential in India is around 8,000 terawatt hours per year. Now you can say we may go offshore, we may find other modes. Add 25% more, add 50% more. You are not going to reach 28,000. So one assumption is, the other big thing is nuclear. And I want to do little marketing for nuclear, and this is where at least half the community here is nuclear. So the other big energy source is in fact nuclear. And so you cannot but take recourse to nuclear in a very big way if India wants to be among those advanced countries of the world. Otherwise, we have to decide that we will remain underdeveloped. I see there is no third way. So this is where that importance of creating that transition comes about. Now, that's a mind-boggling number. You want to produce that energy, translate that into gigawatts installed capacity. depends on what scenario you're talking about and all, but it will run between more than 1,500 gigawatts to around 2,500 or even larger gigawatts. We are at around 7 gigawatts right now. 7,000. So you can imagine the gap that we need to cover. And there is no alternative, I'm saying, for India to be developed to become that. So you need a very big role for nuclear, and that is necessary for meeting our development aspirations, as I say, but it's also required for affordable electricity. See, there are some papers, Central Electricity Authority has, I think in a recent seminar, they have come out with some numbers, and they are talking about the round-the-clock renewable energy, essentially by creating storages, both battery storage as well as the pumped hydro storage. And then they are looking at different scenarios as to you get wind from one state and solar from another state, so that if you look at the 24-hour energy cycle, you can smoothen that out. But the integrated tariff, if you do that under different scenarios, it ranges anywhere between 5.8 to around 7.58 rupees per unit. These are CEA numbers, fresh CEA numbers. Now, DAA has commissioned 700 megawatt PHWR, and there are, I think, 15 more such units under construction. And that tariff, the first unit tariff, of course, tariff keeps on evolving, but it's around little more than 5 rupees, 5 rupees 15 paise, somewhere there. So the point I'm trying to say is, while nuclear as a source is required, because without that you don't have a source, it's also economic. So that meets the second bullet, affordable electricity. And of course, you need that for climate security. Because you can achieve net zero. Well, the question is net zero at what level of energy availability? If you achieve net zero at a much lower energy availability, then your development is at stake. So this is the challenge that we need to do. And of course, you will require, as I said, most of it is available in the form of electricity. I hope and wish that even now we give more attention to solar thermal, because then the storage option becomes that much cheaper. And in any case, while you may have produced so much of electricity, at the consumer and at the demand, you will require a significant fraction of that energy for other purposes, for heat and chemical reactions, material transformation, and so on and so forth. And so electricity and hydrogen are going to be the two most important sources which the users will want, the consumers will want. And today our emphasis on hydrogen is on electrolyzers, because there is no another option right now. But recognize, when you say you first produce electricity, then you use that electricity to electrolyze hydrogen. So there is double efficiency loss. Iodine sulfur process, which has been developed at BARC, which Dr. Vyas was mentioning. First of all, I want to reinforce that by saying that that's the contemporary development. There is development going on across the world, but we are, I think, the front runner, or at least among the front runners in that technology globally. But wo ghar ki murgi dal barabar, that problem is there in many cases. And that pilot plant is running on round the clock basis. And there are many other opportunities. You can do that in an integrated manner. You can couple it with, for example, industries where there are sources of sulfur, either say copper, zinc, or even say refineries. Now you can couple segments of that process in a more beneficial way, and that hydrogen production would be, I think, first of all, it's going to be way cheaper than electrolyzer, and the so-called economic benchmarks which are people are talking about, dollar per kilogram, I think, no? Dollar per kilogram. Now, those kind of thing, if you want to make, it's right now it is far away, but you need to do this kind of thing. And the point I want to stress is India is the front runner in doing this. So we need to create this ecosystem which we are talking about. The research, the industry, the manufacturing, scale up. And that is, I think, extremely important. So I'm not going to spend time. I know there are papers going to be presented. I think Dr. Grover is talking here, no, tomorrow. So we will certainly hear more details about it. But you need products. It's not as if a single product will deliver this gigawatt level of electricity. But you have the 700 megawatt well done, standardized thing, extremely safe. I don't have time to describe all that. One fleet is under implementation. I think we should take up maybe 4 or 5 fleets with different delivery agencies, NPC1, NPC2, NTPC, and DERAS. Similarly, there is, there are a large number of coal plants, and many of them will retire, and that number runs in hundreds. If you take next 10, 15 year scenario, many coal plants will be ready for retirement. So these are all brownfield opportunities for setting up SMR. And I think we should develop an indigenous product, because if you produce these reactors in the country, the cost is half. You ask for same reactor or PWR. PWR theoretically should be cheaper than heavy water reactors, but you import PWRs, it will cost you at least twice. And that has been the problem DAE has been facing all along. So I think you develop these products domestically and have a fleet of SMRs located at the sites vacated by retiring coal plants, because other infrastructure is available. Railhead is there, water is there, the grid connectivity is there. Similarly, there is a new trend which is emerging. See, industry actually, they are more forward looking than academia, and many times than government also. And industry, in fact, they have contacted me many places. I'm sure they have contacted DAE, and they are now vying for captive power plants. See, for example, steel industry. Tomorrow, if the steel is not green, they will not be able to export. You may use it in the country, but once those yardsticks are say export will finish. Same thing is true about chemicals, and also, so unless industry is fed with green energy at a competitive cost, our industrial activity will be under a great threat. And in that context, I think there is space for even existing 220 megawatt units, which have been very well proven, to be built as captive power plant. And industry is prepared to pay money, so it can be completely outside this and do that. Advanced heavy water reactor, which has been designed and very large scale development has been done, that can be also deployed in a similar load. I talked about hydrogen. You want to produce hydrogen through either iodine, sulfur, copper. Even copper chlorine process, India is very advanced at ICT. That process also is developed. So you want to do that, you need high temperature reactors, just as you need the CSP, concentrated solar power plants. I also champion thorium. That has been my lifetime ambition. And I think thorium and LEU in PHWR, actually it works wonders. So here is an export opportunity. There are many, the threat to the globe on global warming will come from countries which are developing, which energy requirements are growing, like India. That's why people are putting pressure on India. Same thing is true with the emerging economic countries, and they have a huge hunger for clean energy, and the same arguments will hold good. And if you can deliver an energy system which is safe, which is cheap, and most importantly, which is proliferation resistant, because one of the barrier for nuclear deployment is this concern. And here India has an opportunity to export and do lot of manufacturing activity in the country. And then, of course, we must carry on with the large PWRs we're talking by built by collaboration with our foreign partners, and a domestic three-stage program consisting of fast breeder and molten salt reactor. So you can imagine the level of challenge. We have the products, development done. The question is scaling it up, taking it to the industry. So this part has come in the domain of engineers from the researchers. And so the community of engineers, please do something. Thank you very much, and I wish all of you great success.
Indeed, sir. We must recognize the shape of the things to come. Thank you for emphasizing the ecosystem with connections in various academic institutes, research-led industries, and highlighting that it's the time to bring nuclear energy onto the center stage. Thank you very much. I request Professor Manna to present a memento to Dr. Kakotkar. Thank you. The program for Engineers Conclave 2023 includes 4 plenary talks, 1 evening talk, and 8 technical sessions having about 30 presentations on topics of the 2 themes that we have identified. An abstract book has been prepared summarizing the essence of these presentations that will be made during this event. To mark the inauguration of these Engineers Conclave 2023, may I now request the chief guest and the dignitaries on the dais to please release the book of abstracts.
जैसा कि हमें ज्ञात है कि आज इंजीनियर्स कॉन्क्लेव 2023 के मुख्य अतिथि विश्वविद्यालय अनुदान आयोग के अध्यक्ष आदरणीय प्रोफेसर जगदीश कुमार जी हैं। प्रोफेसर जगदीश कुमार जी एक शिक्षाविद, इलेक्ट्रिकल इंजीनियर और शिक्षा प्रशासक रहे हैं। वह आईआईटी दिल्ली में इलेक्ट्रिकल इंजीनियरिंग विभाग में प्रोफेसर हैं। प्रोफेसर कुमार ने जनवरी 2016 से 2022 तक जेएनयू कुलपति के रूप में कार्य किया। वह नैनो इलेक्ट्रॉनिक डिवाइस, नैनो स्केल डिवाइस, डिवाइस डिज़ाइन और पावर सेमीकंडक्टर डिवाइस के क्षेत्र में काम करते हैं। वह वर्तमान में इंस्टीट्यूशन ऑफ इलेक्ट्रॉनिक्स एंड टेलीकम्युनिकेशन इंजीनियर्स, नेशनल एकेडमी ऑफ साइंसेज, इंडियन नेशनल एकेडमी ऑफ इंजीनियरिंग में फेलो हैं। वह राष्ट्रीय विज्ञान संग्रहालय परिषद के गवर्निंग बोर्ड के अध्यक्ष हैं और हमारे लिए इससे भी महत्वपूर्ण यह है कि वो अभी इस कंक्लेव में मुख्य अतिथि के रूप में हमें संबोधित करने के लिए उपस्थित हैं। आज सुबह उनके साथ विचार विमर्श हुआ, उसमें यह प्रतीत हुआ कि वह बहुत ही सहज, सरल, सुलभ और मृदुल भाषी हैं। तो मैं निवेदन करता हूं प्रोफेसर कुमार को अब मुझसे।
Hello. Yeah. Yes, it's good. Do you like a free electron or a bound electron? So I want to be a free electron. And in the afternoon, when you have heard so many good lectures, I'm sure you are already tired. If there is a moving object in front of you, you will remain alert. So I thought, let me be the moving object here. My thanks to Professor Manna for inviting me here, Dr. Kakotkar, Dr. Vyas, Dr. Nake, Professor Manna, and Professor Paul, my distinguished colleagues, and the young students who are there in different parts of this hall. My namaskars to all of you. I am very honored to be here on this stage during this engineers conclave that we are conducting, INAE is conducting. I'm also thankful to my previous speakers for taking some of my time. So I'm cutting down my time, so I have put an alarm there. So when it rings, I will stop. Friends, during the talk, we heard Dr. Kakotkar saying that both agriculture and manufacturing are important for the development of our country. And the INAE president, Professor Manna, she said, engineering is transforming our ideas for societal good. So I would like to expand on this because often in conclaves like this, we talk about futuristic technologies. Obviously, the two topics that they have selected, laser technology, green and clean technologies, they are futuristic technologies. And of course, we need to discuss about them, starting from quantum computing to space technology, starting from radio waves to the gravitational waves. We must work on futuristic technologies if our country has to develop. But at the same time, that is one side of the coin. The other side of the coin is in the words that Dr. Kakotkar and Professor Manna have said, the societal good and agriculture. Agriculture is one component of this societal good. So I want to capture what they have said using the words of our Honorable Prime Minister. Just last week, when he was speaking somewhere, he said if our country has to develop, there has to be grassroots development. And that is what both of our esteemed colleagues meant when they said we need to strengthen agriculture and we must work for societal good. So I want to expand on that. When Prime Minister said that, his voice, it resonated with the deliberations in G20. For example, the G20 deliberated on the challenges associated with the uneven economic growth, the failing economic systems, the issues related to extreme poverty, the multidimensional poverty, and the need for creating shared prosperity. Now, these are all related to societal good. And the most important aspect of climate change. It was deliberated and a consensus was arrived at the initiative of India about the climate financing. Climate change is very closely related to the environmental degradation, the biodiversity loss, pollution, the deforestation, desertification, lack of access to clean water, land and ocean degradation, and we are all struggling to keep the increase in the global temperature below 2 degrees centigrade as compared to the global temperature of pre-industrial times. So these are all challenges related to the societal good. And one very important thing the G20 discussed, which our Prime Minister often mentions, is that the development has to be women-led development. And G20 agreed on that. There was a consensus on that. The fact that there are reduced opportunities for women and girls. We are targeting to become a developed country by 2047. Currently, our GDP growth is about 6.5, 6 to 6.5. And it is estimated that the growth has to be, GDP growth has to be 8% if we want to become a developed country. And that is possible only if the development is women-led. Now, these are issues, these are the challenges that we need to address. And that's the reason why today experts recognize that sustainable rural development is key to our country's overall progress. Let me tell you why. So in year 1800, nearly 97% of Indians were living in rural areas. After 223 years now, we still have 65% of Indians living in rural areas. That is a staggering close to 90 crore. And you all know that 50% of Indians are below 25 years. That means nearly 45 crores of young people, they are living in rural areas. So unless we achieve sustainable rural development, we will not be able to make our country a developed country by 2047. That is the reason why, as engineers, scientists, and technologists, we must come up with interventions. We must come up with strategies which are in tune with the changing societal, economical, and environmental dynamics that is taking place. And that's the reason why experts say that sustainable rural development is possible only if we do three things. I would like to highlight these three things. Number one, we must ensure that the rural communities have multiple economic activities. They should not depend only on agriculture in order to meet the urban demands. And we must encourage local entrepreneurship in order to sustain and expand these multiple economic activities. And most importantly, we must strengthen the social capital. Let me explain. You're all scientists and engineers. Just like me, I am a professor at IIT Delhi. We rarely think, when we are so busy doing our experiments, our engineering feats, we rarely think about the social capital. Social capital is all about recognizing the importance of social interactions, social relations, social mutual trust among the rural communities. It is all about promoting the local leadership, encouraging the women collectives, making sure that individuals and communities get support from these social networks. It may appear to be very abstract when I said this. Remember in 2001, on January 26th, at 8:46, what happened? Do you remember that? There was a huge earthquake in Kutch area. More than 20,000 people died. More than 1 lakh people were displaced and houses were razed down. a group of doctors from Mumbai went to Kutch area in the rehabilitation work. And they reached a village, half of the village people were dead. But they found that the rest of the people, they were reconstructing their lives. The lady who was cooking the food for this group of doctors, she lost all her 3 children. She lost her husband. Her house was damaged, but still she was coming and cooking food for these doctors. That is what is social capital. So when the doctors asked her, in this hour of grief, how is that you are able to come and cook for us? She said, as soon as the earthquake took place, the elders of the village called us. They said, whatever has happened, that is past. We cannot get back our lost people. Let us focus on our future. Let us help each other. And that is what is the social capital. If you want to achieve sustainable rural development, we must focus on this social capital. And often as policy makers, as scientists, as engineers, we think that we have a solution for the problems of the rural community. We come up with a policy. It's always a top-down approach. You remember when the cochlear implant was invented 50 years ago, the scientists thought they had a great invention and it will help the deaf people. So they went and approached the deaf societies. And what did the deaf people say? They said, yes, we are deaf, we are born deaf, but we are just like you. We can do anything else except hearing. So why do you want to spoil our life with your cochlear implant? So that is the disconnect we will have if it is a top-down approach. What we must do if we want to have sustainable rural development is a bottom-up approach. Involve the people in decision making. Democratize the processes of making the policies and the strategies. When you do this, people own these policies, own these strategies, and it will ensure that the solutions that emanate from these are socially and culturally rooted. And this is something as scientists and engineers, we must constantly think about how to democratize the processes that will help these rural communities. Other major problem the rural communities face is how to manage their natural resources. After all, the global population is going up and there is a huge demand on the materials that come from the rural societies, the services that are provided by the rural communities. And unless we educate, we create awareness among the rural communities to adopt sustainable practices so that the climate issues, the climate change issues are not mitigated, so that their dependence on fertilizers is reduced, so that they adopt efficient water and energy management systems, so that they will adopt climate centric, climate smart approaches in their activities. You cannot achieve sustainable rural development. Friends, let me also tell you how engineers can play a major role in bringing sustainable rural development. We have seen how the digital technology and communication technologies are changing the lives of the rural communities. Today there is increased financial inclusivity. Nearly 80 crores of bank accounts are created and money directly goes to them. And today we have, through mobile networks, through phones, the farmers and the rural communities have access to weather forecasts, agricultural advice. They have access to the markets. The best example is the open network digital commerce platform that we have designed in the country. And this is what is the digital public infrastructure that India is now leading in the whole world. And this is where our engineers and scientists are playing a critical role. It has become an envy to the rest of the world. the digital public infrastructure that we have developed. It is open source, it is interoperable, it is secure, and you can see today more than 40% of the online financial transactions that takes place globally, they are from India. And today you have voice-based banking. I may not know English, I may not be able to use my cell phone, but I can use the voice-based banking and carry out my banking operations. And that is how science and technology can go down to the last person and change their lives. Friends, another important thing that I would like to bring to your notice, because we are all scientists and engineers. Most of the rural communities, they are faced with so many challenges, including disasters, including financial challenges, lack of access to healthcare, education, and so on. So building resilience among the rural communities is also extremely important. How many times as a scientist, as an engineer sitting in a lab, we think about these issues? The reason why I'm telling is the days of working alone in the lab without thinking about the society are gone. We should be constantly thinking about how what I am doing is going to impact the rural communities. So the bell has come on this. So I have spent 16 minutes. I will take one more minute. Friends, if you want to change the lives of our rural communities, education is the only solution. And especially for those young people who are there across the country, in the towns and the villages, we must ensure that they are provided with skill education and vocational education. It's not that everybody wants to come to a city and study a master's program or a doctoral program. They have pressing issues, they have financial issues, they want to look after their family. Can we provide high quality skill and vocational education to them? And another biggest challenge our rural communities face is the language barrier. We think that if somebody is unable to speak in English, if somebody speaks with faulty grammar in English, it's something not a good thing. But time has come now to focus our attention back on our Indian languages. There are 40 crore Indians who do not know English, and you can't expect them to learn English and then become skillful. Therefore, the skills and vocation, the education that we'll provide to these youngsters has to be in our Indian languages. So my appeal to the engineering and scientific community here and also to INAE is to constantly come back, keep away from your work for a few minutes and think about the society and think about how your work can positively bring change in the lives of the ordinary people across the country. And that is the only way we can develop our country fully by 2047. Thank you. Thank you very much.
आज के महत्वपूर्ण सामाजिक, वैज्ञानिक व तकनीकी विषयों पर अपने विचार रखने के लिए महोदय आपका अनेक अनेक धन्यवाद। अब मैं हमारे यूजीसी डीएई वैज्ञानिक अनुसंधान संकुल के सम्मानित निदेशक प्रोफेसर अमलान जयपाल जी से निवेदन करूंगा कि वो जगदीश कुमार जी को स्मृति चिन्ह प्रदान करें।
Dr. Shankar V. Nakhe, distinguished scientist and director, RRCAT, is a leading laser expert of the country. He is spearheading the center to excel the frontiers of science and technology in lasers and particle accelerators, as well as several lab-to-lab initiatives under Atal Incubation Mission initiatives of the Government of India. I request Dr. Nakhe, the overall coordinator of EC 2023, to propose the vote of thanks.
Thank you. Very good afternoon to all of you. Today, RRCAT is witnessing unprecedented gathering of stalwart engineers of the country, and we are very much honored to hold this engineers conclave here. And friends from RRCAT, you will agree that we have a feeling like मानो तारे जमीन पर जैसे यहाँ अपने ऑडिटोरियम में ये luminaries यहाँ पे present है. Of course, on the dais and off the dais also. I will not name each and everybody here. And जो भी presentations हुए हैं, मुझे ऐसा लगता है जैसे ज्ञान की गंगा का बहना यहाँ चालू हो गया है. And I'm sure this trend and tradition will continue throughout this engineering conclave. So with this, I'm very much filled with feelings of gratitude towards all dignitaries, and let me express my vote of thanks on this occasion. So first and foremost, I would like to thank our chief guest, Professor Jagdish Kumar, Chairman UGC, and he has spared his valuable time and guided all of us here, and I'm sure his thoughts are very much out of box and will be thought-provoking for us. Sir, Indore has done the same thing. The cleanest city has come like this. There is a movement from the bottom to up. Everybody, every citizen is contributing to that, and of course there is a support from top side also, and that's why the Indore is cleanest city of India. And as you said, example is here, and our campus is the cleanest campus of the city also. So we are very much proud to be of that achievement. So thank you, your words of advice, and we'll keep that in mind, and they're definitely guiding us in future. Dr. Kakodkar sir, today's distinguished guest and former chairman AEC, he has been very much instrumental in having setting the themes of this conclave, although he has guided in only one or two occasions, but the most important part of the conclave, he has guided in setting the themes that are quite relevant and bringing those very pinpointedly to us. Sir, listening to your lecture is always a new learning experience, and you are guided here, and we thank you very much for your presence in this conclave. Dr. K. Vyas, Homi Bhabha Chair Professor and former Chairman AEC and Secretary Department of Atomic Energy. His talk has been very interesting and brought out many engineering and technological developments. Vyas sir has encouraged to have this event in RRCAT when he was working as a chairman of Atomic Energy Commission, and he promoted us to have this event at RRCAT. Thank you, sir, for your contribution to this program. I would like to thank Professor Manna, President INEA, for agreeing to our request and to have this flagship event of INEA at RRCAT Indore and at Indore to be precise, and at RRCAT as the venue. Sir, thank you very much, and he has provided guidance at various points in organizing this event, and his crisp guidance and quick decision making has made this event a great success. I would like to thank Professor Amlan Pal. His foresightedness has brought this event at Indore and again at RRCAT. Thank you, sir, for getting this event at Indore and contributing in organizing this event. Under your guidance, this event is very successful. I would like to thank all dignitaries, speakers, invited speakers, participants, session chairs, and theme coordinators for their contribution to this event. I'm sure with their contribution, this event will be successful, and there will be very strong and justifiable
recommendations that will be coming, and implementation of those justifications and recommendations will definitely take our country ahead. I would like to put on the record the hard work put by INEA office and particularly Colonel Shobhit Roy and his team who coordinated from Delhi in organizing this event. There were a lot many back office activities that Dr. Roy and his team has coordinated. Thank you very much for all your contributions. I would like to thank all committee members here who has contributed and organized this event very smoothly. I would like to thank all partnering institutes and their various agencies who have contributed directly or indirectly in making this event successful. I would like to put on record and thank the support from members from press who had been covering the event appropriately and always covering good events at RRCAT with very positive outlook. And your coverage of events at this center is very important, and I'm sure it gives good signal to the society and it creates a collaborative effect on a very large scale. Thank you, all the press members. And I would like to thank all of you for your very enthusiastic participation in this event. I'm sure your enthusiasm will make this event a grand success. And let us work together, carry this networking, knowledge, and inspirations from this conclave and make our country great, Vishwaguru and Atmanirbhar Bharat. Unless we work together, that will not happen. That is the message that is very clear from our chief guest today. So let us work together. I'll call this Om Tejasvina Madhitamastu, that is from our Upanishads that guide us on this front. Thank you. Thank you for all your participation. And I wish a wonderful event and grand success for this. Thank you.
Thank you, sir. We now move on to the first plenary session of this conclave, and I request Dr. Kakodkar to please chair the session, and I request the other dignitaries on the dais to be comfortable in their seats in the auditorium.
पॉकेट में डालना कि इसकी पॉकेट में डालना है? जेब में डालना, इसमें डालना है। बस दिस इज ओके, हो गया, राइट, थैंक यू। Oh, okay. Okay. So do we start?
Yes.
Okay. Why don't you pull a chair? Sir, I'll be standing next to you. Well, after that little prolonged inaugural session, maybe I played some role in prolonging that. But let's begin the first plenary talk to be delivered by Dr. Ajay Mathur, Director General, International Solar Alliance, and he is going to talk to us about the all-important subject of energy transition. To introduce Dr. Mathur, I'm sure all of you know him both as the Director General of International Solar Alliance and also the former chair of the Indian Bureau of Energy Efficiency, all the star ratings that you see everywhere. So architect is here, and I think that has been a major contribution to the energy saving and energy efficiency of devices in the market. Of course, he has a large list of achievements and contributions, including before he took over as the DG of International Solar Alliance, he held the position of Director General of TERI. He was also a former member of Prime Minister's Council on Climate Change, former co-chair on Global Energy Transition Commission, former co-chair of Clean Cooling Initiatives One Planet Summit, India's spokesperson for climate negotiations at the United Nations Climate Change Conference at Paris, all important Paris we all remember, and the former interim director of Clean Climate Fund. And there is a long list. And I take your permission not to read it. Absolutely. There is. But I think we're going to hear a very important discourse on the energy transition, which is something which is bothering all strata of society, not only in India, but across the world. So without too much ado, let me hand over the platform, the floor to you, Dr. Mathur. I don't know whether I have created him, but he has volunteered. He's asking, "Come kar de time ko." So I am hesitant because we want to listen in full. But let's say 20 minutes you present, and then 10 minutes we'll have question answer session.
A very good evening to all of you, Dr. Kakotkar, ladies and gentlemen. As has been said, the energy transition is a very, very difficult subject, both to comprehend and even more to be able to fix what should be our next steps. Whether it is in our lives as users of energy or it is in our professional jobs as industrialists or as policymakers to figure out where is it we should be putting our money in as far as investment is concerned. And the reason is that what we are seeing is a complete change in the way energy, both electricity and non-electricity, is being produced. Next. 3.9 and 4.21 rupees per kilowatt hour. This is for 960 megawatts. It's not small. Of this 960 megawatts, 700 megawatts is for 4.1 rupees per kilowatt hour. 4.1. And the reason why I'm saying this, because if you compare it with the most recent coal power plants which have been commissioned, they started being put into place a long time ago. The price is being determined. So there are two ways price is determined. One is through a bidding process, you find what the price is. The second is you say this is what my total costs are, and the regulator sets a price based on what your costs are plus something more. So the coal power plants have gone through the route of the regulator setting the price. And that price has been set at a minimum of 5 rupees, is between 5 and 5.5 rupees per kilowatt hour. The short point I want to make is that solar plus wind plus batteries is today cheaper, even in India, as compared to coal-based electricity. This is if you ask me, this is a major change. This is a change that happened about 2 months ago. But what it implies is that it is going to be very difficult to find financing for electricity that is more expensive. So let us say that 5 rupees per kilowatt hour is the price at which electricity will be acceptable. It will be very difficult to find financing for something which is more than that. Having said that, one of the things I want to leave you with is that while 100, if you need the equivalent of 100 megawatts of electricity from coal at 85% availability, generally this is typically what is done, you will need 180 megawatts of solar. You will need 120 megawatts of wind, and you will need 120 megawatt hours of storage. This is to replace 100 megawatts of coal. The price, the investment price becomes double. Investment price becomes double. But because neither renewables, neither solar nor wind need any fuel while operating, it's the sun and the wind which provide them the fuel, the net price of electricity is still less. So what is our challenge? Our challenge now is how do you find the total amount of money that you will need? Yes, there are questions on how much renewables we can do. Dr. Kakotkar talked of the paper that Sukhatme Saab had written, I think somewhere around 2010 in Current Science, if I'm not wrong. It has been the subject of a huge amount of discussion. In that paper, I think he had said that the maximum amount of wind India can have is about 65,000 megawatts. We are already at 50 plus. And the reason is very simple. At that point of time, the maximum hub height of those wind machines was something of the order of about 60 meters. And he had assumed that you can go up to maximum of 90 meters. Well, we already have machines which are being put now, which have hub heights of 110 meters. We assume that today 150 meter hub height, because the higher you go, the better the wind speeds. And therefore, the same machine can produce more kilowatt hours for every megawatt hour, for each megawatt that it is designed for. What we are seeing is therefore a huge change in the way we have looked at energy generation. I'm sorry, this उधर करना किधर? I think I'll just push this and that's better. Okay. Now, I completely agree with Dr. Kakotkar that nuclear has played and will continue to play an important role in the energy transition for a variety of purposes. I did not know of the 700 megawatt PHWRs. If I understand correctly, the price today is something of the investment cost is something of the order of about $1.3 billion per megawatt, $1.3 million per megawatt. But the point simply is that they are there, and therefore they provide us with the base power and base carbon-free power that we need. What is amazingly important is that we are able to get small modular reactors into the market soon, and that these start producing electricity at prices which are competitive, let's say 5 rupees per kilowatt hour. That will determine whether the above slope of an increasing amount of electricity from nuclear comes in, or if we are not able to do that, then we will go on the lower one as more and more plants retire. And if the prices of nuclear electricity is more expensive, then we will probably not see those replacements, at least not in the same amount as you would. And therefore, a large part of our energy transition depends on the fact that we are able to develop small modular reactors which are cost effective. I would like to emphasize this because nuclear is essential and we cannot have nuclear electricity at large scale, which is much, much more expensive than other electricity. So this is one of the challenges that we face. Next, please. Next, this is going back. Next, yeah. Now, if I look at the various renewable energy sources, one of the things that we are seeing is that the price of most sources of renewable electricity are declining. One of the, I see that it is not very clear. You can probably see the numbers there, and you will see that in the case of both gas and coal, we are seeing increases in price over the next till 2030. But on the other hand, for most of the non-carbon emitting sources, whether it is solar or onshore wind or nuclear, we expect that prices would become less in the years to come. In other words, the price reduction will continue to occur for several years ahead. It is this combination of price reduction on the one hand and of the availability of large-scale infrastructure on the other hand, including the ability of a national grid, which is able to get solar from one part of the country, which is able to get wind from another part of the country, and possibly battery storage from a third part of the country, and mix it together so that you and I continue to get electricity as to when we want. We are in the process of carrying out an analysis of what is the amount of land that India would require for this. It is our estimation that the total amount of land that India would require would be something which is in the vicinity of 30,000 square kilometers. This is a large number. It reflects approximately 1% of the total land area of the country. But if I look at it another way, it's about somewhere less than 50% of the area of the Thar Desert. It is approximately half, or more than half actually, it is about 80% of the area of the Little and the Greater Rann of Kutch. Areas where both solar and wind are happening. The short point is that while 30,000 square kilometers is a large area, it is not an insurmountable area. Whereas we have not focused on land acquisition and land availability, we will need to focus on that in the years coming ahead. Next, please. The point that I want to leave you with is, yes, of course, solar is in most parts of the world the cheapest source of electricity, but only when the sun is shining. How is it that many countries are able to get a very high penetration of solar and wind renewable energy and still be able to meet all their demands, whereas many others are not able to? The answer lies if they have access to storage. And most of the North European countries, for example, have access to the huge hydro potential that is available in Norway, which is the reason why countries like Denmark, countries like Germany are able to have 100% renewable days and reach somewhere in the vicinity of 80%. Costa Rica is a largely hydro-driven country. It is this availability of storage which makes it possible for us to use solar and wind. Without storage, solar and wind cannot work. Remember, the cheapest electricity that we have found till now is solar plus wind plus storage. This, therefore, becomes a key technology development area for us. Next, please. At the outset, what I'd like to focus on is the fact that supposing, we've had a large decline in the price of batteries. Since 2008, the price has become, is 10%, 1/10 of what it was in 2008, in 2023. But even now, solar plus battery alone is not cost effective. But it could be. It could be if the price reduces by a further 20%. Based on our estimates, that should happen in the years, this year, 2023, or 2024, or 2025. Certainly before 2026, we will probably see battery prices becoming low enough so that solar plus batteries should be able to provide electricity, not solar plus wind plus batteries. So the country will have choices. There are parts of the world where solar is good. There are parts of the world where wind is good. So solar plus wind, or hydro, or wind plus solar plus storage, or wind plus storage, either way can make a situation in which you can get the vast bulk of your electricity from these sources. Remember that I say vast bulk of the electricity. It will not ever, in most of these countries, it will never be all. For that, you need something of the sort of nuclear electricity. Next. Next. Okay. I talked of the large reduction in the price of batteries that has happened. So there are three things that are happening. One is that price reduction is occurring because the amount of the critical materials, the more expensive materials that are used in batteries, have been reducing. And what we note is batteries made today, lithium batteries made today, use 10 to 15% less lithium than they did 10 years ago. This is because of competitiveness between various producers of lithium batteries. In order to sell more, they have to innovate. And innovation in terms of using less lithium is one of them. The second thing that we are seeing is that we are finding lithium even in places where we didn't. So for example, there was this All India Geological Survey that occurred in the late 60s. And when there was a lot of geological mining, surveying done in Ladakh, they found a lot of bauxite. They weren't even looking for lithium. But now when they went back and were doing the prospecting for taking out bauxite, they also found lithium. The short point I'm saying is that geology follows where the demand is. Once lithium came onto the list of critical materials, we started looking for it. So you start finding more lithium, that's number one. You start using less lithium per battery. And the third is that we are now using batteries which don't use lithium at all. Vanadium redox batteries. There is a building in Bhopal, a large building, which uses solar and uses vanadium redox batteries. So commercially they use it. And they're able to have prices which are competitive with the prices that the electricity company supplies to them, which is 7 rupees point something. But we also have other kinds of batteries. You have sodium ion batteries. And a very large Indian company has recently bought a company, a startup in the US and another in the UK, which are using sodium ion batteries and also antimony-based batteries for storage. Because what they say is, while they cannot be, because of the high temperatures, they cannot be used for mobile purposes, they can certainly be used for storage of electricity that is generated from the grid. Next. Now, Dr. Kakotkar talked about the fact that we will more and more electrify the future. This we see, for example, happening in the cars that we drive. A very large number of vehicles. In India, there are a lot more vehicles which are two-wheelers rather than four-wheelers, which have become electric. But we are seeing a progressive electrification. I have been driving an electric vehicle for the last 2 years. What I needed to do was to set up a charging station in my office and a charging station at home. In other words, a large array of charging stations is necessary. Shri Prakash Saab is here. 3 or 4 years ago, when pandemic happened, he led a survey of potential buyers of electric two-wheelers. And one of the things that they found was the people who were the potential buyers of electric two-wheelers said, I don't see charging stations, so I will not buy. But then we talked also to people who had already bought electric two-wheelers and asked them, where do you charge? And they said, we charge at home. So people need to see charging stations in order to alleviate their range anxiety. We therefore need to have a model in which low-cost charging stations can be put up. I would suggest that charge of the cost of the charging stations charge all of us, like the renewable portfolio obligations helped bring down the cost of renewables, and they were socialized amongst all of us. So similarly, all of us will pay a little bit, and we computed that it will come out to approximately 2 rupees, 2 paisa per kilowatt hour for a very dense network of charging stations. That would enable you and I to feel comfortable that at least in urban areas, we will be always near a charging station. The problem comes when you start talking of long distance transport, because long distance transport can be done by electricity. Yes, it can, but it needs a lot of battery. And a lot of battery is heavy, which is therefore a weight penalty on the truck. Using hydrogen becomes more acceptable. And you can, especially if you put a fuel cell with the hydrogen storage, then you can create electricity to run it at a much cheaper cost than you would with even as compared to a diesel-based system. There are trucks which have been in use for 5 years plus in China, in the US, which use hydrogen and fuel cells and have been working relatively smoothly, though I must say that the prices are something on which we have not been able to get the detailed breakup as we would have liked. Next. Okay. This takes us immediately to green hydrogen. Dr. Kakodkar mentioned that green hydrogen for the non-electricity part is the way forward. I hope that the iodine sulfur systems become cost effective. As I understand, they're technologically shown, but we need to show that they're commercially proven as well. Today, if you use solar electricity to electrolyze water, it costs about slightly less than 5 rupees a kg of hydrogen. But if you reform natural gas and produce hydrogen, which is how it is done for the vast amount of the fertilizer industry, vast amount of the refinery industry in India, then the price is about $2, 160 rupees a kilo, 180 rupees a kilo. There's a huge difference between $2 and $5. We will need to have a strategy to see how this comes down. And one of the key challenges is, if we have got various kinds of electricity, how do we ensure that the capacity utilization factors of the electrolyzers remain high? Because solar is available for some of the time, wind is available for some of the time. Would they run on nuclear electricity? That's quite possible. But if these are set all over the country, we will need to ensure that they get electricity, or that we have electrolyzers which can work at high efficiency at cost-effective capacity utilization factors. This is an engineering challenge that remains with us. Next. So here again, the problem is one of the capital cost, capex. Because for hydrogen to be produced, you are putting in a lot of money into the electrolyzer. You are putting a lot of money into the solar panels which will produce the solar electricity. And therefore, we need to ensure that this gets a return. Therefore, either it is worked for a very high capacity utilization factor, or the costs come down. Next. The other thing that we are looking at, and Dr. Jagdish Kumar had referred to the fact that digitalization is completely changing the way in which we look at various things in our lives. This is true of energy as well. The fact that, look at batteries. Batteries absorb electricity at some time and can be producers of electricity at other times. Similarly, you, as the owner of a PV module on your roof, can be a producer at some times and can be a consumer of electricity at the other time. How do we keep track of these exchanges of electricity, especially if they're at a very large scale? To me, the only answer is digital. Consequently, we will need to look at business models that are made cost-effective through the use of digital technology. So to me, decarbonization goes hand in hand with digitization. What is also very clear, as Dr. Kakotkar mentioned, as Dr. Jagdish Kumar mentioned, is that we will need to ensure that a vast number of people across the country have access to electricity, which means that you set up decentralized systems. Oops, everybody's already connected to the grid. Right. Then we are looking at energy that is embedded locally for local use, but is connected. So therefore, there is an energy security. When this embedded system, which is a small system, does not have enough electricity, the electricity can be drawn from the grid that connects it. But at other times, you can get electricity from the grid connection. This is where grid connectivity helps. But the decentralized electricity, because of its lower cost, because it is closer to where the users are, helps us in ensuring an autonomy of supply, control of people over the electricity that they get, much as you have when you have an inverter at home or a diesel genset at home. Next. So where does this leave us? This leaves us with, in my belief, 4 engineering challenges. First is the challenge of batteries. The second is the challenge of developing low-cost SMRs and at the same time carbon capture, utilization and storage, CCUS, which I haven't talked of at all till now, but I am assuming that 100% carbon-free will possibly not be possible by 2070. There will be some amount of carbon dioxide that will be produced, but it will need to be captured. And that's why cost-effective CCUS is important. The third is charging infrastructure. Very clearly, if we want the electricity vehicles to take off, we will need to provide the security that they can get electricity to charge them as and when they want, where they want. And finally, electrolyzers. This is important for the non-electricity part of the energy system, where we are looking at seeing where is it that we can find zero carbon energy. Hydrogen is the answer, but we need to ensure that we have a cost-effective production schedule. This also leads me to suggest, next please, this also leads me to suggest that the National Academy of Engineering could possibly look at these transitions from the eyes of its expert fellows and get these expert fellows to write about these issues. It will be great, for example, Dr. Kakodkar, I'm looking at you, it will be great if you could pen something which is focused very much like what you talked about in your lecture, the big picture. I would also like you to write about the about what we are doing as far as the 700 megawatt PHWRs are concerned, what we are doing as far as the iodine sulfur systems are concerned, about the SMRs. But I think the wisdom in this group, in the National Academy, is such that this is something that would be of help to all of us. We're looking at moving ahead, whether you are looking at it as a student, whether you're looking at it as a professional, these are issues that we will need to address as we go along. So therefore, those are the 5 things that I have thought about, but those 5 could become 10. I would suggest 6th, engineering education. When I look at the future, I, for example, look at a much larger role for solar energy. Solar energy is solid state physics. But electrical engineers are taught very little solid state physics, an increasing amount, but not an adequate amount of high power controllers based on solid states, and much more on machines. I'm not saying that machines will not be used. They will be used. If you're talking either nuclear or you're talking of hydro, of wind or hydro, we will use machines. But we need to look at the engineering curricula so that it meets tomorrow's needs rather than yesterday's needs. Let me end here and thank you all for this opportunity to share my thoughts with you. And sir, may I say what an honor it was to be chaired by you. And sir, it's in your hands. It's not working, sir. Sir, again, Mr. Chair, I know this is working now. Okay.
They control it there. Well, thank you, Dr. Mathur. This very clearly spelled out horizon as far as energy transition is concerned. We are running behind time, but maybe I think it's an important topic. So we have 1 or 2 questions are in order. Mr. Sanak Mishra. Can you reach mic there?
Yeah.
Yes, but I think it will be easier if we can get a mic to you. Yeah, I think it's coming.
Hello. Yeah. So what I understand is that these photovoltaic cells, they have a finite life. Therefore, the solar panels need to be changed from, period to period. I'm not defining the period. So what worries actually me and a lot of people is, if India is going to go through that kind of a large scale 30,000 square kilometer of panels, and they need to be changed every 5 years or 3 years, whatever it is. There would be a very pressing need for the disposal of the panels, and apart from the cost, of course. But I'm worried about the environmental impact of disposing of this. Thank you.
Okay. The suggestion is let's get couple of more questions and then Dr. Mathur can respond to all of them together. Yes, please.
A.K. Jain, very brilliant lecture by Professor Mathur, but I have a complaint that he has not addressed of the question whether the nuclear should get preference over the renewables.
Anybody else?
There was one more here.
Yes, please. Oh,
Dr. Mathur, wonderfully articulated lecture. Very quick question. Should India worry about grid, national grid? Are we going to worry about having a smarter grid, or do we already have one?
So should I? Oh, there's one more. And then.
Good afternoon, sir. My question is regarding the capital expenditures for these. These are the very good ideas, but where do we get the financing in the India? That's my question.
All done? Yeah, one there. And I think we'll stop at that.
Thanks, Madhu sir. I would like to ask, what about the afterlife of these products, like the lithium-ion batteries? They have not yet been that's not been thought that what will be done after they have been taken proper use of, like how they will be recycled, and the nuclear waste, how they will be recycled. Is if that poses a threat to environment, and what causes it?
Okay, so all yours.
So the last question and the first question both dealt with the end of life of PV panels and batteries. And would they essentially create a lot of landfill for us? Would they create the kind of environmental damages? I think it's something that we need to worry about. I'll tell you what the problem is. The problem is that we don't know what the solar technology or the battery technology will be when the current technology retires and reaches end of life. Look at what the technologies were 15, 20, 25 years ago. They clearly were not the same, whether in PV or in batteries, as the ones today. This leads to two questions. One is, what is the kind of recycling we want? And second, what is the recycled material used for? Not knowing these answers, what we as the Solar Alliance are looking at, and we will be coming out with the paper on this very, very soon, is the fact that you need to be able to dismantle the entire solar panel and the entire battery so that all the materials can be separated out. This means that we have standards today on how the manufacturing is done so that they can be dismantled at the end of life. This helps, therefore, in developing the recycling technologies of tomorrow. And then you know that no matter what is the kind of technology that is there 25 years hence, this material would form an input to the chain, whether in PV cells or somewhere else. As you can notice, this is a troublesome exercise. We will be coming out with recommendations, and we will be moving with the standard setting bodies, particularly the ISO standard setting bodies, to see how the changes occur. So that is where we are. It's not a complete answer, but let me just say that this is work in progress. The Ashish, this is a tough question, because in a sense everything is always evolving and the grid is also evolving. What we have achieved is a national grid in the sense that all over the frequency is the same. Every part is connected. The parts, yes, there are parts which are weaker. In other words, the interlinkages between the generator and the load center are less than they would be. This will increase as more and more renewable comes in. Because now imagine, for example, in Khavda in Gujarat, they are setting up a 30,000 megawatt farm, which is solar and wind and battery. Okay, so you can have one line from there coming to places like Ahmedabad and so on, and then connecting with the rest of the grid. But supposing you have a different solar, you have a different place where you have wind, and you have a different place where you have storage. Then you've got three different lines. We have not yet started working on that. So yes, a lot of work on the grid development is essential. The last question was about the economics. Yes, it will need a lot of money. We calculated that the amount of money that we will need is something in the vicinity of about 2 lakh crore rupees. Sounds very large? Well, we are already looking at an investment of approximately 1 lakh crores, half of this, in current technology. Where is the money coming from? If you look at what the pension funds in the world are holding, they are holding somewhere in the vicinity of 5 lakh crore dollars, not rupees. So about 8 into 5, 50, 40 times more than this amount that they're holding today. What do these pension funds need? These pension funds need to be repaid on time, year by year by year. Can we make that happen? Why are they not investing? First, they want to see an asset. Asset is important. So once you have got a solar, once you have got a wind, once you have got a solar plus wind plus battery, whatever it is then possible to sell this as a bond, right? But you will need the money to make it. How do you get the money for that? Again, the investment companies in the world have enough money. We carried out an analysis for something very different. What you need is the guarantee that they will be repaid. So creation of guarantees is important. And I think this is where the developed countries can help the developing countries by providing the resources, the financial resources to provide the guarantees so that the private sector will invest into these kinds of generation solutions. It's a convoluted answer, but with guarantees and with bonds, it should be possible to raise the money that we need for this large-scale capital expenditure. You had asked about the question about should nuclear get priority. The way priority is happening is, I think that we will move to priorities of firm power versus infirm power. Now, nuclear provides much firmer power than renewables does. So that is the benchmark to which renewables, by mixing up two kinds of renewables, solar and wind, or by mixing solar plus wind plus battery, will seek to achieve. But the advantage that nuclear has is that it is providing carbon-free firm power. So I'm sorry I'm not able to answer your question directly, but that is where I see the grid of operators going.
I think with this, let us give Dr. Mathur.
Thank you, sir. Thank you very much, sir.
Thank you, sir, for the wonderful.
Well, friends, yeah. No, I think we're already too late, so let's turn back to organizers. Please.
No, I wanted to request you to please present the memento to the speaker of the session.
Of course. I don't have a picture. So let's say the camera.
Thank you, sir, for chairing the session. before we break for the tea, I have few small announcements. After the national anthem, we'll first move on to the high tea on the first floor of the convention center. Then we will commence our two parallel technical sessions at 5:30. Yeah. The technical session 1A on laser material processing techniques will be held in Vikram Sarabhai Hall, and the technical session 1B on renewable energy engineering will be held in Homi Setna Hall. These two halls are just outside and the same auditorium convention center. And these sessions will commence at 5:30. Later in the evening, a special talk titled India's Pride Chandrayaan 3 mission by Dr. M. Shankaran, Director, URSC, will be held in this auditorium at 7:30 p.m. Now, let's please all stand up for the national anthem, and I invite Dr. Suparna Paul at the podium, please.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात मराठा द्राविड उत्कल बंग विंध्य हिमाचल यमुना गंगा उच्छल जलधि तरंगा तब शुभ नामे जागे तब शुभ आशीष मागे गाहे तब जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Thank you all. One last announcement for the parallel technical sessions. The speakers are requested to upload their lectures in the respective halls. Thank you.
Hello, hello, hello. Hello, hello.
It is my proud privilege to introduce briefly about the Professor U. Kamachi Mudali. He is the Vice Chancellor of HBNI, a deemed to be university affiliated to the Department of Atomic Energy. He was earlier the Vice Chancellor of VIT Bhopal University during the year 2021-23, Honorary Professor of Practice at IIT Madras from 21-22, and Chairman and Chief Executive of Heavy Water Board, Mumbai, a flagship industrial unit of DAE during the year 2017 to 2020. He was at the Indira Gandhi Center for Atomic Research, DAE Kalpakam, during 1984 to 2017, and was finally the director of the Materials Chemistry and Metal Fuel Cycle Group. Professor Mudali is a distinguished alumnus of Indian Institute of Technology, Bombay, PSG College of Technology, Coimbatore, and adjunct professor of the Institute of Chemical Technology, Mumbai, and PSG Institute of Advanced Studies, Coimbatore. With this brief introduction, sir, I hand over the session to you.
Good evening. Thank you very much. So we start the technical session 1A, laser materials processing techniques. I think discoursing about the laser materials processing techniques at RRCAT is like selling coal at Newcastle. You are all learned people on the laser technology and its application for various industrial solutions. Just after the pandemic, if you look at the global laser technology market, it has been estimated in the year 2022, the market size was about US $16.7 billion. And they have also predicted that in the next 5 years, it will rise to about 25.6 billion US dollars at the rate of 9 to 11% compound annual growth rate. So this clearly indicates that this is one of the top 10 technology that is growing today after the pandemic. And this technology is going to contribute significantly to mostly in the material processing and production, healthcare and medical devices, the automotive production, aerospace engineering and manufacturing. And all of us know very well that it is only because of the accuracy, productivity, the sustainability and adaptability of the laser techniques in the materials processing. I do not want to take much of my time between you and the speakers. We have 4 eminent speakers with us who will be speaking for about 20 minutes. I request the speakers to complete it by 20 minutes. After 15 minutes, I'll give a bell, and then followed by that 5 minutes for interaction. Let us begin the first lecture on the transformative power of the 4 P's in product innovation. This lecture is delivered by Dr. Naganumaiah. He is the director of Central Manufacturing Technology Institute, CMTI, at Bengaluru. He is basically a mechanical engineer. He did his MTech in tool engineering and PhD in mechanical engineering. And his areas of research work includes additive manufacturing, micro nanoscale manufacturing technologies, tool design, rapid tooling for injection molding, manufacturing process selection, and manufacturability evaluation, and so on. And he has to his credit 108 papers and 9 patents. He has been recognized with the Raman Research Fellowship from CSIR, and he has also received We Think for India award by the Prime Minister of India for his role in shaping the Indian manufacturing policy dropped in 2003. He has received the Distinguished Leadership Award from the International Society of Industrial Engineering and Operation Management, USA. He has also received the Eminent Engineering Professional Award from the Institute of Engineers, India, and he is also the Fellow of the Indian National Academy of Engineers. Dr. Naganumaiah, I'm pleased to welcome you to deliver your talk now.
Thank you, sir. Good evening, and thanks to INEA and RRCAT for having me here. My talk, of course, though the session is laser focused, my talk is a bit of different in the sense it can be applied to any source, but yes, I'm being a additive manufacturing background, so I will try to correlate with respect to additive manufacturing. You may be knowing product development or the technology development. If you look at the three criteria, that is made in India, make in India, or made for India, and the last one is originated in India. If you look at the survey conducted in 2016 by Department of Commerce and Industry, it predicts that more than about 60% of the so-called industrial R&D is new to company, and 9% is new to India, about 3% is new to world. It means, so still we are not so good in terms of technology originator. If you look at it as a technology originator, we as a country have our own limitations. But whatever the technology developed is more or less is customized, localized to meet the requirements. There are several technologies done, or it is re-engineered or remanufactured to suit the specific applications, and that is how primarily our industrial R&D is focused. Working in last 30 years in the R&D lab, applied R&D lab. I was there 20 years in CSIR. Now last 5 years I'm in CMTI. The major responsibilities that we did is design, develop a machine, design, develop a process that customized to the local needs to basically either to enhance the performance or productivity of the manufacturing value chain in the industrial domain or the user industry. But the challenges, if you question, I won't go through this. This is always debatable. But yes, there are a few aspects. One is our education system, because we never focused on, because our education system is a percentage driven. So naturally, not much focused on the technology driven, and connecting the last dot was never taught in the school. Then there's other aspects, networking and all. I'm sure by this time you must have read. But we are being a national R&D lab under the Ministry of Heavy Industry. Over last 6 decades, we designed, developed a machines and process technology. Unlike the other R&D, basic R&D institutes, we primarily work on higher TRLs, that is TRL3 and above. For the lower TRLs, we will go to the fundamental research institute like IITs and other CSR labs. We are proud to say CMT has developed about 500 solutions, and most of the solutions are working in industry. Other than our mandate, and we also work on because we need to generate our revenue also. Currently, we are like, you can look at this, these are all machines, sample machines we developed, and these are all not prototypes, these are the machines ready. And second is, none of these machines are, even today, there is not a commercial machine. We designed, developed the machine first time in India, and that to meet the customer's requirement right at first. And these are the few areas right now we are focusing. The first area is that we design, develop a machine which is capable of creating micro nanoscale features. So naturally, the accuracy level at least the 5th decimal of the millimeter. Then the special purpose machine here, mostly we design, develop the machine to meet the customer requirements. They are visiting us with a request that, okay, this is the requirement and we need to develop the machine or automation system. In many cases, process is already known. Process recipe is known, but if it is not there, then we will also work on that. Then when we are building a machine, sensors and controls is a now, because all these are mechatronic systems. We have a dedicated vertical which focus on sensors and controls, and right now in our CMTI, we have a dedicated laboratory that could process 6-inch wafer, starting from fab, then to characterization, starting from design to fab, then to characterize and packaging. So if any requirement is there, we can able to help you to develop the sensors. Then the special purpose machinery, we also do the textile machines. We also do develop the machines like this. This is used to mix the solid propellant, which is used in all these rocket vehicles. In fact, Chandrayana, 4 lakhs kg of your solid propellant was mixed by the mixers developed by CMTI. So like that, there are several machines under special machine category. And next is sitting at aircraft. I'm sorry, I'm taking a minute because the reason is to know we're doing business, and at the same time knowing each other is always better. Sitting at Bangalore, we are closely working with all the aircrafts, but aircraft aerospace giants like HAL, ADA and all. Our specialization is we design, develop the test rigs to qualify the LRUs. That is our strength. Then precision metrology, as far as dimension metrology is concerned, we are definitely, at least NPL recognizes us, we are better than them. Of course, NPL being NMI, they do a lot of other metrology, but we are only on the dimension metrology. Then smart manufacturing and industry 4, we have smart factory. If anybody wants to look at what is smart factory, how it looks, there is a factory, production factory is there. And at the same time, we have developed our own technology. If any workshop, say for example, RRCAT, you have a workshop, you want to make it smart. So we have our own solutions, no need to import anything. So we will convert it. We already implemented these solutions into MSME, even to the company like Toyota engine manufacturing plant. We made it workshop shop, basically engine shop floor, we converted to a smart workshop. So then naturally technology, skilling and reskilling, and then technology transfer. These are all essential components of being a national lab. Apart from that, annually we provide about 3,000 plus services to the industry, which is both on-site as well as on the laboratory test, on 10 different aspects of associated mechanical engineer and also including nanomaterial characterization. And training is, of course, there are 55 training programs and then customized training programs as per the requirement. In the true sense, we are already into Atmanirbhar because whatever we design, develop, that is first time happened in the country. So for example, this is what I mentioned, the mixer that you can look at our chairman. This is a 10-ton mixer we have developed for ISRO. This is globally highest capacity for mixing a solid propellant. And we also developed like some LRUs. This is a pump which is used in your LCA, 30 LPM pump. This used to come from Ukraine. So we started as a study project, but finally now it succeed. Engineering model is already demonstrated. So now my manufacturing rights is already assigned to HAL. And this is like diamond turning machine. Well, I showed this slide particularly. The reason is the equipments designed, developed in the country would cost you 60% of imported cost. So 40% net saving. So for example, if you look at 10 ton, ISRO received the quote in 2019 for one machine 120 crore. And I supplied two machines in 100 crore. So that means 140 crore is the net saving. Still I have a profit. I'm not supposed to discuss, but yes, even with that I have a profit. I think that is what the advantage. If you look at a diamond turning machine, India still is not a commercial, but we transfer the technology to US designer. If you had happened to visit last IMTEX, this is the machine developed by this owner of a company. Then based on our design, that is commercially launched. Similarly, another success was happened this year only 2000. This is Rapier loom. In India is the Surat based. If you go out, all loops are operating at 200 to 250. Or some imported machines are there from China, but this is at 450 RPM, and we transfer the technology to 5 companies, 4 at Surat base and 1 is at Coimbatore. The Surat based company is launched in Milan, so last June. So that is how basically our working domain. While working this, what we understood is, no matter whether you develop a water bottle or you build a machine or some spacecraft, we need to address, we as an engineer, we need to address the challenges related to 4 P's I call, that is related to product design, process design, people design and the production. So that is what I transformed, my title was that we need to understand the implications of 4 P's. So then only can able to develop the technology. I think that experience I try to share this. So what we do in this 4 P's, addressing 4 P's. So basically at the product design level, there are a lot of technology. Somebody does the mass customization, then localization, or the new product or novel process like that. These all things comes under this. Finally, using all these tools, we end up with a design which is acceptable to my stakeholder. It doesn't mean that what it looks beautiful with a CAD and good design in the laboratory may not be a good in the shop floor. That is what at least I learned after I moved to CMTI. Then process, if you look at process also we do lot of connectivity. material resource, particularly in additive laser and material interaction. Unless you understand this, you can't build a machine and you can't produce a component, no matter what machine, who is the manufacturer there. So, like that, there are challenges again. People that comes simple skilling, reskilling, but there are a lot of other things, even in the behavior. Unless team decided, no matter, you can't develop any technology. So team has to commit, so then only it is possible. So a lot of psychological aspects also get into this. Then the production is scalability and sustainability. What I mentioned, the technology which is good at lab may not be good at there. So now challenge is, while doing an experiment in the lab, so that is what not taught in the school. So are we able to consider these aspects? Because even doing an experiment at the lab has an implications to address these challenges when you're looking at a technology which is ready to use. So that is what I called it as a DISC approach. But what tools we have? We engineers have only these 5 tools to address these challenges. So one tool is with respect to form, then to function, then to flow. Then I added, just to remember 5 F's, I made physics, but not necessarily physics, it is a science. Then the fabrication, right? So irrespective of the discipline, irrespective of the product what we develop, so one has to address these 4 P challenges and using these 5 F's tools. And if you come to the manufacturing, because I'm from manufacturing, so I'll try to move that side. In manufacturing, if you look at the technology evolution happened on 3 aspects. One is with respect to process, another is with respect to engineering of the machines or the equipment, and the third one is the factory systems, like factories, all your TQPM, TPM, whatever, all this technology, which basically attributes to enhancement of the productivity of the company and the profit of the company. But challenge for us is, we get over of this, made for India. I think globally nobody is look at now any technology which is made for India. Of course, maybe functionally, yes, we Indians are this much taller or shorter than Russians or like that. So that is a different story. Otherwise, we are capable to do it. Then made in India, it is made in India is the target. I'm sorry, that is a make in India. Make in India is a process. To reach made in India, if not originated in India. I think if you look at Atmanirbhar, that is what they call. Can we look at technology originated in India? So if you look at these challenges, product and process innovation, there are these 3 components or matters: design, material, and the technology. Right? I'll just give an example. This example, no. This is what the gear rotary actuator we developed for LCA. Material is not available, so material has to be imported, but that guy is not ready to give a certificates. So those are all challenges. If you look at the process, if additive manufacturing is the process, so all these challenges are still not unknown, not known. So for example, there is no RP. I will go back to the slide. So there is no RP process. You give a drawing, I can able to make it. So there are a lot of, if you ask the question, is it possible, is not possible, can you change the part orientation like this? So that is the maturity levels. So technological limitation. Of course, now digital aid, digital twin technology and all, they facilitate the design process, at least that automated the design process. But taking digital twin to the factory, so still we need to focus on material and then the process related challenges. So that collectively requires the skilling. But in the product development, new product development, the challenge is prototyping is unavoidable. No matter prototyping, maybe just 3D simulation, you have done some CAD package. But at the same time, maybe it is a pre-functional prototype or pre-functional parts. So as this is all, I'm sure everybody knows this. There is a different physical prototype or analytical, focused or comprehensive. Each has its own limitations and each stage. So at the same time, fundamentals remains fundamentals. You name any manufacturing process, every manufacturing process could be grouped under any one of this. So now I will just additive, because this community belongs to laser additive manufacturing. If you look at, so additive manufacturing evolved like this. So when, because I did PhD in the same area, so the earlier days in this is only story is 95, but 1987 was the first patent on 3D resolutions. So earlier they thought that making a product using RP pattern, soft tool, bridge tool, art tool. Now we are looking, can we use AM as a direct manufacturing process, if not as an alternative manufacturing process in the industry. So if you look at alternative manufacturing process, you need to focus on this. With respect to design for AM is still not known, and flow maturity level, all this process are optimization and hybridization. As I said, if you give a drawing, I cannot build it. So then there are also size limitations and all. Then training, so still it is not taught as a core course except few IITs, additive manufacturing itself. The laser, I think mechanical engineer only studied laser in first year physics and as a part of optics in the physics, engineering physics. So those are all to be required to be taught extra beyond the curriculum. Then the production, because machines made elsewhere are normally expensive, and you will also come up with institute like us, machine, imported machine, okay, warranty clause valid only if and but. So there itself will stop. So that is the advantages if you can able to engineer the product, the machines here. But these are the open areas with respect to additive manufacturing, excluding laser. I am not included laser because I am not understand full laser. So right, so these are the requirement, direct and smart. That is what people are looking for additive manufacturing, and including art tooling. So one has to address these all 4 key challenges. But these are like, look at product design, so redesign. So first question is, the components were designed for manufacturing rolled component by rolling or by casting or by forging. So now AM made components that are same design valid. I don't think engineers can able to have an answer. Why? The reason are 2. One is all machines are made by 300 cubic size maximum. So but if you look at the guy asking a turbine design, so with a cold model he has to extrapolate, but that is not there. Even metallurgy, I think I'm sure metallurgy, medium and all they can easily understood. Lot of confusion answer whether AM made products are good or bad. And second is, even I have my answer, I don't have find an answer. AM made context tensile specimen we are testing, right? Is it correct or not? Because metallurgically it is not a homogeneous component. So there are so many gap area we need to address, so that your design qualifies whether it is a cost efficient, and then material restriction, lot of restrictions are there. Repairing and reconditioning of the dies and molds still not used. So each itself can have a multiple research problems. It is an open area, so one has to look at that. If you add laser, again it multiplies by another 10 times. We CMTI into AM, so we are the first to introduce the metal additive. We have not built commercial machine yet. We are building now 2 machines. Otherwise, yes, this is ready for commercialization, microstilography. Then also we made a smart, and we did lot of services to the industry for reconditioning the high value one-off time replacement components, because particularly the strategic sector, this is more. There are many components were systems were imported by Russia, but now company is not existing, but still life is there. So we need to recondition that kind of operation. And we are also working on finishing of these AM machines, AM made components, because that is one of the major challenge in AM. So when we are looking at the finishing of these complex shapes, so we have developed the machine like abrasive flow finishing to finish the AM components. And we are building 2 machines. So because of the IP, I will not talk much, but the idea is that first machine is a DED machine, powder based. 98% is Indian content, except few sensors. Everything is Indian, including lasers. This is already assembly is going on. Some trial experiments are already done. This we use parallel kinematic based configuration because it was there with us. Then we started with that. In fact, that time I came to CAT Indore for the laser source. I was looking for high power laser. Then we are building another machine. This we are working with jointly with an industry or ministry funded. Here basically 5-axis additive manufacturing DED machine. What we are trying to do is, instead of using a high power laser of 2 kilowatt, we are trying to use 8 laser heads of 250. and we are trying to focus on single point and wide based. This application we are targeting for reconditioning and reconditioning of a larger components. It is 1000 millimeter size. So the summary is we basically is a team. Team should be a multidisciplinary, even if you want to build a laser based system. One should have an experience. This is applicable to any domain, but this is domain. One should have a machine building experience, controls and software. Then, well, as I said, process technology, material and laser interactions. Then optical design expertise is required. A lot of optical design is there. And testing and standardization. Still, testing and standardization is not happened. I think ISO, it is little old information. About 7 standards are there. BAS adopted 2 out of that.
Sir, you can come to conclude.
Last slide. So when you do the collaboratives there, this is one example I'll show. If we, as I said, if you all decided, we can build. This is one example. There are 10 institutes, private institute, government institute, and labs. We all joined together. We developed a foundry which has a footprint of 8 feet by 16 feet. This was funded by DST, Advanced Manufacturing First Call. And we developed a metal casting foundry which is capable of casting 1 kg aluminum, and it is completely smart and 100% domestic content. We have not imported even single sensor. So I think that was there because of multidisciplinary. We had a computer science, mathematics, and all. So study this I will skip because the student community is less. Education, I think we need to focus. The reason is, does kids understand, identify stapler? How many parts are there? What are the different materials? How they are made? If they are able to answer while passing out from the engineering college as a mechanical engineer, if you say, I think he can be made a good engineer. These are all the things which are required. I think that is not happening right now. So if mechanical engineer, the employability is all depends on this. It does not depends on how you will solve the differential equation. Because differential equation can be solved by referring a book. This is my last slide. So the idea is to focus on technology or the product originated in India. Then there is no shortcut. It has to start. Why not we start today? So then, of course, we Indians normally problem, even faculties, one of the IIT Kanpur faculty told, Dr. Naga, you know what happens? Whenever PhD students comes, if I give a previous thesis, tomorrow his answer is, I will not do it. Because who take the credits? I think that is where, because that doesn't happen, we need to work on maybe, so one day, if not you, your next junior would reach to the technology that is industry ready. So that is what in fact the Einstein statement. So it is very difficult to measure what is important in the innovation process that we are addressing at 4 P's, because thing which is novel to me, it is new to you, or which is new to you, which is novel to me. So that is what basically we need to discuss, collaborate and all.
Thank you, Dr. Naga. Are there any questions? One question?
Sure.
Yes, Dr. Sanak.
Yeah, actually, you are a research institute. That's the character of yours. So yeah.
Hello.
Yeah. So sometimes I wonder, an institute like yours, which is designing wonderful things and all, how do you actually assess the efficacy of your work? What is the parameter that you are doing very well? You are doing a lot of design.
So we have 4 parameters.
What are the parameters?
One is technology.
See, technology can be in only numbers. It may not mean carry any meaning.
No, technology. That's what technology. If I say, if I claim this technology works, then whether it is good for industry or it is good for you, and does it bring the money?
Yeah, you have balance sheet.
Yeah.
Your balance sheet. So what is the profit you made last year, 2022-23?
The last, we are now meeting at our expenditure of the requirements. It is our 78 crore, our earning, and expenditure is also 76 now.
78 crores. So you don't make a profit, right?
But still now we're not making
So you will
profit.
still remain as a research institute, okay? You're not making a profit, right? You're only covering your cost.
We are covering our cost.
I wonder actually how does one measure, as I said, are there parameters to measure the efficiency or efficiency of an institute like yours?
So these are 4 parameters they use: technology, and then the revenue generation, then the IPR content. Well, only the last 5 years we filed 18 patents.
18.
Yeah.
And what else is the 4 parameters?
4 parameters: publications and training, all those social. Yeah. Human resource development.
Thank you.
No, I can allow only one, and the last person. The want of time, you can interact with him. He is available.
Good evening, sir. So my question is regarding Industry 4.0 and smart factories. So what are the skills that are required for a mechanical engineer so that he can build his career in this smart factories and Industry 4.0? And what is the scope of this field in this
So
country?
according to me, smart Industry 4 is not a technology. Industry 4, which was there, how we used to do, even if you go to shop floor, how industries, majority of the industries works is, it depends on in each shop floor 1 or 2 people, right? But that was, say for example, let us assume lathe is an operation. So your control parameter is only you want to achieve the required surface finish, just RA value, right? So the parameters or the opportunity for an operator to control has only 3.5: speed, feed, and then one is the depth of cut, right? So now, but if you look at it as a mechanical engineer, if you started writing what parameters, attributes to ensure the desired RA value, at least you can list 10 parameters. So now these 10 parameters implications understanding by individual would take 15 years. So now naturally there is a so-called somebody Rama Bima who is an expert. So operator usually learn from him with an experience, and problem is fixed by those so-called experts. But Industry 4, what will happen is, so now because of the technology development in terms of aggregating the data, that is sourcing the data from the real sources, and second is there is an algorithms, AI, ML, whatever you call. So there is a prediction, you predict what has happened, right? So after that, so it can also send back to the machine, right? Even without the knowledge of an operator. Also lower level is you just give an alert. Okay, there is something wrong, you change it. Means offline, those kind of things. So Industry 4 advocates only that 4 pillars. One is acquiring the data from the real source, digitize and sharing the data with all the stakeholders, using the models, intelligent, whatever you call, it may be simple regression model. You predict, and that predictions you bring back to the real source so that your efficiency increase, machine shutdown will reduce. That is the fundamental this one. So now it was happening in the industry, but it is happening now with the help of ICT technology.
Thank you, Dr. Naga.
Thank you, sir.
And on behalf of the organizers, I am presenting a memento. The second speaker is Professor Jyotsna Datta Majumdar, my good friend. She is from the Indian Institute of Technology, Kharagpur. She is a PhD in metallurgical engineering, and her areas of research work include laser material processing, surface engineering, corrosion and wear. She has more than 154 papers, 8 book chapters and 1 edited book. She has been recognized with the Fellow of Indian Institute of Engineers India and the Indian National Academy of Engineering, Distinguished Women in Engineering Award, Fellow of the West Bengal Academy of Science and Technology. She has received the prestigious Alexander von Humboldt Foundation Award. She was also recognized with the MRSA Medal by the Materials Research Society of India and the Metallurgist of the Year by the Ministry of Steel and the Indian Institute of Metals. I would like to request now Professor Jyotsna Datta Majumdar to deliver the lecture on development of tailored titanium aluminide by laser directed energy deposition.
Thank you
Over
so
to
much,
you.
sir.
After 15 minutes, I will give a bell.
Okay, sir.
You
20
can
minutes, yeah.
finish it by 5 minutes.
Okay, thank you very much, sir. Good evening to all of you. So today I am going to share some of our experiences on development of tailored titanium aluminide by laser direct energy deposition. So in this particular talk, I would like to give a brief introduction and then experimental steps that were followed in the present study, then results and discussions, and finally the outcome and future direction of research in this particular field which may be undertaken. So titanium aluminide as materials do not need any introduction because you know it is very important class of materials and it is very much competitive to nickel-based superalloys. But problems with this kind of material is that it's having very poor ductility, poor fracture toughness, and particularly the high temperature oxidation resistance property of this material is very poor. So if you just quickly go through the different techniques that are applied for the development of titanium aluminide, they may be of melting and casting technique, powder metallurgy, and maybe laser direct energy deposition is a new approach which is coming these days. And by these two techniques, people have been developing these alloys since over last 2 or 3 decades. And if you just quickly go through the processing steps followed under these particular two techniques like powder metallurgy and melting and casting, they are huge. Like if you have to start from melting and then atomize, encapsulate and then heat compact, then you have to remove the can, then condition surface and then again rolling, and finally you have to have the main product by machining. Similarly, in melting and casting also there are large numbers of steps which need to be followed for the development of component out of the titanium aluminide. But laser direct energy deposition is the advanced manufacturing technique which can reduce the number of steps. In addition to it, it is environment friendly and it is having very fast processing speed, and also it is having the flexibility of developing a materials of a component of any shape and size by one step processing. So these are the advantages associated with laser direct energy deposition, but there are also a number of disadvantages or maybe limitations arising out of this particular technique, particularly the residual stress which are developed, which is different directions along the component, and also if you just talk about laser direct energy deposition, then homogenization is also another trouble. Whatever microstructure you get in small components, that's very much homogeneous in nature, but whenever you talk about large scale component, then it is a big task, and also that for batch processing that's not a problem, but whenever you talk about continuous processing for large set component, it is a big trouble actually. You have to optimize those things. So in this particular study, we started with development of known alloys. Known alloy means this is again industrially developed alloy with a modified composition consisting of titanium, aluminum, chromium, manganese, silicon. These all additions. It was supplied by industry, and that particular alloy powder were developed by laser direct energy deposition, and we tried to compare our results with that of whatever existing standard available, and then later on we tried to modify the composition a little bit, and where the beauty of our approach is that we basically mixed all the powders like titanium, aluminum, niobium, silicon, because this particular problem, naturally titanium aluminide was not my field, so when I visited under this Alexander von Humboldt Fellowship to Germany, so that was their mandate, so I have to do work on this particular material only. So I had no other option but to just mix those powders and subsequently go on developing it by laser direct energy deposition, where we modified it a little bit, apart from the industry supplied powder. So where we added niobium and also silicon and also titanium carbide and titanium boride, different mixtures we added based on our main requirement was to refine the microstructure and as well as to improve the high temperature oxidation resistance property. In addition to that, we also tried to investigate the effect of these all alloy tailoring on the mechanical properties to some extent, depending on the facilities which are available within us. So the experimental steps which are followed are shown here. So here we just took a large numbers of powders, like this powder was industry supplied powder like titanium, aluminum, niobium, manganese, and molybdenum, boron. These first two powders were industry supplied, but these powders were actually developed by us by mixing elemental powder composition, and subsequently we developed that typical product having the dimension of 10 centimeter by 5 centimeter into 5 millimeter thickness, and laser we used was high power continuous wave fiber optic delivered NDR laser with beam diameter of 2 millimeter. We varied applied power, scan speed, and powder feed rate. So in one condition we developed this alloy without any preheating. Other set we developed the alloy with preheating. Preheating was done at 780 degrees Celsius in the alpha 2 plus gamma regime in order to homogenize the structure, so that there is no inhomogeneities in the microstructure. The typical precursor powder used in this study, the powders were not really, it was highly flowable, but not spherical in shape. And this is the typical laser and the component which was developed. So now I'll just try to share some of our results in different approaches, whatever I can within the time given to me. So this is typical industry supplied alloy, that is titanium 47.5, aluminum 2, niobium 2, chromium. As I mentioned that we developed two set of alloys, one is with preheating, another one is without preheating. So this is without preheating, this is with preheating. So what we saw is that after preheating, the gamma content in the typical microstructure is nothing but alpha 2 plus gamma, but whenever we just went on doing preheating, we saw that the gamma percentage was increased to a large extent. Obviously, we just developed different types of microstructures based on the alloy composition, but what was the main differences that were only the alpha 2 plus gamma content was varied. Otherwise, there was not much difference because this is basically this titanium aluminide based system. So, but when we just try to see the effect of the alloy composition and preheating on the mechanical properties, we saw that in one set of alloys like titanium 47.5, aluminum 2, niobium 2, chromium, this particular alloy where the microstructure was actually it was fully lamellar microstructure. There we found a significant enhancement in the compressive strength, though OE strength was a little bit reduced than that of other alloy, where boron was there, and but manganese and molybdenum were there. There was no chromium, where the microstructure was predominantly lamellar, fully lamellar in nature. But because of the boron addition, there was significant refinement of microstructure. So yield strength was increased, but that typical UTS under compression was not really as high as for the other cases. But in both the cases, we saw that due to heating, there was a little enhancement in the ductility or little reduction in the yield strength as well. So this was because of grain coarsening effect. So now coming to the second set of compositions where we just modified the composition and elemental powder mixtures were applied. So that were different compositions having different percentage of silicon. So what we did is that initially we tried to eliminate the parameters, or maybe tried to optimize based on trial and error observation, where we found that the range of power, scan speed, or powder feed rate which led to defect-free microstructures, those parameters were initially considered for development of the typical coupons. It's not product, because when we try to develop a kind of coupon having the thickness more than 5 to 6 millimeter, we saw that cracks are there even after heating. So we stopped over there only. So what we found is that we developed 3 layers, and middle layer was always taken into consideration for all the structural analysis as well as other property analysis. So naturally thickness doesn't have any value, which increases with increase in power and then the decrease in scan speed and also increase in powder feed rate. But what is important here is the microstructure. So in one case where silicon content was very less, a little bit silicon addition was essential in this particular alloy, because without that we could not have very good it was very much viscous, it was not really fluidic in nature. So we added 0.5 silicon in the base alloy. So we found that with heating there was not much change, but there was homogenization of the microstructure with increased gamma content as compared to the other alloy where same alloy where without heating we developed the coupons. So due to heating this small change in microstructure, what we found is that there was no reduction in hardness to a little extent, but interestingly there was increase in high temperature oxidation resistance property with increased activation energy of oxidation, so which was attributed to actually that increased gamma content in the microstructure. So in the second case where we added 5% silicon, we found that there was silicide distributed all throughout. Little bit porosities were unavoidable, though content was very less. And in 10% silicon, it was significantly higher amount of Ti5Si3. But it is interesting to note that when we just increased more than 10% silicon, like we had tried with 12 or 15% silicon, we found that again silicide content was so high that there were crack formations, micro crack formations all throughout. So we stopped there at 10% of silicon. So if you see, you'll see that in 5% there were some silicide Ti5Si3, but in 10% there were also TiSi2, TiSi, different types of silicides are formed also the structure. But it was really, this is the structure developed after heating, preheating. Without preheating, we didn't get such homogeneous distribution, but obviously the silicides were present, but the alpha 2 plus gamma phase were not homogeneous actually. So we found that with this particular these compositions, like we saw that there was improvement in the mechanical properties in terms of that Young's modulus as well as hardness, and also the compressive strength. And but however, whatever compressive strength we got here, it was lower than that of earlier developed alloy, where the alloy composition was itself titanium aluminide base, that same composition. And also this maximum compressive strength what we observed, it was lower than that of reported literature. But what is interesting here is that whenever we just did the cyclic oxidation resistance, we just activation energy was significantly improved because of silicon addition, and 10% silicon showed maximum improvement in the oxidation resistance property even as high as 900 degrees Celsius. So we just developed the model for increased oxidation resistance, or the mechanism of oxidation. And what we observed is that due to heating, there was microstructure homogenization and increased content of gamma, which were responsible for improving the high temperature oxidation resistance, as well as there was decreased solubility of oxygen in this study because of higher mass fraction of gamma. And alpha, that niobium and both niobium and gamma, they promoted the alumina and silicon dioxide formation in the microstructure. So in case of silicon, there was a higher amount of higher thickness of the silicon dioxide and alumina layer on the surface, and also at the interface, which were responsible for improving the high temperature oxidation resistance property. So in other case, we just added titanium carbide in the microstructure in the alloy, and subsequently we did DLED. So after titanium carbide addition, what we found that there were different types of titanium carbide certainly were dissociated, and there were formation of titanium aluminum mixed carbide after the solidification. And what we observed that all titanium carbides, they were mostly present along the interdendritic boundaries, and also some titanium carbide were also dispersed in the very small particles forms. And we observed that titanium carbides were also present along the grain boundaries very fine. Naturally, these kind of precipitates are also good because they can pin the grain boundaries and good for improving the creep resistance property. So finally, when we just try to see the effect of process parameters on residual stress, this is one of the important criteria for choice of the process parameters for any kind of LDD operation, because I told you that residual stress is one of the critical factor which is responsible for, which might cause earlier deterioration of the material when it is under compressive loading. So we found that under 500 watt applied power and 300 millimeter per minute scan speed and 2.2 gram per minute powder feed rate only, we observed that compressive residual stress, which was within reasonable limit. Even compressive residual stress also at a very high level is not desirable. There was improvement in micro hardness. This is as desired because of titanium carbide presence, and also improvement of high temperature oxidation resistance property. But we are not yet, I mean, we are in the process of investigating the mechanism of the high temperature oxidation resistance enhancement because of the addition of titanium carbide. And finally, I would like to say a few words about outcome and future direction, as I was told. So, notable conclusions are in all cases the important, you can say contribution of this thing is that we could optimize the process parameters for the development of titanium aluminide with tailored composition by mixing of elemental powder, which was a little bit inferior to that of the same, supplied to us by the industry. Obviously, industry earlier didn't develop this same composition by powder metallurgy or by LDED technique. They developed it by melting and casting technique, but they gave us for not to me, rather to my German collaborator for the for development by LDED, but we didn't get the other compositions developed by them. So naturally, we had our no other way but mix the elemental powder and subsequently do develop the coupons. And in the coupon stage, it showed very good oxidation resistance property, high temperature oxidation resistance property, and also significant improvement in the compressive residual stress. But what is important here is that in these all cases, whatever I learned is that first of all, industry were very much involved in the development of this alloy and also development of the technology for the component development. So initial idea came from the industry. So naturally, the whole process is very expensive. Also, the titanium aluminide powder, if you would like to procure, that is also very expensive in nature. So that initiative has to be there from the industry based on their demand to be associated with the academicians or the research laboratory to start this kind of collaborations, and show selection of alloying element and heat treatment schedule based on the required properties need to be finalized, and then an extensive research and development and its optimization need to be undertaken for design and synthesis of powder, because in our study it was certainly mixed powder. Neither not much research activities have undertaken on the effect of powder particle size, shape, and its distribution on the product, final product, product microstructure as well as composition and properties. Because in AISH 316S stainless steel, earlier we saw that whenever we used water-atomized powder, then it gave some results. Whenever we used gas atomized powder, it gave some other results. So naturally, this is also one area where extensive research needs to be carried out. And finally, the designing of process and post-processing treatment, thermomechanical and surface treatment schedule need to be extensively studied to achieve the desired microstructure and properties. For example, this alloy is having good high temperature oxidation resistance property. Naturally, there is also a lot of scope of developing compositionally modulated surface so that this high temperature oxidation resistance property can be taken care of. And there is need for research and development and from the participation of the experts from different sectors for having a complete solution for very good alloy developed titanium aluminide alloy development, having improved ductility as well as fracture toughness both at room and elevated temperature. Naturally, takers infrastructures for we need from government side. If you just if you'd like to say that there should be adequate takers for this particular alloy to be developed by LED, infrastructures for laser processing, characterization, experts on modeling and simulation, knowledge experts on titanium aluminide and its behavior, sufficient fund and time. These are the requirements for complete solution of any problems which are existing, not necessarily for this particular alloy or material, or rather for any material based on the new technologies which you would like to develop. So challenges in this regard include reducing cost for powder production. The powders are very expensive. Any aluminide powder, reducing cost for laser processing. Continuous processing, this is one of the big challenges in laser processing. You can develop small coupons, but if you would like to develop big product, naturally there should be provision for continuous processing with post-processing possibility, and collective efforts involving the industry and systematic effort of the researchers, time and fund are the requirements. And just before finishing my talk, I would like to convey my gratitude to Professor Manna. Because of him, we have recently developed the laser system, high power laser system. We took a lot of efforts, and with the help of this laser also we can do similar kind of research work. But naturally I started this research activity long back in 2015, so I cannot do that. I mean, naturally it can be easily done if some project fund is available. And I would like to convey my thanks to INA and also RRCAT Indore for giving me the opportunity for sharing my research results. And the laser treatment was carried out in Faunapur Institute of Laser Technology, and in IIT Kharagpur we did all processing with characterization and testing. And finally, these are the funding agencies with the help of with the help of which I could carry out some research work. And thank you very much.
Thank you, Professor Josana. And the presentation is open to questions. Yes, please.
Good evening, ma'am.
Yeah.
I am Manish.
Yeah.
I just seen the presentation in which you mentioned that there are some porosity also
Yeah.
in the structure.
Yeah.
So there are some processes in which the porosity is desired. That means we can having a technology like non-evaporable better technology in which porosity is desired. So is there any process which can be utilized in laser direct energy deposition which can give us the desired porosity for a given structure development?
Yeah, you can always develop porous structure using a laser powder bed fusion technique. Not here, but the powder bed sintering technique, you can always have desired porosity. Here also, you can just go on manipulating the laser parameters as well as gas pressure to introduce porosities. That's possible. In aluminium, we got porous aluminium. Obviously, we didn't continue the study for a systematic investigation, but it is possible.
Thank you. Yes, please.
The temperature used to changing the alpha to gamma.
We just didn't do any kind of post-processing heat treatment. Just we did preheating operation at 780 degrees Celsius in alpha 2 plus gamma regime. And by that technique, we could have some...
After processing,
yeah.
you heat...
No, we didn't do any after processing, post-processing treatment. But that can be done.
At that time, you have done.
No, that can be done, but we haven't done that.
Okay, you have not done. Because 930, at 930, alpha is converted to gamma,
Yeah.
titanium. And gamma titanium is lower strength than the alpha.
Yeah.
So where strength is required, alpha should be there.
Yeah.
Alpha titanium should be there.
Yeah, certainly. This was not intention. I mean, we didn't do any post-processing heat treatment, but continuous processing was done for removal of the residual stress. Yeah.
Yeah, one last question.
Yeah, that's it. Good evening, ma'am. I'm Vivek Pal. I just wanted to know, like, how this temperature of 780 degrees centigrade was invented. Like, it was some practical theory based or some analysis based 780?
No, actually, that was the regime where that alpha 2 plus gamma is, wide range, within wide range. And there we can also have the homogenization of the microstructure. But above that particular temperature, there may be that transformation. No. So we just had the optimum temperature so that there is alpha, that is within alpha 2 plus gamma regime, and it can take care of homogenization as well as it can reduce the residual stress which might be arrested because of the... It is not theoretical, it was inbuilt during the process. We didn't do any theoretical calculation actually. It was done by experiment only. It was.
Like these are the things we are making with the additive manufacturing.
Yeah.
How the entity we are going to do, because some casting we are doing in the some furnace, something like that. So it is totally different. The entity process is totally different. So how to ensure the indications of success or some success in such type of manufacturing? Like, because there are no known standards, right?
Standard means what standard are you looking for? Yeah, you can go for NDT. Also, we did micro city operation. We did micro. There are also gamma radiation. You can do gamma. So you can. There are several NDT techniques available which people often do. CT scan, micro CT. We did, for example. Yeah, radiography is having greater depth of penetration. So you can always have gamma radiography or X-ray radiography. Yeah, it should be defect free theoretically. If it is defect free,
I think you can continue the discussion. She is available. Okay. Thank you, Professor Devasana, for a perfect presentation. So there is a change in the sequence of presentation. The next talk is by Dr. Arvind Patel. He is the founder of Sajanand Laser Technology Limited. He is BE Electronics and Communication and MTech Biomedical Instrumentation. His work experience is on laser technology, laser micro machines, and business and industry in laser and science and technology. He has received Dr. Vikram Sarabhai Award, National Award for R&D efforts in industry, National Award from NRDC, and again he received National Award in 2003 and 2005, and National Award for Excellence in Electronics 2002. So he will be delivering a talk on precision in photonics, laser material processing role in emerging engineering. Over to Mr. Arvind.
Yeah. Thank you, everybody. Thank you, give me opportunity. I just want to start as an industry. We are from industry, so I start with the video only, and then after the presentation. Yeah.
We are taking you toward a technologically advanced future with a motto of innovating constantly, an initiator that has been driving a paradigm shift in the industrial laser, gems and jewelry, medical, defense and space, renewable energy, high-tech software development. We are SLTL Group. The journey of absolute excellence began in 1989 by our visionary founder, Dr. Arvind Patel. With a few people and passion in abundance, we envision inventing revolutionary technology with one purpose: to extend solutions across the spectrum, just like in the hearts of our customers. We are located in the capital of Gujarat, Gandhinagar. The experience of more than 3 decades in numbers started in 1989. First fiber laser cutting machine in the world. 6+ manufacturing units laying over 54,000 square meter. 26+ patents, 15,000+ installations, 40+ countries covered, and yes, a government-approved R&D facility. We listen to our clients' needs, discuss them, and create solutions. Every day, we join together to create brands and long-lasting partnerships with our clientele ranging from Fortune 500 companies to small, medium, and large-scale industries. The journey has been nothing less than a major success. The manufacturing and management processes are what it takes to be a leader across the domain. We take care of all our customers and the environment, as our machines are ISO and C certified. and follows 5S, Kanban, Six Sigma, Kaizen, lean management, and quality management systems. As an outcome of this strict quality control, we have been trusted associates with research institutions for years. We have contributed to hugely successful missions like Chandrayaan. Our prime focus lies in making India proud, adored by the customers, honored by the world, as the mark of our sensational acknowledgement. So far, we have received 27 plus awards, to name a few. 5 national awards, 2 R&D and Innovation Awards, 2 Entrepreneurship Awards, 2 Best MSME Awards, 3 Quality and Manufacturing Excellence Awards, the Dr. Vikram Sarabhai Award, and Best Workplace Award and counting, Best Electronics Industry, 2 Best Brand Awards. The flag bearer of many ingenious systems, a true trailblazer, which has been making its way across the industries, from standard to highly customizable laser machines for cutting, marking, cleaning, annealing, scribing, welding, hardening, cladding, and micro-machining applications. Our purpose is to make solutions that utilize the least amount of manpower, yet attain an accurate result. Keeping this purpose at the center of our product line, we offer solutions across all the strata, matching diversified manufacturing needs. We have developed shop floor automation and robotic laser solutions since they are the industry's future, because robotics are highly flexible to do 3D applications, with quick mobility and high quality output. These robots can readily process the work in no time. The seed of innovation has been striving since its establishment, and we are continuously giving to the world new types of laser solutions, and many special purpose machines for those who need more than just a laser solution. The solution identified after an in-depth analysis of production needs has undergone many tests and experiments. Gem and jewelry. We are the pioneers of the diamond industry and have proliferated the industry with our one-of-a-kind diamond processing solutions. Our laser systems have blown the wind of the automation revolution in this field. As a result, manual work has been substantially eliminated. With our R&D efforts at their best, we engineered one-stop solutions to convert a rough diamond into a polished one. By creating CBD or HPHT diamonds, we are now focusing on one of the most lucrative and valuable alternatives for mined diamonds. We closely monitor the latest consumer trends with market needs and push our limits to empower the gem and jewelry industry. The Masterclass solar thermal solution that channelizes the heat exactly as required. A crucial liquid heating system that works incredibly across many kinds of plants and enhances operations magnificently. To curb the existing energy crisis, our team has developed and successfully registered a patent for a decentralized energy solution to generate biofuel from radiant energy, agricultural biomass, cellulose, or industrial bio-waste. Superior isolation is what our system capably delivers, which allows great measurability. We offer radio frequency and microwave solutions to identify the measurements perfectly, presenting complete solutions from acoustic to photonics to stealth. We customize end-to-end design assembly and testing of the defense and aerospace components. Manufacturing of the U.S. patented design of coronary stents and PTCA balloons in Class 100 and Class 10,000. The company has a dedicated in-house R&D department approved by DSIR Department of Scientific and Industrial Research and acknowledged by DST Department of Science and Technology to comply with international standards of products, the medical division in varied manufacturing and QC activity instructions and corresponding standards. To be ahead of the times, our major emphasis has always been to outshine the solutions in terms of hardware and software to attain advanced perspectives. With the in-house software development team, we are giving one-stop solutions to our customers in our numerous laser solutions, developing internationally while remaining close to our customer and their needs. Our WeCare team provide remote assistance, on-site installation, maintenance, troubleshooting, training, and support globally. The WeCare experts are proficient enough to repair any sort of industrial fiber laser solutions. These are the technocrats with knowledge way ahead of the laser machinery expertise. As quoted by veteran entrepreneurs, a true companion to the customers. We don't sell the machines, we form a relationship with each of our customers and be with them before they buy, while they buy, and after they buy for eternity. Empowering innovation, empowering people. We are taking you toward a technologically advanced future with a motto of innovating constantly. An initiator that has been driving a
So, thank you for watching the video. Actually, I think that first let's show the video so we have an idea what I'm going to talk. So multiple technologies are there. So now going to presentation about that. SLPL is a 34 years laser experience in industry. Go to So we have more than 25,000 installations worldwide. We are established in 99. We have manufactured 6 manufacturing plant. We have DSI approved R&D house. We have 700 employees. ISO 9000. We have more than now 31 patents. We have more 33 awards and exports should be 45 countries. These are our export countries where we supply the laser fiber laser machine to USA, UK, Europe, China. Everywhere we exported more than 500 machines. So basically, when we talk about photonics material processing, so that's why we are exporting all the different segments. Somebody think about why the different segments. When we have opportunity to get a problem of the customer, then we make a solution for them and manufacture a system like that. So we are first in industrial laser. We are first in power laser technology to be inward. In 2003, when the fiber laser introduced by IPG company, a small 10 watt laser, we bought it. Particularly, first interest was to diamond, but it's not working diamond because energy was not there. So we utilized it for other applications for marking. And then in 2003, we developed from them IPG to make a 300 watt single mode laser. So they designed it for us, and we started to cut metal from this thing. Diamond processing, we have also worked our first in world for diamond to polished diamond. So here it's all processes by laser. It's coming over there. Medical device will be also medical stents where it is metal parts, very tiny parts, and we cut it by very special fiber laser systems. So all the equipments of the manufacturing of stent is also manufactured as only. They're not imported. Certain parts we import, otherwise we manufacture all the parts. We also make a building of the balloon catheter is a plastic building. So plastic building and metal cutting is the two parts in the laser side in medical device. Other than micro, we do a lot of for the defense and things. So that is also other part. Renewable energy, we also talking two segments, solar thermal and biomass biogas. So biogas generation by technique, solar thermal is for drying the biomass, and solar thermal and biogas is generated by photolysis. New technology we developed, patented also. It is not pyrolysis, photolysis. We do bombard a laser beam and you could immediately decompose gas. It will decompose biomass and convert it gas. And high-tech software, we do industrial 4.0 all type of machines or equipment we design for and make it for different applications. These are industrial laser systems, so it can be worked out from any problem with powerful. Just we have provided one 22-meter machine to railway for bogie cutting. So this is 22 machine. That is right. Yeah, this is 22-meter laser cutting machine, fiber laser, and here is a welding machine, coach welding machine. This one, and a lot of other machines which is customized and application oriented fiber laser machines. Yeah. This is all evolution of the things. In 1990, we started with the plywood cutting, wood cutting with the CO2 laser, and started to up to the CO2 laser for metal cutting. Also, we supply to Odin's factory, and then after that, we first introduced with the fiber laser, and we supply a lot of these things. Even low power laser to high power laser. Low power means start from milliwatt to we produce 8 kilowatt. So in space and defense, we done a lot of project, customized project. Customer come from problems and we provide a solution with our team and we offer them the solution. So we can take also, we have done the research satellite. We produce, design ourselves, have recently kept a radar, manufacture in our plant. We make a machine. The antenna also manufactured at our place. Then it is launched in space. So this we can, mostly our main expertise is machine building. These are all other products which is mostly absorber. So different absorber, reflectors and transmitting POIs we are making for according to different products. So there is a different rubber absorber for say Navy. There is also some defense product also. So it is like we are certain now direct energy weapon also. This is the laser what you see the CM2I. They use our laser for that prototype. So and this is also 2 kilowatt high-power laser. It's Indian made. 100% laser is manufactured in India and we making it with our own systems. So it is we also make a Penta 5 qualified 1 kilowatt laser which supplied to DRDO. This is our research for manufacturing laser source. So we do for different laser source from up to 6 kilowatt multi mode, 3 kilowatt single mode. Even the laser is required diode. So we fabrication concept for diode manufacturing facility also at our own place. So we manufacture diode ourselves only. We still reach up to 70 watt. We are expanding up to 140 watt. This is the range of FM series, 1000 watt single mode, 2000 watt single mode, and 8 kilowatt multi mode. These all these manufacturers complete indigenously make in India concept. This again depends we supply machine. This is a portable machine for what air cooled for military applications. Directly they want to destroy the mine. So for destroying the mine, we supply the machine. So there is no need water cooling or something. Limiter system for different, we do laser based limiter systems. So we supply to mostly Bell, chess or a lot of defense equipment also. We're limiting for long distance up to 5 kilometer, 10 kilometer with different 915 nanometer with what we making diode. According to that, we combine the diode and multiple power. We design it and design optics to give it to the customers.
5 minutes.
So this is all antenna what we make in that. This is where we have a defense exhibition, so defense officer have visited at our place. This is a stand manufacturing machine. This is a fiber-based stand cutting machine. So we cut the stands, we cut the balloon. Also we supply laser flex as a surgical laser, CO2 laser, can supply to different surgical applications. This is our stands which is used for heart blockage and so. This is the medical device plant, manufacturing plant. This is diamond processing. We do also CVD diamond. We are growing CVD by atom to atom. 3D printing of atom we do. So we design a machine, RF operated 6 kilowatt laser, so microwave, and then we growing with the methane and hydrogen. We growing the diamond. That is lab grown diamond. This is an illustration that in Industry 4.0, as previously diamond has a lot of manual process. Now we have laser process that can be from 4-5 process, it will be manufactured complete diamond like this. Television process 8 months, now it is processed in 8 days. So because of that, we have 15 of the word diamond, 14 diamond is manufactured in India. So we are #1 in exporting diamond because of the technology. This is solar thermal. So this has different application we also offer for energy efficient house, white coal power electrification, the thing. This is a different part of the things. This is a biomass photoresist process. So it decomposes biomass immediately and convert in gas. So we have also patent now, US patent, European patent and Indian patent also. This is the process what we have changed that in the concept. We had normal pyrolysis process, this is the process. What we develop is a photolysis, there is no residuals coming, directly coming, the gas will be converted from that. Yeah. So all different, we have first diamond plating machine in world, diamond laser machine, sewing machine, and lot of things we have first in India and first in world. These are all different awards, we got it from different places. This is our manufacturing plant. This is a private laser manufacturing plant. This is plant, new plant, which can be diode manufacturing on top floor, and bottom floor is a clean room facility for fiber manufacturing. This is also our system manufacturing. This is our main manufacturing of the machinery. This is our head office. With a different, globally we participate in different exhibitions and we have a display of machine there. Yeah, thank you.
Thank you, Mr. Arvind Patel, for a very informative presentation. Any questions? There are no questions. I would like to thank you for your presentation. Just hold on.
Thank you.
Thank you. We'll move on to the last presentation by Dr. B.N. Upadhyaya from RRCAT Indore. His PhD in physics and his areas of research work includes development of solid state and fiber lasers and deployment of laser-based technologies in Indian nuclear power plant for its refurbishing and maintenance. He has, to his credit, 60 papers in journals and 160 presentations in conferences. He has received the DAE Science and Technology Award, and also he received the DAE Group Achievement Award as leader and member for 5 times. He will be making a presentation on development of 1.5 kilowatt pulsed ND laser. Over to Dr. Upadhyaya.
Okay, good evening to all of you. Actually, the title of my talk is Laser Material Processing Technology for Nuclear Field Applications. So, lasers, when it was invented in 1960, it was not known where these will be used. So, lasers were the solutions waiting for the problems at that time. So, in the field of nuclear applications, actually we require sometimes some maintenance, some cutting, welding, drilling, these kind of applications for refurbishing as well as maintenance. So for these applications in nuclear field, it becomes very special because any conventional technology, it requires a lot of time to go there. So because of radiation dose, it is huge consumption will be there for radiation dose. So for that to avoid or to minimize the radiation dose consumption, we try to deploy laser based material processing techniques in nuclear field. So outline of my talk is like this. I will introduce a little bit about laser material processing. Then based on requirement, we have developed several solid state lasers at RRCAT, and then some innovative material processing techniques which we have developed especially for nuclear field applications. And innovation will be related to like in-mass coolant channel replacement, single selected coolant channel removal, triangular block cutting, then water jet assisted underwater cutting, laser welding of fuel pins, and there are several techniques we have developed for nuclear applications mostly. So when we look at the laser material interaction, laser is a low divergence, high focusability source, and we can have a high intensity at any point. So laser acts like a thermal tool. When it falls on some metal surface, what happens? Some portion of it will be absorbed into the material and some portion it will be reflected. So based on the reflectivity of the material and the absorptivity, it will be certain portion will be absorbed and heat will be propagated into the material. So the most of the properties which are important for material interaction is its wavelength, power, pulse duration, and beam quality. So depending on the power level, it will be able to melt the material or it will be able to vaporize the material. So removal of molten material by any assist gas, it can be active or inactive gas. So that will work for cutting. And when we solidify after melting of the material, it is kind of welding will take place. So use of an assessed gas actually provides extra energy that adds up to it, and we have extra energy there. So cutting will be easy in case of active gas. If it is inert gas, then whole energy will be deployed by laser only. So laser material processing requires various intensities, like if we are in the range of 10 to the power 4 to the power 5 watt per centimeter square, then only heat treatment or hardening can be done. Then if it is 10 to the power 5 to the power 7 watt per centimeter square, then melt cutting, conduction welding, and then marking, surface treatment, and manufacturing can be done in this range. And then when the power density is in the range of 10 to the power 7 to 10 to the power 9 watt per centimeter square, then drilling, keyhole welding, marking, cleaning, and shaft cleaning can be done. So this is like this. So deep penetration will occur into the material. And when it is beyond this range, it is not for using in material processing. So basically plasma shielding will take place and gas breakdown will take place. So if you look at the solid state laser technology, then we have a laser material, we should have a laser material or gain medium. Then there is a pump source and pump geometry. That can be either a flash lamp pump system or diode pumping is there, and there is a resonator. So based on that, we will have lamp pump solid state laser, either direct diode lasers or diode pump solid state lasers, diode pump fiber lasers also. And it can be operated in continuous mode or pulsed mode. And in continuous mode, laser beam will be coming continuously. There is no energy will already be there. There will be no time gap. In pulsed mode, it can be either free running, and pulse duration can be in the range of microsecond to millisecond. And if it is a Q-switch laser, it can be in nanosecond to microsecond region. And then mode lock lasers are there, which can provide pulses in the duration of femtosecond to picosecond region. So here we have two types of basically bulk lasers as well as fiber lasers. So bulk laser, basically we have a NDR rod, and it is pumped by flash lamp or diode, and there is a resonator. So there are discrete mirrors here, and all the components are discrete. So any misalignment of the mirror is there, then power will get reduced. But in case of fiber lasers, it is all integrated, and it is pumped by a diode. And double clad fibers are the basic architecture in which there is a core, small core, which is doped with gain medium, and we laser comes out through this core, and pumping is done through the inner clad region. So it is all fiber integrated. Because of all fiber integration, it is very much flexible, and it is also very much rugged as compared to bulk solid state lasers. So based on these technology, we have developed several lasers for nuclear applications. So one of the lasers is our basic building block is 250 watt average power NDR laser. This is a lamp pump system. It provides average power of 250 watt and pulse energy is 100 joule. And here we have a peak power of 5 kilowatt, and durations can be varied in 2 to 20 millisecond. Repetition rate 1 to 100 hertz, and it provides basically efficiency is very low, only 5%. But still it can cut up to 12 mm thick steel because the flexibility is very good. And the advantage is that it is a 1 micron wavelength, so it can be delivered through optical fibers. So optical fibers make the beam delivery very much flexible, and we can have remote processing at a long distance. And about such 10 laser systems we have provided to different units for nuclear field applications. Similarly, based on the same lamp pump technology, we have developed a 500 watt average power NDR laser. It provides a 500 watt average power, and here basically one rod is pumped by 2 lamps, and pump power is 10 kilowatt, and pulse durations are similar. And here again it is our fiber optic beam delivery. So with 10 kilowatt power, up to 25 mm thick steel can be cut, and welding can be done up to 4 mm thickness in SS. And about 6 such laser systems we have provided for cutting and welding in nuclear field. This is the third version in which we have developed about 1 kilowatt average power NDR laser, and that is a 20 kilowatt peak power, and provides about 600 joule of pulse energy, which is very high, and it is the highest reported pulse duration energy with millisecond pulse duration. It is a similar pulse durations, and beam delivery is through 600 micron optical fiber, and then it is able to cut about 35 mm thick steel, and we can weld up to about more than 4 to 6 mm thickness in steel. Then fiber lasers we have also developed, and this is a 500 watt fiber laser which we have developed for again nuclear applications. But here you can see the efficiency is very high, and it is a continuous mode of operation, and beam quality is very good. Lambda square value is 1, and then beam delivery is through a 20 micron core fiber. So here flexibility is very high. So it can be applied for cutting up to 6 mm thick steel and 2 mm well depth, and also for lamp application, laser additive manufacturing applications can be deployed. So this is again a 1 kilowatt fiber laser we have developed. It is based on YB doped fibers, and here efficiency is again 74%, and it is again a single mode output being delivered through 20 micron fiber. And here you can see some cutting a small video. So how the fiber laser is able to cut into metal of about 4 to 6 mm thickness, and this is the steel cutting, very fast speed we can achieve, because in pulse laser speed will not be very fast, but in CW lasers it can be very fast speed. So here for nuclear field applications there are several issues and challenges basically, because it's not in open atmosphere or anywhere where there is no radiation field. If we are doing some job shop, it is very easy to do by any mechanical method or something. But when it is a radiation field or nuclear field, then the basic issues comes out like radiation dose level. It can be internal and external, and there will be gamma dose which will be consumed by any person. Then space restrictions because of the location of the problem. Then unique nature of problems, it will be there. There will be contamination of plates we have to worry about. The safety of person and safety of reactor also is a very point. Secondary waste generation, it has to be safely disposed. There is no provision for trial and error because we can spoil the reactor. And the training of unskilled manpower has to be done because it will require several manpower even after doing with laser technology. Then time limitations because reactors always generate power, and there is a limited shutdown time, so we have to do the job in a limited time period, and then cost also involved. So we go for radiation safety and allow as low as reasonably achievable. So radiation dose has to be minimized in any reactor operations. So maximum dose limit is about 5,000 milliar per year for any nuclear industry employee. So cutting is required either in dry environment or in underwater conditions. So underwater conditions it can be, we have developed two techniques like gas jet assisted as well as water jet assisted techniques. So here at RRCAT we have strength that we have developed our own system, so we can make it tailored for any kind of application. Then we have developed various laser material processing techniques which are unique, and then we also design tools and manipulators as per field requirement. So laser based material processing basically provides the advantage of radiation dose saving, time and cost. So with these in mind, we have deployed laser-based techniques for various applications over the past 15 years in nuclear field. And like this is a daily lip cutting during mass coolant channel replacement campaign. There are several. I will go through these one by one. And recently we did some cutting in TAPS 1 and 2 reactor. So this is actually, if you look at the reactor, a PSWR, it is a very complex design. These are all the coolant channels. So in a single coolant channel, we can see that there is this tube, and there are two more tubes here. So this tube is a Jekyll pressure tube, which has a limited life of 10 to 15 years. So it has because here high water flows through this, and because of this radiation, gamma field, neutron field, and high water as well as high pressure and high temperature, some hydride cracking takes place after 10 to 15 years of operation. So these tubes, these required pressure tubes, need to be removed after an operation of 10 to 15 years. And it is a very complex process because these tubes are joined with a end fitting here. So this is a 2 meter long end fitting, and there is a 5 meter long required pressure tube, and then again at the other end there is a 2 meter end fitting, and inside there is a liner tube. So first it has to be cut. This pressure tube has to be cut from inside. Then there is a bellow here, bellow ring, which encirculates CO2, and then there is a ring, two rings, which has to be cut at the weld joint. So if you can cut the weld joint, then these tubes can be removed, and fresh channels or fresh coolant channels can be placed there. And during the mass coolant channel replacement process, all these feeder pipes and there are reactor intervals like yoke assembly, it has to be removed. It can be removed, and only we have to cut directly the bellow lip. But in case of, if it is required that out of 306 coolant channels, only one coolant channel has to be removed, then all the pipes will be intact there, as well as yoke assembly will be there. So it is a lot of hindrance to reach the bellow location is there. So it is a most complex process for a single channel removal. So how we have done all these things? So here one of the images you can see inside of the reactor. Here you can see there are several feeder pipes, and this is the bellow. So where this is the weld joint, it has to be cut along the periphery. So there is a lot of hindrance around this. So that's why it becomes very difficult to remove a single coolant channel. But in case of EMCCR, all the these feeder pipes and yoke assembly is removed. So for EMCCR campaign, we have developed this 250, we have utilized 250 watt NDR laser, and the required pulse energy is about only 15 joule. And here it is a 3 millisecond pulse duration, and you can see a depth of cutting is required only 2 to 3 mm. So along the periphery, we have developed a tool. Here it is, this is the tool. It fits at the end fitting, and then through optical fiber laser beam comes, and there is a nozzle, so which carries gas as well as assist gas as well as laser beam, and it is focused on the bellow ring, and it cuts around circumference, and within 3 to 4 minutes, 6 minutes time, it cuts the whole periphery, and this can be separated and remove the coolant channel. So this is the actual process in which in reactor it is being cut. So you can see how the cutting is taking place, and this technique we have deployed in 6 reactors nowadays. In each reactor there are 306 coolant channels, and cutting time as compared to conventional techniques, it was earlier estimated to be 3 months by mechanical methods, but by laser method each channel is cut in 6 minutes and only 1 week time is taken. So radiation dose reduction is by 40 times, you can say, and there is a lot of cost saving because of the power production in nuclear power plant. So per day, if you can see a 230 megawatt reactor, so per day power cost is about 2 crore, more than 2 crore rupees. So if we are saving a 1 day, even 1 day of maintenance, then it is a huge money saving. But for single channel removal, it is required that all the feeder pipes as well as yoke assembly will be intact. So that is a very complicated process. In that process, we have to utilize the coolant channel space. Means the same coolant channel for removal of that channel. So for that purpose, there are several steps involved. So first we cut the pressure tube using mechanical chipless cutter. Then laser cutting of 4 mm thick liner tube from inside of the tube is done. Then laser cutting of 11 mm thick end fitting from inside of the tube. And after this, outboard end fitting is removed. Means out of the 2 meter length, about 1 meter length is removed. So now bellow lip is accessible, and we cut the outboard end fitting bellow lip by using bellow technique. And then after cutting of bellow lip, inboard end fitting is removed. So, and after that, because PT, which is a pressure tube, which is roll joint with the end fitting, so that takes away, means underwater cutting is done to remove the PT steps for post radiation examination. So this is the various tools which have been developed for cutting from inside of the tube. Now earlier it was from outside of the tube, now it is from inside of the tube. So these are the various tools which has been developed for cutting of end fitting as well as bellow lip. So this technique also we have deployed in several reactors for removal of selected coolant channels in 220 megawatt as well as 540 megawatt reactors. So this is the how PT stub is cutting is done in reactors. So PT stub is basically required to analyze the stresses around the roll joint area. So here it is very high radiation field, and it is done actually underwater conditions. So here it is the actual optical fiber is coming, and this is the end fitting, and at the end there is a roll joint. So it is done underwater conditions. So this is the how the underwater cutting is done, and you can see the underwater is a very violent process because we have gas jet in the water creates a lot of bubbles. So, but in case if we, and this is another thing is required actually in RAPS 3 reactor, there was a triangular block in place of rectangular block. So for cutting of this we have devised this special technique, and this is a manipulator which we have developed for cutting of these triangular blocks to enhance the life of the reactor. So this is the cutting in reactor, how it has been done. So this is the triangular block to actually enhance the creep margins. So by removing the actinium triangular block, we have enhanced the life of operation of the reactor by more than about means per 2 mm there is actually creep up to mm per year. So 80 mm thickness it can enhance the life of about 9 years, and only the laser technique was possible to do this kind of operation in a very restricted place, even in the presence of yoke assembly and all other things there. So about 32 channels we have done this triangular block cutting, and more than about 160 megawatt unit per year power was means if reactor was shut down because of this, then this much loss of power was to be there. And this is one of the cutting in Kudankulam reactor, in which secondary shutdown system DCV valve was repaired, or it was removed and the replacement was done. So here you can see the orbital cutting, and there is a orbital cutting tool which was designed and developed, and around the circumference laser beam is moving and it is able to cut, and a very fine cut is observed because of the pulse laser. It has a very short duration pulse, and we could do that and remove the double check valve and replace it. So with minimum radiation dose consumption. And again, this is recently done technique in which about 30mm thick steel pipe in TAPS 1 reactor, which is a recirculation loop, and we know that TAPS 1 2 reactors are BWR, boiling water reactors, and it has a means about 40 years of life has spent, and again it is being renovated for further operation. So, but there, because of IESCC corrosion cracking, it has cracked, and these tubes has to be replaced and with a new tube, and for cutting it was required because of high radiation dose. We have developed a tooling. It is an orbital cutting machine in which a nozzle is here. It will rotate around the circumference of the tube. It is 700 mm diameter tube. So around the tube in single pass it is able to cut 30 mm thickness, and with minimum radiation dose we have cut one joint, and which was very critical, and recently our team is going to cut another joints of this loop. So this is one of the techniques in which underwater water jet assisted cutting. So water act as a fiber. So like that, in earlier cases, beam was delivered through optical fiber, and after optical fiber, we can guide the beam through water like a fiber. And in Dhruva reactor, there were several coolant tubes, fuel tubes lying in underwater condition in SFSB there. And it was required to salvage these tubes because these were lying in underwater about 7 meters deep in underwater condition, and because of huge radiation dose it was not possible by mechanical methods, but by laser technique and water jet assisted cutting without any turbulence we could cut by this method. And you can see a small video of cutting. So this is with water jet and laser. So just it cuts the channel. And in actual field, if you see, then here you can see the actual these fuel bundles lying inside the water pool. This is the top of the water pool, and this is the flared end where the fuel bundle is there, and it is highly radioactive component. And we could salvage about 12 number of such tubes to do the to solve the problem. So this is one of the recently done work in which a 500 watt average power NdR laser has been deployed for cutting of end plates. So in place of the fuel bundle. So actually there is a requirement of cobalt for sludge treatment. Recently it has increased because of government initiatives that sludge treatment in metro cities will be done by this cobalt treatment of sludge. So central pin has been decided that central pin will be of cobalt. So that cobalt pin in plate has to be just 2 minutes. So this will be cut, and then it can be removed by laser method. So we have developed a technique for cutting in underwater condition at a 7 meter deep meter. So there are two nozzles which will be cutting these end plates at 2 locations, and this has been separated, and we have done recently mock-up, and actual cutting will be done in KGS reactors. This is a welding problem in which a 500 watt average power NdR laser we are using for welding of fuel pins of PFBR as well as BWR reactors. It is a pulse laser, so that's why heat affected zone and other things will not be there, and it has been deployed at FF Tarapur for in production line, and about more than 1000 pins have been already produced, and it is going on in line, and now we have installed 3 such systems in production line at FF Tarapur, and it is working there. So this is one of the micro welding application in which a small iodine capsule we are fabricating, and in capsule there is about it has a diameter of 0.8 mm only, and wall thickness is 50 micron. It is made of titanium and 4.7. So for this purpose we have deployed a tool in which there will be seen by a CCD camera on a monitor, and welding is done at the periphery, and it has been, this system has been deployed at RPSD BRC, and they are now regularly producing these kind of capsules for eye and prostate cancer treatment. Similarly, for welding of iridium capsules, this is a high dose rate capsule. It is a 10 QE source. and about 1 mm diameter and 80 micron wall thickness is there. So at the end there is a radioactive capsule and it is sealed at the here, this place. And this is for internal organ body cancer treatment. And we have developed this kind of mechanism in which it is can be, because of miniature size, it is very difficult and it is highly radioactive. So it is done in hot cell. So we have deployed it at BRIT, and now BRIT people are doing this and providing it to medical industry. This is one of the marking in which marking machine we have also developed. So it is marking on full bundle end plates. This you can see the marking on. So this is basically evaporation of the surface. So vaporization is done. Earlier cases it was melting and blowing out the material or solidifying the material. So the ablation and cleaning also can be performed by using the ablation method, in which laser system we have made, and on the surface of marble as well as zirconia as well as in cooler, we can remove the surface layer by 10 to 100 micron by utilizing a pulse laser of about nanosecond to microsecond pulse duration. And with fiber optic beam relief, we have developed this technique for decontamination applications basically, and doing this. And one of the methods is laser cleaning, in which compressive strength or compressive residual stress can be generated inside the material, and there is a basically very high energy pulse laser and nanosecond duration, 10 joule, 10 nanosecond pulse laser we have developed, and it is used for peeling of the surface. So at the last I will summarize my talk by saying that I have just introduced laser metal processing techniques, and we have developed several lasers at AutoCAD for nuclear field applications. Then innovative laser metal processing techniques have been developed, and along with tools and manipulators, and we deployed these laser metal processing techniques for various nuclear field applications. And still, although we have developed several such lasers, but there is still requirement for cutting up to about 100 mm thick steels in different nuclear and industrial applications. There is a process requirement for welding up to 10 to 15 mm for reactor installation purposes, and there is a process for cutting out different reactor internals is also required for decommissioning purposes. Also, laser cleaning of reactor components for life enhancement study is also required. And then laser cleaning, contamination of fuel pin components. So there is a potential of laser metal processing technology that should be tapped in a bigger way for nuclear field applications to ease the process, reduce manual consumption time as well as cost. So this was done with a team, and I acknowledge the support from Dr. Svinaki, Director AutoCAD, Dr. S.K. Dikshit, Director Laser Group, Sri Aryaji, our head, and then Samyal team from NPCL, and all my team members in contributing these applications. So thank you for your time and attention.
Thank you. Any questions?
Yeah. Yeah.
I have one question related to this pumping an Nd:YAG laser with the fiber. So
Yes.
what is the wavelength you are getting?
Wavelength 1064 nanometer.
In case if I am interested in to go for 355 or 532, will it be possible?
Yeah, it will be second harmonic generation, third harmonic generation. So after 1064, you have to use a crystal to go for second harmonic at 532, then again second harmonic to go 355.
So in that case, you need to pump that crystal also, or only the?
No, that crystal will not to be pumped. That will be just kept in front of the laser beam, so it will generate that. So
the second question is related to this underwater laser processing.
Yes.
So up to what depth you can do the cutting? So
depth doesn't matter. What happens when fiber is going inside the water?
Okay.
So nozzle will be near to the job.
Okay.
So only a small gap between nozzle and job will be there. So water will matter. Water column is hardly a few mm, means 5 to 10 mm. Yeah,
Any more questions?
How do you deal with these vapors coming out of in the nuclear field?
So vapor is collected by a HEPA filter. So there we keep a exhaust, and through a pipeline we connect whatever hops are, we contain the thing, and we keep pass out through HEPA filter. So HEPA filter contains all the fumes as well as contaminations which are coming out after cutting debris.
And this when you are cutting underwater, these pressure tubes, how do you dispose of this water and the
water? Actually, it is contained inside a container. So pressure tube or this end fitting is vertically down there. So in water it is there. So after cutting, whatever contamination or debris is coming out, that will be collected inside water. So that water is disposed of in some bay or underground because of it will be volume of about 10 to 15 liters only. So that volume is disposed of safely.
And for this below lip cutting, those debris which are coming out, how they are disposed of?
Debris are basically very fine debris and it will be hardly few grams. So they take a very exhaust fans of very high power, and at the top there is a HEPA filter. So again it is taken away and it is exhausted through that. So,
You generate some waste.
Yes.
yeah.
You can't do without that.
How they deal it.
Yeah. Thank you, Dr. Bhatia, for a very good presentation. The session is closed and all are requested to go to the main auditorium for the plenary.
On behalf of the organizers, I would like to thank session chair, Professor Kamachi Modi, for conducting this session so nicely. And I'll request Dr. S.K. Dikshit, Laser Group Director, to please give a moment to our session chair. And there is an announcement now that we have the evening lecture in the main auditorium by Shri M. Sankaran, who is director of UR Rao Space Satellite Center. And the title of his talk is India's Pride, Chandrayaan 3 Mission. So you are all requested to be please assemble in auditorium. Thank you. 7:30.
Bhasmi. In the current period of COVID-19 pandemic, Neil Bhasmi, an ultraviolet sea-based disinfection device with multiple degrees of freedom of the light sources, can remotely sanitize air as well as large surfaces of various objects. Neil Bhasmi has integrated safety features to prevent accidental exposure of human beings. The technology of Neel Bhasmi has been transferred to industry. Neel Bhasmi.
Light is ubiquitous in both its presence and its applications. Light makes life possible on Earth and also allows us to delve into the depths of universe to unravel its myriad mysteries. Raja Ramanna Center for Advanced Technology, Indore, an R&D unit of the Department of Atomic Energy, Government of India, is dedicated to advancing the science and technology of light. RRCAT is home to two major sources of light, namely lasers and synchrotrons, and the Light Exploratorium is dedicated to generate curiosity and increase awareness in this vibrant field of science. Under Azadi Ka Amrit Mahotsav, Light Exploratorium was inaugurated on 8th July 2022 by Padma Vibhushan Dr. Anil Kakodkar, Chancellor HBNI, former Chairman AEC and Secretary Department of Atomic Energy, Government of India. The Light Exploratorium is housed in the erstwhile Sukhnivas Palace, which was a summer recreational point developed by the Holkar dynasty of Indore in the year 1903. The palace is situated on the banks of Bhamori Lake and is surrounded with natural beauty and rare species of flora and fauna. The Light Exploratorium at RRCAT, spread over an area of about 630 square meters, is a unique and one of its kind museum in the country that showcases light in its various manifestations and their applications. The Light Exploratorium houses about 25 exhibits spread over 2 floors in the Sukhnivas Palace. The exhibits are hands-on models that students can experiment with to understand the various properties of light and their uses. The Exploratorium hopes to act as a bridge between textbooks and formal laboratory activity in understanding light and serve as a teaching aid for science teachers in explaining about light and its properties. The exhibit layout starts in a central hall which houses a banner with a timeline of important events associated with light in the history of mankind. The bottom half of this banner displays the electromagnetic spectrum in all its glory, starting from very low frequency and all the way up to gamma rays. Subsequently, one walks through various exhibit rooms in sequential fashion, exploring the wave nature of light, the particle nature of light, geometrical optics, the finite speed of light, biological effects of light, physiology of vision, etc. An exhibit on the Raman effect is set up in the room dedicated to Sir C.V. Raman. The basement floor houses exhibits on discovery of lasers, modern light sources, applications of light in industry and biology, etc. There is an exhibit dedicated to our star, the Sun, in the Sun Room, followed by an exhibit on light and gravity demonstrating the use of laser interferometer for detection of gravitational waves. The Light Exploratorium endeavors to make learning about light both interesting and fun. The exhibits in the Light Exploratorium will be constantly upgraded and modified so that people visiting it after a while would have something new to learn about light.
Good evening. The session is about to start in few moments. Those who are sitting at the back rows, can I request you to please come forward and occupy the seats in the front rows, please? Can you please occupy the seats in the front rows? Thank you.
The Raja Ramanna Center for Advanced Technology, a constituent unit of DAE, has India's only two synchrotron radiation sources, Indus 1 and Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. There are 19 operational beamlines, among which 2 beamlines were commissioned in the last 3 years. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation at Indus 2, 3 insertion devices have been commissioned in the last 3 years and the related beamlines are being constructed. The total number of user experiments have been increasing steadily and was 639 in 2016.
Sheetal Vahak Yantra. Shivai is an economical and eco-friendly liquid nitrogen-based transportable refrigerated container for perishable items like fruits and vegetables of farmers, pharmaceuticals, dairy products, etc. It can be transported on any carrier like train or truck or built on any chassis of vehicle. It is designed to withstand rough roads without maintenance problems. Shivai has successfully completed 1000 km of road trial. This development will enable farmers to transport produce without quality degradation. Oncodiagnoscope. Oral cancer is the third most prevalent cancer in India. Presently, biopsy is the only definitive method for determining oral cancer. Oncodiagnoscope is a point-of-care optical device for instant non-invasive diagnosis of oral cavity cancer. It provides online probabilistic diagnosis in real time. Oncodiagnoscope will be a boon for India against cancer. Oncodiagnoscope, harnessing light for early diagnosis of cancer. Tuberculoscope. Tuberculosis is a major health concern in India. Sputum smear fluorescence microscopy is the gold standard for diagnosis of pulmonary TB. Tuberculoscope is an indigenously developed, portable and user-friendly fluorescence imaging device for rapid TB diagnosis. Clinical validation of tuberculoscope is being carried out in collaboration with TB hospitals. The device provides 100% diagnostic accuracy. Tuberculoscope, a complete diagnostic aid for complete eradication of TB. Neel Bhasmi. In the current period of COVID-19 pandemic, Neel Bhasmi, an ultraviolet sea-based disinfection device with multiple degrees of freedom of the light sources, can remotely sanitize air as well as large surfaces of various objects. Neel Bhasmi has integrated safety features to prevent accidental exposure of human beings. The technology of Neel Bhasmi has been transferred to industry. Neel Bhasmi.
Light is ubiquitous.
एंट्रेंस नहीं आया अभी।
Indus 2. When a moving high-energy electron is bent by a magnetic field, it emits radiation called synchrotron radiation, which is used for experiments in experimental stations called beamlines. There are 19 operational beamlines, among which 2 beamlines were commissioned in the last 3 years. The beamlines are national facilities dedicated to the utilization of X-rays for the study of materials. Experiments for Mangalyaan and Chandrayaan 1 and 2 missions for the calibration of detectors and validation of software have been carried out. Determination of the crystal structures of materials for understanding and enhancing their properties are carried out. Proteins present in all living organisms have extremely complicated structures which can be easily determined at a synchrotron beamline. Uranium-based nuclear fuel have been studied, which is important for fuel production and reprocessing. Detailed measurements and analysis have confirmed the non-toxicity of mercury-containing Ayurveda medicine Ras Sindura. X-ray lenses developed at Indus have been used for in-house applications and at the Diamond Light Source, UK. Imaging of the internal structure of tissues and human bones have been carried out. To further enhance the properties of synchrotron radiation at Indus 2, 3 insertion devices have been commissioned in the last 3 years and the related beamlines are being constructed. The total number of user experiments have been increasing steadily and was 639 in 2016.
Sheetal Vahak Yantra. Shivai is an economical and eco-friendly liquid nitrogen-based transportable refrigerated container for perishable items like fruits and vegetables of farmers, pharmaceuticals, dairy products, etc. It can be transported on any carrier like train or truck or built on any chassis of vehicle. It is designed to withstand rough roads without maintenance problems. Shivai has successfully completed 1000 km of road trial. This development will enable farmers to transport produce without quality degradation. Oncodiagnoscope. Oral cancer is the third most prevalent cancer in India. Presently, biopsy is the only definitive method for determining oral cancer. Oncodiagnoscope is a point-of-care optical device for instant, non-invasive diagnosis of oral cavity cancer. It provides online probabilistic diagnosis in real time. Oncodiagnoscope will be a boon for India against cancer. Oncodiagnoscope, harnessing light for early diagnosis of cancer. Tuberculoscope. Tuberculosis is a major health concern in India. Sputum smear fluorescence microscopy is the gold standard for diagnosis of pulmonary TB. Tuberculoscope is an indigenously developed, portable and user-friendly fluorescence imaging device for rapid TB diagnosis. Clinical validation of tuberculoscope is being carried out in collaboration with TB hospitals. The device provides 100% diagnostic accuracy. Tuberculoscope, a complete diagnostic aid for complete eradication of TB. Neil Bhasmi. In the current period of COVID-19 pandemic, Neil Bhasmi, an ultraviolet sea-based disinfection device with multiple degrees of freedom of the light sources, can remotely sanitize air as well as large surfaces of various objects. Neil Bhasmi has integrated safety features to prevent accidental exposure of human beings. The technology of Neil Bhasmi has been transferred to industry. Neil Bhasmi.
Light is ubiquitous in both its presence and its applications. Light makes life possible on Earth and also allows us to delve into the depths of universe to unravel its myriad mysteries. Raja Ramanna Center for Advanced Technology, Indore, an R&D unit of the Department of Atomic Energy, Government of India, is dedicated to advancing the science and technology of light. RRCAT is home to two major sources of light, namely lasers and synchrotrons, and the Light Exploratorium is dedicated to generate curiosity and increase awareness in this vibrant field of science. Under Azadi Ka Amrit Mahotsav, Light Exploratorium was inaugurated on 8th July 2022 by Padma Vibhushan Dr. Anil Kakodkar, Chancellor HBNI, former Chairman AEC and Secretary Department of Atomic Energy, Government of India. The Light Exploratorium is housed in the erstwhile Sukhnivas Palace, which was a summer recreational point developed by the Holkar dynasty of Indore in the year 1903. The palace is situated on the banks of Bhamori Lake and is surrounded with natural beauty and rare species of flora and fauna. The Light Exploratorium at RRCAT, spread over an area of about 630 square meters, is a unique and one of its kind museum in the country that showcases light in its various manifestations and their applications. The Light Exploratorium houses about 25 exhibits spread over 2 floors in the Sukhnivas Palace. The exhibits are hands-on models that students can experiment with to understand the various properties of light and their uses. The Exploratorium hopes to act as a bridge between textbooks and formal laboratory activity in understanding light and serve as a teaching aid for science teachers in explaining about light and its properties. The exhibit layout starts in a central hall which houses a banner with a timeline of important events associated with light in the history of mankind. The bottom half of this banner displays the electromagnetic spectrum in all its glory, starting from very low frequency and all the way up to gamma rays. Subsequently, one walks through various exhibit rooms in sequential fashion, exploring the wave nature of light, the particle nature of light, geometrical optics, the finite speed of light, biological effects of light, physiology of vision, etc. An exhibit on the Raman effect is set up in the room dedicated to Sir C.V. Raman. The basement floor houses exhibits on discovery of lasers, modern light sources, applications of light in industry and biology, etc. There is an exhibit dedicated to our star, the Sun, in the Sun Room, followed by an exhibit on light and gravity, demonstrating the use of laser interferometer for detection of gravitational waves. The Light Exploratorium endeavors to make learning about light both interesting and fun. The exhibits in the Light Exploratorium will be constantly upgraded and modified so that people visiting it after a while would have something new to learn about light.
Hello, hello. Okay. Security. Same bro. The mic is already on. Hello, sir.
Thank you so much. Thank you for coming.
My pleasure. My pleasure.
Good evening. Welcome all to the special evening session of this Engineering Conclave 2023. To deliver this talk, we have with us Shri M. Sankaran, Director, UR Rao Satellite Center, URSC, and the title of his talk is India's Pride, Chandrayaan-3 Mission. It is indeed my proud privilege to introduce the esteemed speaker to the audience. Shri M. Shankaran is a distinguished scientist of Indian Space Research Organization, ISRO. He took over as the director of UR Rao Satellite Center, the lead center in the country for design, development, and realization of all satellites of ISRO on June 1st, 2021. He is currently leading this satellite fraternity to realize various types of satellites to meet the national requirements in the areas like communication, navigation, remote sensing, meteorology, and interplanetary exploration. He joined the ISRO Satellite Center, ISAC, currently known as URSC, after obtaining his master's degree in physics from Bharatidasan University, Tiruchirappalli in 1986. Before taking over as director URSC, he was functioning as deputy director for communication and power systems area in URSC and spearheading the developments. During his 35 years of experience in URSC ISRO, he has contributed primarily in the areas of solar arrays, power systems, satellite positioning systems, and RF communication systems for low Earth orbit LEO satellites, geostationary satellites, navigation satellites, space science missions like moon missions, Mars orbiter mission, AstroSat, and follow-on missions. He was instrumental in successful realization of the 70-volt bus for the ISRO satellites, unique design for power generation and distribution systems for the interplanetary missions like Chandrayaan 1 and 2, Mars orbiter mission, AstroSat, etc. He has fostered the industries in the country for fabrication, testing of solar panels, battery systems, etc. He played a significant role leading the center in adopting new technological developments, thereby achieving the historic feat of successful Chandrayaan soft landing on the lunar south pole, thus making the nation pride India as the first country in the world to land on the dark side of the moon. He is currently leading the center towards miniaturization of the avionics systems, indigenization of electronics and power electronics components, micro mini satellite bus developments, etc. He is also spearheading various avionics system designs, realization and qualification for the Gaganyaan program. He has been awarded ISRO's Performance Excellence Award for the year 2017 and ISRO Team Excellence Award in 2017 and 18. He has about 50 publications to his credit in peer-reviewed journals and international conferences. With this introduction, sir, may I now invite you to deliver your talk.
There are only 3 slides. Thank you for that introduction, and good evening to everyone who is present here. And at the outset, let me apologize for the delay in the start of this talk, which is, as we all know, is due to circumstances beyond all of our control. So today, I'm not going to talk anything which you don't already know. I'm going to talk about the Chandrayaan-3 mission, about which almost all of you know very well. But I will be telling certain things which you would not be knowing, some details you will not be knowing. I'll be talking about that. At the end, I'll be also talking about what are the key takeaways and what are our perceived gaps in the ecosystem that is there in making this kind of missions happen. Nothing particular to Chandrayaan-3. In general, the space infrastructure, that is satellite launch vehicles, in this domain, what we see as the gap areas, which the fraternity of engineers and the industry, with the active support of the government, can do something about. So I will give my few cents on that that aspect. I'll be talking about. So my talk, I have not made many slides. Actually, these only 3 slides. The second slide contains a big video. It's about 12 minutes video is there, which contains a lot of information about the Chandrayaan-3 mission. So I will be pausing in between to tell something about what you are seeing on the video. Now, as you all know, Chandrayaan-3 was launched in the month of August. It came for soft landing on the 23rd August. It is actually a combination of 3 satellites. Chandrayaan-3 is actually 3 satellites. As you can see, the assembled module is the one which is on the next to the launch vehicle. What you are seeing, that is the assembled module, and it consists of a propulsion module, a lander module, and a rover module. So this is the actual image of. This is the image of this is the propulsion module, the lander module, and the rover module. The rover module is a very cute, tiny one. It is a 26-kilogram rover, which is a full-fledged satellite. Everything that is in any satellite is there in the rover module. Yeah. I need to go back. This is. I'll stand here only. It's easy for me to do it here. Okay. Okay. Oh, it's not working. pause, I think we have to. Okay, the mouse works. Okay. Okay, the propulsion module is a satellite practically without any payload. The payload for the propulsion module is a lander module. The purpose of the propulsion module is to carry the lander from the orbit in which it is injected by the launch vehicle LVM-3 and carry the lander up to a lunar orbit of 100 kilometer by 100 kilometer orbit around the moon. So this is the purpose of the propulsion module. And as an afterthought, we included a small payload in it. Is called a shape payload, which is a payload which is to study the spectral and polarimetric signature of a living planet like Earth, a planet which is supporting life. The purpose of this payload is to take these signatures at a distance of nearly 4 lakh kilometers, which is the distance at which moon is there from Earth, look at Earth and take the spectroscopic as well as polarimetric signatures of a planet which is supporting life. So that in the future, when we are going for a mission to study exoplanets or the planets which are beyond the solar system, whether we can look for a signature which will be similar to Earth so that those planets can support life. That was the idea. So this is to get a signature of how a planet which supports life, what are all the signatures are there to get it is like a reference signatures to take that this payload has been included. It is a last minute addition, and it also uses acousto-optic tunable filters, new technology which uses the RF and the tuning of the sound waves with which the filter bandwidth is getting tuned, so that we can look at different species. If you can see the electromagnetic spectrum of the reflected light of sun from Earth, so it varies from say around 0.15 micron to around 2 micron. You get the sunlight getting reflected and also absorbed by the atmosphere, and also the processes that happen in the atmosphere. So we are looking for the signature of life through these absorption bands in the light reflected, sunlight reflected by Earth. That is the purpose of the shape payload. So this is the lander module. Not fast enough. It's going too fast. Yeah. Okay. Let's pass. We pass. So a lander module is the purpose of the lander module is to provide the energy to decelerate the craft from the 100 kilometer by 100 kilometer orbit around the moon and make it to land on the lunar surface. If you know that the orbital velocity around moon in about 100 kilometer by 30 kilometer, which is the final descent orbit, 100 kilometer by 30 kilometer, at the perihelion is about 1.6 kilometer per second, and which is, we call it as a horizontal velocity. There is no vertical velocity because it is not moving towards the moon's surface. So what is to be the idea of lander is to kill that horizontal velocity, that is the orbital velocity of 1.6 kilometer per second to close to zero, and increase the vertical velocity. That means make the craft to move towards the surface of the moon and then kill it so that it lands softly on the surface of the moon. Now this lander has three payloads. There is a payload called ILSA, which is supposed to measure the lunar quakes. It is a accelerometer. It's a very fine accelerometer which measures if there are, which is supposed to measure if there are any quakes on the moon surface. We know that moon doesn't have a big seismic activity, but there is a suspicion there are some small amount of vibrations happening, and whether there is a chance we can capture this kind of vibration. What is the source of the vibration is not known. The known source of vibration on the lunar surface is the meteorite hits. When from the galactic particles come and hit the moon surface, that creates a small amount of vibration that is sensed by these accelerometers. And as we later we found out, when the rover moves on that surface of the moon also, it is creating sufficient amount of vibration which the accelerometer is able to pick up. We will come to that at the end, what were the outcomes. So that is one payload. Second payload is called Chaste, which is a Chandra thermophysical experiment. It is an experiment to measure the gradient of temperature across the lunar regolith over 100 millimeter depth, and also to determine what is the thermal conductivity and the thermal capacity of the lunar regolith, which is an important information for future possibility, studying the possibility of whether this lunar regolith can be used for, as a construction material or as an insulating material, or to go for any kind of manufacturing that can happen on the surface of moon using the lunar regolith itself. We need to know about the properties of this regolith. So the idea of this experiment is to get this thermophysical properties of the lunar soil. The third experiment is a Langmuir probe. It is called Ramba. It is basically a set of Langmuir probe which is going to do the temporal variation in the very weak plasma field that is available around the lunar surface, both electron and ions, to measure that. A suite of Langmuir probes are there in the Ramba payload. These are the three payloads which are in the lander. The rover is packed inside the lander itself. One wall of the lander is openable. This rover is mounted on that and closed, so that during the ascent from the ground, the orbit raising period and reaching the lunar orbit till touchdown, it is safely cocoon, like a cocoon, it is sitting inside the lander. And after the landing, the rover ramp will be deployed onto the ground, and rover will be made on and released onto the lunar surface. So as I was mentioning, this is a very cute small satellite, a full-fledged satellite with, in addition to satellite, what it has is this wheeled mobility. It is a 6-wheeled rover, each wheel independently controlled by its own motors and drivers, and weighing all of 26 kilogram, and having its own power generation, battery, everything, and a host of full electronics. This also contains two payloads. Both are basically to study the elemental composition of the lunar regolith. One is the alpha particle based system, which is with an alpha source. We are going to create X-rays, and these X-rays are going to bombard on the surface of the moon, and whatever emission comes out of it, take the spectroscopic signature and identify the elements that are present there. The second instrument is called LIPS, which is again similar work, which is done through a laser. We are ablating the material on the lunar surface with the laser energy, and again doing the elemental composition. These are the two payloads in the rover. Of course, supported by all other paraphernalia, communication, baseband, everything is there in this rover. Now, when I said this is a 3-satellite combination, it is also, in another sense, a 3-craft combination. This we knew when we did the Chandrayaan-2 itself, and it got reinforced after the setback we had in Chandrayaan-2. And I will tell you what are the three in this. It is, Chandrayaan is a combination of 3 crafts, one a satellite, one a reusable land booster, which is landing back after in the rockets. Now you would have studied, you would have heard about all new rockets, particularly from SpaceX. The booster, the first stage is being recovered. Every time they are using more than 20 times the same booster, which is one of the cost-cutting measures. So the booster will take the remaining stages of the launch vehicle up to say some 40-50 kilometers, and then generally it will be disposed into on the ocean. That's how we have been doing. Even now we are doing that only. Whereas in a reusable launch vehicle, that booster will stop burning. After the separation, it will do a retrofire and come back and land precisely on the place where it is supposed to be land in the launch pad itself. So the Chandrayaan has a satellite, reusable booster landing back, and also an aircraft, but which doesn't have a navigation system, which doesn't have a GPS. An aircraft without GPS, you can assume. You don't have what is the terrain, you don't know what is your coordinates, but still it has to do a function an aircraft does of navigating itself over an unknown terrain. So Chandrayaan 3 spacecraft, when we say it is a combination of 3 crafts, a spacecraft, a reusable booster which is coming back and landing, and an aircraft without a navigation system. So all of them put together, if you make one craft, that is what Chandrayaan did. For the interest in the people who will know what happened in Chandrayaan 2, why we did not successfully land in Chandrayaan 2, and how we managed in Chandrayaan 3, there is only one simple answer for that. The answer is that any mission of this type, every system has to work within a defined limits of performance. You can call it as 1 sigma, 10 sigma, or 3 sigma, whatever be the sigma. The limits of performance have to be defined, and every system has to work within that limit of performance, so that everything you can plan for different contingencies, and we can achieve the goal. Chandrayaan 2 was designed for a 3 sigma deviation in the performance of all systems, and everything was tested for that also. But unfortunately, we did not make any provision for beyond the 3 sigma. If any system performance goes beyond the 3 sigma variation, there was no provision made in the system for handling such a scenario. That was the flaw in Chandrayaan 2, because as I mentioned, it's such a craft which is like a aircraft without a navigation system and a landing rocket. We should have foreseen that some system will go beyond the defined limits of performance. So, and we should have made some salvage arrangement for that, which was not there. That is the reason why we did not achieve the success in Chandrayaan 2. Chandrayaan 3, actually what we built so much margin and robustness, and also instead of 3 sigma, we allowed it up to go to 6 sigma, additive extremes, all that were done. But when you are well prepared like that, you call it luck or your own preparedness, no margin was required. All systems performed on dot, not even 1 sigma. Everything performed, everything worked well, and we landed dot on the point what we were supposed to do. So this is the critical lesson we learned from the unsuccessful Chandrayaan 2 landing attempt, is that though we believe all systems will work as per the defined limit of performance, be prepared for the worst and make some provision to take care of the unforeseen. That is what was done. And as there is a saying, luck favors the prepared mind, not the brave. Luck favors the prepared mind. We were better prepared for this one, so there was no need for any luck, and everything happened as per plan. Again it has started. Okay. Okay, let it go. Okay. No video. Yeah, that may be better. I'm sorry for the, I try to be more smart, but smartness doesn't work all the time. Now spacebar itself will work, isn't it? So as I was mentioning, uh, this is the rover ramp. This is openable. The rover is packed inside that. Now this is the disassembled view of the lander rover. This is a propulsion module. I'm not going to discuss all these things because these are like any standard satellite. All the elements are there. Only I was telling about the payloads. The Ramba payload, its probe, a deployable probe is there. And similarly, the Chaste payload, which is also a deployable probe, which needs to be deployed, and about 100 millimeters it has to penetrate the lunar regolith. And we have a number of other cameras and sensors, which we'll discuss as we move along. We'll discuss. Okay, the ILSA payload is there at the bottom. So this is nothing but one chassis of the lander is the rover is just one chassis on which everything has been, all equipment has been placed. The 6 wheels with a differential and 6 DC motors are controlled. Now, when we say Chandrayaan, we realized 3 satellite combination. It is not also realized for only one time. A number of models of same Chandrayaan 3 also was realized, not exactly identical, but many systems were packaged for different purposes. As I was mentioning, this is the whole module for flight. That is what we are seeing here. We have made one model for what is known as the integrated hot test. I will tell about the details of all these tests in subsequent segments. This is a test where the hot test is a test where we are testing all sensors, the software and all the electronics along with the propulsion system together by hanging it from a tower crane, simulating the 0G condition as if it is from some 100 meters, it is going to come down and touch down on the ground. Like that, it was a facility was created in our Sriharikota range, and the whole system, everything worked. All logics were tested. With the vibration and the noise that is created by the engines. There are 5 800 Newton engines and 16 58 Newton engines there on the lander modules. All of them, when they are firing, it is going to create a lot of vibration. The very sensitive laser-based sensors and cameras, they have to work, and so this was confirmed in this hot test. The cold test is the hot test minus the propulsion system, which is only the sensors and all the electronics. This was put on a helicopter, and the helicopter was made to go up and down, simulate the velocities. Of course, we cannot simulate the 1.6 kilometer per second velocity. We could simulate up to about some 60, 80 meters per second, 100 meters per second. That range it was possible to simulate. And the third one is the landing legs design was validated through a number of tests. The single leg alone, 4 legs together, it's only as a shell, only CG simulated. As the entire structure, CGMI, everything simulated. A qualification model was made. You have to, the trick is, we have to do the lander leg qualification for various conditions, like because there is going to be a horizontal velocity as well as vertical velocity. So we have to create a test rig where we can give a controlled horizontal and vertical velocity, and make the lander to land on a slopy surface. We have to create a surface with different slopes, and the slope is filled with simulant, which simulates the lunar soil characteristic. The soil characteristic is as identified by the Apollo missions in the 70s. Whatever landing missions they had measured. One point what we will discuss at the end about this, Apollo missions, all of them landed near the equator of the moon, whereas we were going to land near the South Pole. Nobody even had a suspicion that the regolith properties are going to be completely different. But that is a different story. At the end, I will tell it was completely different. But this test bed we made using that Apollo data and simulated the this soil simulant. We found a place in Tamil Nadu, in Salem, one quarry. We found the rock characteristic is exactly similar to what has been seen by the Apollo mission. So we one lorry load of that rock was brought, pulverized into various grades, small, different sizes, to simulate the various particle size of the lunar regolith, and the test bed was created. So this very extensive test. This test campaign itself went on for nearly 2 years. These are all hardware-based tests, and the software logic and everything. Maybe about 100,000 test cases we would have done for the software end-to-end simulations. Because every time you make any change in any system, you have to redo all the simulations one more. At least easily 100,000 test cases we would have done the software simulation. It's a huge amount of work that was carried out for this. So as I was mentioning, the 3 modules and the 3 main hardware test cases. Now this is the integrated code test which I was mentioning. A module was created which can fit at the bottom of a helicopter, where there is a cutout is there in the helicopter, because it has to see the earth. We have a range at Chitradurga. It's a large campus. We created a large terrain simulating the moon surface with boulders and craters, removed the bushes, because we found, after doing the test, we found the trees are also giving false signature. Trees are small bushes which are there on the ground on earth, because there are no trees in moon. But these trees were giving signatures similar to a boulder or a crater. So we had to clear a large area full of all de-weeding had to be done, create a barren area, make the craters and boulders, so that through that cutout the sensors can see the ground and the sensor working and all the logics working. We need to also do this autonomously, because the power descent, entire duration of the power descent is about 20 minutes. There is nothing you can do from ground. There is no intervention possible from the ground. Everything has to happen autonomously on board. For that reason, when we are going to land, we should find where we are going to land is safe to land or not, or the trajectory what we are taking, whether the trajectory is as per the planned trajectory. So what we do, we had imaged the entire moon surface, the full circumference of the moon surface using our Chandrayaan 2 orbiter. We have the best camera on the moon there with a resolution of about 25 centimeters resolution. We have a camera on the Chandrayaan 2. So the entire surface of the moon was imaged, and we created an atlas of moon. And when we made the trajectory for this landing from the perinoon point, the craft is being made to move around the entire trajectory. What it is going to see, the sensors and cameras, what are the features that are going to be seen, how to recognize those features, and from that the software should autonomously find out and tell the lat lang of the point, so that the software can confirm that the planned trajectory and the realized trajectory are same, or there is this much deviation. This is during the flight, and just prior to the landing, we also need to make sure where the lander is about 4 meter by 4 meter wide. But even though we are looking for a very safe place, there is no safe place large enough the landing site was 4 kilometer by 2.4 kilometer. But even though that is relatively safe, the site is full of craters and boulders. So we need to make small grids of 24 meter by 24 meter. So in that 4 kilometer by 2.4 kilometer, small grids of this 24 meter by 24 meter was made, so that which grid is safe for landing. If there is a big boulder or a big crater, that is made red. If it is less than 1 foot, anything is there, okay, it is safe for landing. Like that, a grid was made. So the camera, when it images, it has to compare with the previously imaged, previously taken images of the surface, which is loaded already in the craft, and it has to come out with a 3D fit and tell this is, we are at this point, the grid number so and so of that 4 kilometer by 2.4 kilometer. So directly Nadir, right down is may or may not be safe. You move by horizontally some 10 meters or along X direction by 20 meters. This output has to come from the software autonomously, and this output should be used by the software autonomously to move the craft to the required orientation before landing. Everything has to be done autonomously because no intervention possible. So this is the importance of this test. This nearly took more than a year for us to do this test. The Indian Air Force, I should thank. They had, in fact, they went beyond the agreed number of sorties, and in fact, they also became so much interested. No, they said, "Sir, when we can go for the next sortie?" Like that. So, like that, so many tests were done. It's an outstanding experience. The people, how everybody has contributed for this test. I will leave you to that. So this is actually the test in the Chitradurga range, where the craft was made to hover, go, ascend, descend at different speeds. Everything worked properly. Okay. This is the hot module. This is the hot test module. The peculiarity of this hot test module is, you all know that Moon's gravity is 1/6 of Earth. So the landing is being done by balancing the gravitational acceleration by firing the engine in the retro direction. So you balance the gravity and allow a small velocity to build so that it will come. And as it comes closer to the surface, you try to balance it so that the touchdown is happening at a very small velocity of the order of 1 meter per second. So when we and the lander craft, when by design, the landed mass is supposed to be 800 kilograms. Now we have to test this on Earth, means the landed mass has to be made 1/6 of that. Then only we can, with the same engine, we can compensate the gravity. This is one problem. Problem is all these kind of thrusters are designed for working in vacuum. The same thruster, if you fire in 1 atmosphere condition, you are going to get nearly about 60% of the thrust only you are going to get, because in vacuum there is no restriction for the flow of the ejecta from the engine. So the entire effluents go out, the gas goes out, the burnt gas. Whereas in Earth, because of the resistance offered by the atmosphere itself, 800 Newton engine was giving less than 600 Newton engine. It was giving 540, 550 Newtons. So it's a double whammy. We have to compensate 6 times more gravity, and the engine, same engine we have to use for the test, but engine capacity is reduced by 60%. So we had to make a module which ideally we should have made it about 90 kgs or so that we could have done the test. But 90 kgs we cannot even put all the engines and the smallest amount of propellant tank. So we came up with a scheme of offsetting through balancing. Other side put a balancing load and make a new dedicated mechanism to release it as and when required, so that the gravity balancing, that itself became one project. It took really some time for us to work out this. This test was carried out in Sriharikota. Nearly, this also took about 6 months for us to do the test. It has to, like any a flight satellite, it also has to go through all dynamic balancing, CG inertia measurements, everything. So on a tower crane it was hung. Here also we created the boulders and craters to simulate the lunar surface so that the sensors are able to identify and make the required movement. Actually, the people who have got involved in this, though URL Satellite Center is the lead center for this work, and many people work from URL Satellite Center. I think across the country, all ISRO centers and many industries and many people who are not even connected with our work have contributed for this. Now we'll come to the lander leg. As I was mentioning, we developed a new test rig where we can give a controlled horizontal as well as vertical velocity. And we made the test bed such that we have a flat surface as well as a slant surface, which is a 12-degree slant. That is the maximum in the landing zone was expected. So many tests were done. You put it on hard surface, soft surface, only one leg touching, two leg touching, and one leg not touching. Like that, so many different combinations, permutations, because the idea is to ensure that after touching down, the craft should not topple. You do everything, and at the last moment, this one problem. The other issue is because there is an expected gradient about 12-degree gradient, and we are firing the engines at touchdown. The moment the one of the leg touches, your CG has now gone. Till it is hanging in vacuum in air, we know where is the CG. We can, the thrust axis is passing through the CG, and we can control with the control thrusters. The moment one leg touches the surface, the whole system, the CG gets transferred. The point where it touches acts like a fulcrum. So if you are firing the engines, it is going to any duration, even 300 milliseconds. If you are firing, it is going to topple the craft. This has been simulated and found. So what has to be done? We have to, as soon as it touches down, within 100 milliseconds, we have to cut the engine, and so that another 50 milliseconds, the transient will be there. The engine shutdown transient will be there. Within that time, it should go off. This became very important for us to characterize in the different surfaces what are the reaction forces, how many times it is going to jump up and come back, what is the maximum slope it can tolerate. Lot of things had to be done. So it's also a very involved test. Even assuming that we may land on a rock, we did a test by putting MS plates on all surfaces, made it to land on very hard surface. So when all these tests are done, we have got sufficient confidence. I have not intentionally put anything about the software tests. As I mentioned, there is nothing for me to show here. Only 100,000 cases have been, software simulations have been done, and we ensure that not even a single case we are getting a failure. That was the outcome of that. This is the flight model, how it is getting realized. The flight model realization actually took less than 1.5 years. We made the entire craft. So this is the craft lander getting into the thermovac chamber. The EMI test, because some 6 carriers are there and 6 receivers are there. All of them have to work together. So this is the rover deployment on the ramp. The Chaste, ILSA, Langmuir probe. This is the Chaste. Again, all these deployments, that helium balloons are there for 1G unloading. As part of this rover development, we developed a single board electronics, all satellite electronics other than power system, remaining all were made into a single board. Actually, that was the starting point. This we did for Chandrayaan-2 itself. And that was the starting point of the other point. When they introduced me, they were telling Now we are moving towards making all the electronics of the entire satellite except the RF front ends, LNAs, the sensing elements and power system. Remaining all make into a single package. That is the work which is the offshoot of this rover development. A number of vision-based sensors are there in both the lander and the rover. Vibration and the thermovac for the rover, and within the thermovac chamber also deployment was done, because the rover is going to get deployed on the lunar surface, where though we have made all arrangement to control the temperature, we were also trying to make sure that even if the temperature is slightly low, the rover deploys and moves. So the vibration and acoustic was done repeatedly with the combined module together. The vibration and acoustic tests were done, and their modules were separately transported to Sriharikota, where after again test of all systems, they were fueled and assembled back one over the other, and given to the launch vehicle team for launch preparation. So that is a payload fairing. Encapsulated the assembly is assembled on top of the LVM3. So that was a majestic liftoff of the LVM3 with the Chandrayaan-3. It was better than what you could have asked for, because it gave not only a very precise injection and also gave little more orbital velocity than what was guaranteed, because every gram of fuel we can save on the Chandrayaan is bonus for us, because fuel is the maximum premium item in the spacecraft. So the LVM3 gave us little more than what it promised. So after the separation, this is the onboard video of the LVM3, the Chandrayaan getting separated. And while we were en route to moon, the camera on the lander imaged the Earth at some regular intervals. It was done. So this is the trajectory. As you know, progressively, as we have been doing for all our planetary missions, progressively the orbit is raised. The simple reason, most of you must be knowing why it is done. The idea is, if we have to go like the Russians tried, we could have also gone in 4 days to moon instead of taking 42 days. The penalty is the landed mass 800 kilogram would have been reduced to 300 kilograms, because the efficiency of the propulsion system of the satellite is better than the efficiency of the propulsion system of the launch vehicle, because launch vehicle inert mass is high. We cannot do anything about it. So the efficiency of satellite propulsion is generally same kind of propellants. In fact, in the launch vehicle final stages cryo, it is supposed to be even better. But because of the inert mass, advantage is there for the satellite. So we could have put LVM3 could have directly put Chandrayaan in a lunar orbit, but the landed mass would have been reduced from 800 kg to 300 kg, which is not in our interest. That is why this approach, which we have been doing from Chandrayaan-1 onwards, where we are incrementally raising. The raising incrementally also there is a reason, because any orbit raising, the Hoffman transfer requires the impulse acceleration addition has to be given. That is, if I want to raise the apogee, I have to give an impulse at the perigee, so that whatever total energy has to be transferred at a single point, then it is maximum efficient. But that is only theoretically possible, because engines have finite thrust rating, and if you are firing, if you have to get the required force, you have to fire it for a duration. It means you are firing over an arc. When you are firing over an arc, there is something called arc loss that happens. So if you are not going, it is 100% not efficient. So to minimize the arc loss, you have to fire only in a small segment of the orbit, so that the loss can be minimized. So every time you come to the point, in this case we have to raise the apogee. So whenever it comes to the perigee, you keep on giving small amount of this one. So it keeps on raising. It's a very simple thing, effective. That is, maybe I should slightly go back in this one. What is the mathematics involved here is very important. From, well, quickly we'll move there. Launch orbit characteristics on the day of departure from Earth and arriving at Moon, everything needs to be very precisely calculated, because as you see, when we are starting from Earth, Moon is somewhere there. It is almost 90 degree away, or one quadrant of the orbit away. What needs to be done is, where you want the satellite to arrive at the Moon, at which point of the Moon's orbit the satellite has to arrive next to Moon, so that you will achieve the desired orbit around the Moon. Very precise calculation needs to be done, so that this at the time of launch, nearly almost 110 degrees away in the orbit, Moon was there. So we have to precisely compute when it comes at this point, what should be the velocity, so that it gets captured in the Moon's gravity field. So once it gets captured by the Moon's gravity, we again do the same thing in the reverse order. Fire the engines in the reverse direction to reduce the velocity, so that the orbit keeps on reducing. Finally, it came to 100 by 100 kilometer orbit, and there the propulsion modules get separated from the lander module. Lander module at that point onwards is separate. So this is the onboard video which we got when the Chandrayaan 3 craft was captured by the Moon's gravity. The distance from the Moon was about 110 kilometers. From the illuminated side of the Moon, we are moving towards the dark side. So various features of the Moon were captured using the onboard cameras, which anyway our scientists will analyze these. So this is animation. The idea here is, when we are separating the two crafts, we also want to use the propulsion module to do some characterization of the sensors on the lander module. So what we did is, we rotated the propulsion module like that, and then pointed the laser and the RF from the lander module towards the propulsion module, got a reflection back to verify that all our sensors in the lander module are working. This is also a new thing which was done in Chandrayaan 3. What you saw there was just as a dot was the propulsion module taken by the onboard camera from lander. So if we are seeing really the surface of the Moon, nobody will tell Moon is beautiful, but it is really beautiful only. So this is another one. Every system on the lander was characterized prior to the powered descent. In the 100 by 100 kilometer orbit, every system was tested. The test what we are showing is, one of the tests is fire the engines to verify that there are 4 engines, 800 Newton engine, to confirm that all of them working and working to the specification. A test sequence was carried out by firing engines in sequence. In the process, also reducing the periloon from 100 kilometer to 30 kilometer. So this was the simulation of that. So 2 engines firing, they go off, other 2 come on. And a second test where all 4 engines at this time we also did the hazard detection and the position detection cameras. We also need to calibrate for their radiometric corrections. Like we have predicted what will be the illumination and what will be the return from the lunar surface, so that like the image taken by the camera should not get saturated, it should not be oversaturated, or it should not be under illuminated. So we need to tune the integration time for the camera. For that we need to do one calibration. So we did a run over the trajectory with an illumination condition similar to the condition it will be there at the time of actual landing, and try to find out what is the reflection that comes from the moon surface, so that the integration time can be tuned. Now the second deboost, all 4 engines were fired and also throttled from 800 Newton to 400 Newtons in a profile like how it will happen during the actual landing, which is the full end-to-end simulation of our power descent trajectory. After all the assessment of all the sensors, algorithm, engines, everything, we were ready for power descent. Most important thing for the power descent was 2 things. One is the orbit, that 100 by 30 kilometer orbit should be known precisely to the accuracy of 5 centimeter. And the attitude means the x, y, z or r theta, the 3 orthogonal axes. The pointing also should be known to the accuracy of about 50 arc seconds. These are 2 fundamental requirements for the successful landing. Otherwise, if these are beyond these bounds, we are going to overshoot that 4 kilometer by 2.4 kilometer. This is 4 days we remained in this 100 kilometer by 30 kilometer orbit, and ensured that 4 days the orbit remains stable, and also the attitude control is making it happen within this 50 arc second. And also for a contingency purpose, we also tested this contingency communication. For some reason, the communication from ground to the lander does not happen. We should have a contingency backup path. So we did a maneuver on the Chandrayaan-2 orbiter to ensure that at the time of power descent, the Chandrayaan-2 orbiter will come in the line of sight of RF line of sight of the lander, so that communication to and from the lander can happen via the Chandrayaan-2 orbiter. This also was planned, tested, and made available. So as I mentioned, very accurate orbit determination. Here we got support from JPL, ESA, as well as our own ground station for the two-way Doppler measurements, because our own one ground station at Bangalore will not have full orbit visibility. We'll have about 10 hours visibility only. To do this accurate orbit determination, we need throughout the orbit two-way Doppler measurement, which we could do with the support of both NASA and ESA. So this is the final this one. The power descent itself is broken into 4 separate phases, where from 30 kilometer to 7.4 kilometer, and velocity reduction from 1.6 kilometer per second to some of the order of about 100 meter per second. Then an attitude hold phase, where we are not allowing the engines to disturb the craft and taking the attitude cameras to determine the position of the craft with respect to the planned trajectory. Then followed by a fine braking, where we are targeting either 800 kilometer above the surface or 100,300 kilometer surface. That is the dotted one is the contingency case. We are supposed to get in that 6.8 kilometer to 800 meter during the trajectory. We are supposed to get absolute sensor update for the height. We have been otherwise using a inertial navigation of gyroscopes and accelerometers. But as you know, all these inertial sensors will have drift. Over a period of 20 minutes, the drift that will happen are not acceptable for this. So we need to update this inertial navigation given parameters in the software by absolute sensor measurement. So if the absolute sensor gave a measurement, then we would go to 800 meter. If the absolute sensor did not give a measurement, we have to go for a contingency strategy. So there, because the errors are going to be more, you should not go and hit the surface, because the error is of the order of 800 or 900 meters in the height based on the inertial navigation. So the target instead of 800 was made as 1300. Of course, in the actual flight, everything happened as per plan. No contingency scheme need to be invoked. So from 30 kilometers, that 1.68 kilometer reduced to very close to about 100 meters per second. Then here the absolute sensor measurement of the height. We are having two sensors, one laser based altimeter and cab and microwave altimeter. Both worked, both gave accurate measurements. And then because we got the height, we came straight to the 800 meter. If we had not got the update, we would have gone in that other path of 1300 meters. Then again at that point, a sensor is trying to measure both the velocity as well as we are hovering at that 800 meters for about 10 seconds to determine the height and target come to 150 meter. At 150 meter again hover, and a camera is looking down at the nadir and finding out whether the place right below is safe for landing with no craters, no boulders. If there was a crater or boulder, we would have moved based on what is seen to another point and come to 60 meter and then come down. But as I told, no need for any of these things. It happened accurately. All those sensors were working at that phase. So this is what I was telling, the gridding. You can see wherever there are big craters or boulders was made red. Wherever it is deemed safe was identified as green. So that hazard detection camera's idea is to identify one of the green grids and tell how much we have to move in what direction. This was the software doing. That was near the center of the landing strip, came down and landed perfectly. We have omnidirectional S-band antennas which give the continuous coverage of the telemetry, and also a X-band high data rate transmitter with a dual gimbal antenna which was giving all these images which was a big hit during the landing, which came through that X-band dual gimbal antenna. So at 800 meter, out of the 4 engines, 2 engines were switched off because 4 engines will make the craft, it will not allow it to come down. The thrust is too much. So we had to switch off 2 engines. Only with 2 engines it will come down. This was what was expected. Like this, dust will come up. Actually, nothing came up. There was no dust coming up. This is the time where we realized that the terrain is not as per the Apollo landing findings. The terrain, the surface is different from the Apollo landing sites. So all four footpads had touchdown sensors, which all of them declared it touchdown. Within 100 millisecond, engine got shut off. This is after the landing, the rover getting deployed. Onboard video it is. So as you all know, already more than 100 meters, the rover moved around on the lunar surface. Lot of measurements have been done. For the findings so far, I will tell you. For the first time, sulfur has been detected on the surface of Moon. This is an important, if it is found correct, true, because it is only a measurement that has been seen, it has to be confirmed by analysis. If sulfur is present, there is a possibility that you can in future manufacture fuel, rocket fuel from the lunar regolith, because sulfur is an important ingredient which can be used as a fuel. So this is an important finding if found finally true after the analysis. But both the sensors have shown that presence of sulfur is there. Second one is one mild tremor has been recorded by the ILSA, which is the seismic sensor. That also is being studied whether really it is a moon quake or whether it is something which is happening on the lander or rover that has been captured by the seismic sensor. We have to study this. People are studying that. And the Langmuir probe has taken a lot of measurements of the electron and proton densities, energies, all these things have been measured. And the Chaste, which has also now, because we did a hop also subsequently, which we'll see next, at two places we have measured the thermal conductivity and the temperature gradient across that 100 millimeter. This also being analyzed by the instrument PIs. So we will get to know the outcome as we go along. So this is the image of the lander taken by the panchromatic camera on board the rover. So the landing was, the presence of the lander on the moon surface was confirmed through our own Chandrayaan-2 orbiter imager, our radar imager on Chandrayaan-2, and also by the American LRO, the Korean lunar mission. Whoever has a mission on moon, everybody was able to image, and everybody has put it on this one. One of the important finding that was found was, one is dust did not come up. Second one is, you see the track. We had put on the rover wheel the Ashoka symbol, our national emblem, and ISRO's logo on the rover wheel, so that we will make a permanent imprint of these things on the lunar surface. This was the idea. But what we found is the impression is not at all clear enough. Impression is there, but it is not clear enough to be published. Then we also found that when the rover is roving on that surface, the soil is coming like clay. It is coming out like lumps. It is not like a dust on which if I put a foot, mark will be there. If it has more cohesiveness, it is lifting along with the wheel and disturbing itself. So it is not remaining, what impression is there, it is not remaining there. This also is an unexpected result. So then we decided that we need to get some information about what is the surface property or the soil property of this location, because we are landed here. Maybe we can make this as our place. Next mission also we should plan in this area. So next mission obviously has to be a sample return mission. For that we should get some information on this. So we decided to fire the engine again on the last day before the lunar night started. The 4 engines were fired again for 1 second, so that the lander lifted by about meter, 800 millimeters it lifted. And because it is on a slope, horizontally also it moved by about 500 millimeters and landed it in another place. Both the lift as well as the landing has given us additional data through from the thrust given as well as the lift obtained, acceleration measured. All the measurements are there. With that, our people are studying whether we can derive the properties of the lunar regolith at the point where we have landed, so that it will give us, because now we can no longer use the Apollo data on the soil character or the lunar regolith characteristic for this area. We need to have our own data. So that is why that HOP experiment was done on the last day, which later we came to know in 1968 also Surveyor 6 craft also had done similar thing, which when we did not know. Later it was found that Surveyor 6 of NASA did it in 68. You will not see anything. You will see only the plume of the engine. So engine plume only. Then everything goes out of focus and it falls back and settles at a different place. So to give how much it has moved, so from these photos we could measure how much it has moved. Height anyway, we have the measurements on board. So that is the video. So this is the Chandrayaan mission. Can we put back the slide, the last slide? Yeah, the last slide. So I was asked that you tell what are the outcome. No, go to the 2 slides are there. Please. What were the outcomes and what we feel are the gap areas for us? Because it is a fraternity of engineers and people who are influential people are here. We thought we will convey our points here. So the outcome is a technology demonstrator, and it is once again proved that if we put our mind to do anything, we in India can do anything. This has proved, Chandrayaan 3 once more has proved that lot of new hardware and software were developed for this, which is also going to help us in future all our missions. And the third point is more important, more than actually the engineering and design, the importance of process compliance. This has been very, very significantly reinforced by this Chandrayaan 3 mission, because not only the innovativeness of the people and what has been done, but also going through the rigor of the process and review, that just because somebody tells, nothing will be accepted. Everything will be verified. It has to go through the grind of review and verification, re-verification. This process-based approach has been once again proved to be the immediate requirement for every one of these kind of activities. And of course, the amount of enthusiasm it has created, particularly among students, which the amount of messages we get and calls we get is tremendous. And children and youngsters are looking for some inspiration at regular intervals. So I think we should keep on doing, not just only ISRO or Chandrayaan mission. I think as a scientific and engineering community, we need to keep on doing some things which everybody will be proud of at regular intervals. That is what we. And the gap areas, this I am going to tell mainly about the space sector. What we are finding, which most of you already know also, which we have been telling for quite some time also, the problem of not just only semiconductor, the lack of indigenous supply of many items. Electronics, there is nothing is available. There is no semiconductor which can be used in space missions, which is made in India. So we have been trying to do something with the SCL, but it is a 180 nanometer silicon foundry. Whatever could be done is being done there. But still we require support from the engineering fraternity, industry, to build this capability in the country, because we are buying even a resistor from outside, which is not only time consuming, it is also very expensive. The second point is, it is preventing us to do customization, making things smaller, because we can integrate systems into smaller chips. Whatever we are doing in FPGAs, all FPGAs can be converted into small SoCs. The gain will be in terms of very large gain in terms of power, mass, volume, everything will be there. But because of the absence of a good foundry within the country, we are not able to do this. There are other reasons. This is not the only problem. There are other reasons because of which, again, the problem in the mechanical side is little lesser, but there also, even as honeycomb, aluminum honeycomb is not available in the country. It has to be bought from Hexel only. There is no other source, aluminum honeycomb or a carbon fiber. Everything needs, or aluminum sheet, a face skin material of 100 or 200 or 300 micron is not available in the country. We are able to make blocks, but we are not able to make thin rolled sheets. Everything is getting imported. This is an important lacuna for us, and it is a millstone on our necks. We need to do something about this supply chain within the country, because the problems are further aggravated because of other reasons like global tender not being allowed, we have to buy everything in India. They are all done with some good intention by government, but what impact it has on different sectors for different people have their own take. But this only solution I am seeing is the industry and the engineering fraternity should find ways of getting the supply chain available in India. Second one is sustainability of this kind of work. The sustainability will come only when there are going to be large volumes of anything. We can ask for a semiconductor foundry. Whoever government can also fund for the semiconductor foundry, but at least the running cost has to be recovered back. Because as you all, some of you may be knowing, no semiconductor foundry can be left idle. Either you produce or you have to keep on purging with hydrogen, or depending on what is the foundry, you have to keep on purging it. And if you are not running it 24/7, 365 days, the foundry is not going to be commercially viable. Even if you give 20%, 30% off for a foundry, it is not commercially viable. So the only solution we have to find out is, to make it sustainable, we need more work to be done. More work by only government asking you do this satellite or that rocket, it is not going to happen. Sustainability only will come when there is a demand from the society, the demand from the country, industry and the research institutions should demand these kind of things, materials. We are talking about these materials and semiconductors. This can happen only if the volumes are increased by demand. Third one is the HR domain, where the skill set. We are, though we are telling that we have a very big pool of engineers, the required skill set, we have been finding that are very limited to the people who are working in the domain within ISRO. Even in the other scientific organizations, we are not really able to get the domain expertise because it is a special area of work. So unless we are finding ways and means of expanding this HR base, this is going to become really very difficult, because what has been learned by people, there are many intangibles which are only in the head of the people. Nothing is written down. Nothing can be written down in some cases. So by doing more in industry only, this problem is going to get resolved. So again, this 1, 2, 3, all are leading towards the same thing only. That is the recommendation what I am trying to give, is that we have to increase the engineering industry's involvement, more space related activities. There should be more space related activities that should happen in the industry. Unless the volume comes, I am not telling about satellite making or launch vehicle making. I am only talking space based services. You would have, some of you would have read in the international studies, out of the $540 billion global space economy, the share of satellites and launch vehicle building is 7.2%. Remaining 92.8% is in the ground equipment that are used for the satellite based services, like your RF baseband equipment, test equipments, and the services that are provided using the space based data. 92% of the revenue and the market is in this domain. And to do this work, you don't require huge investment. Nobody does this work. Not even a single down converter is available for purchase. An RF down converter, which is usable in any decent ground station, is not available in this country. People are importing. Designs are available. People are making for our own use. We make and use it. Why industry cannot make this and market this product? Today, whole world is supported by 1 or 2 people. It is a monopoly in all these instruments, all these equipments. Unless the industry and the engineering fraternity takes it on themselves that we will enter this business. So what we are suggesting is engage the industries in the downstream activities, which is related to the ground hardware, software, and the services, which is, as I told, 92% of the global space sector business. So no big investment is required. All designs capabilities are available in this country, but nobody wants to take it up because there is a pain in the initial phase. And to make this happen, the other one, what I told, the first one, lack of supply chain. To do all these things, you require the semiconductor foundries. And once industry starts doing this downstream activity, because they will know how to utilize the space data, they will demand even better and even new kind of measurements and services data from the space. So that will ask for more satellites, more launch vehicle. That is how the volume of business is going to go up. So this is what is we are recommending to this forum, that we should find a way of making the Indian industry to take up at least the downstream activities in the space business. Thank you very much for the time. I think I have taken much longer than what the allotted time to me. Thank you for the time. Yeah, I have no problem.
Thank you, sir, for a very informative talk, unfolding the story and the features and the facets that were behind the successful launch of this Chandrayaan mission and some successful completion of this Chandrayaan mission. The claps that we had during the launch site of your video only tells that the thrilling moments that we experienced during the online transmission of the event continues to linger in our minds. Thank you. Now, the talk is now open for questions.
Thank you, sir. Very nice presentation for the India Proud work. And I have some technical question. Before landing this lander, when it was at this around 30-kilometer height, so the legs were horizontal. And when it was touching down, the legs were vertical in the facing the moon. So what kind of rotation devices were used for achieving this?
So only thrusters, only the engines, chemical propulsion based engines are the actuators, and measurement is done through gyros and accelerometers.
Were these laser gyros or?
Laser gyros, yes. Because any other mechanical gyro, during this 20 minutes of forward descent, the drift will be so large, it is not manageable. Laser gyro, the drift over this period is less than, in terms of time, if I tell, it will be less than a millisecond. So it is laser gyro, even though life is very short for the laser gyros, for this 20 minutes duration, it is good enough, and that is the only solution for this. Unless in the mechanical gyros or MEMS gyros, a new breakthrough comes which will reduce the drift. This is the only solution.
Thank you, sir.
We heard that the rover was sleeping and not waking up. What is the situation now?
Sir, the mission was planned for one lunar day, 14 days, because both the lander and rover only have solar power. There is no other energy source other than the solar panel and the batteries. And 14 days without power, you cannot survive, and the temperature expected during the lunar night is minus 200 degrees centigrade. None of the electronics components are rated for anything below minus 55 degrees. Even a single component failure is the loss of the mission. So the mission definition was only one lunar day, that is the 14 days. But as always, we hope that against the probability or the science or the engineering of the thing, if it somehow comes back, yes, we could have. So what we did was two things we did. One is we designed, at least the power system was designed such that with components which can survive this 200 degrees. Like for example, when a switch is used, use only MOSFETs, don't use bipolar transistor. So never use the switch in the linear region. It has to be only on off, because we found the on resistance is getting degraded due to the low temperature exposure. So MOSFET that way is not a problem. It is coming on. Similarly, what we found is don't use any leaded components. All use only SMT components, because the joint of the lead to the component is the place where failure happens due to this very low temperatures. Like this, we did a lot of this work was done for nearly 5 years to find out what components survive, what components don't survive. But still, I can test 100 times, 100 components. 101 component, there is no guarantee because it has not been designed for that. So, wake up was only a hope. It has not happened.
I have just little curiosity about the supply chain which you mentioned and the issue of creating sufficient demand for the industry which is doing this. It's an anecdotal information, but I was told by somebody that, for example, a Russian ship and a Russian truck has a similar fuel pump or same fuel pump. And actually, a ship in distress in some port outside Russia, somebody simply went to the nearby road and stopped a Russian truck, picked up the fuel pump, put it here. Ship went ahead, the truck could afford to wait. So the point I'm making is, are there such opportunities in different segments in the country where a modular approach to make sure that you create larger demand for such critical components?
Sir, the problem is in the volumes, numbers only. The number of satellites what we do per year is 5, 6, 7, 8, 10 maximum. That's all we are doing. But to support a production line of even the smallest one single MOCVD reactor or ion implanter, you require hundreds of thousands of components to be manufactured. That is the problem. Why we are not able to use any production commercial?
My point is precisely that. So that is as far as the demand in the space activity you can create. Now, is it possible that similar equipment or component you have can also be used in some other sector for some other application, so that the cumulative demand is larger and you make this more viable?
Sir,
I don't know, I'm just asking.
I understood your question, sir. The problem is the same component can be used in other commercial utility also. But to ensure the given one fit failure rate or better than one fit failure rate, the semiconductor foundry during the process itself, there are additional measurements, tests, process changes which have to be included as part of the process so that it gives the required reliability. The main problem of semiconductor for space use is you should have a reliability better than 1 in million. Failure rate should be less than that. Commercial components, that one fit failure rate cannot be assured.
I'm not talking about commercial, but
So
let's say
to
military
assure
grade.
that, the cost is becoming 100 times. So if I have to use the space grade component in commercial, like our mobile phones or television sets, the cost is going to go up 100 times. It is not viable financially. The problem is that if I want to use the component, that is the reason why nowadays these constellation small satellites are gaining momentum. By very nature, the constellation are tolerable for failures. If I put 1,000 satellites, some 5 of them fails, it doesn't make any difference. The service will still continue. So that is the approach the constellation designs people are taking. Use commercially off-the-shelf available components, allow some number of failures. So the constellation design will take care of the failures. Whereas the other way around is going to be using the space component for commercial use is going to be very, very expensive.
Thank you very much, and let us thank the speaker once again for this wonderful session. And I request Dr. S.V. Nakhe, Director RRCAT, to present a memento.
As I mentioned, the 3D fit of the hazard, the maps, they are all artificial machine learning only. You made the software as made to identify whether it is a boulder or a crater, and from the feature that is already available using the Chandrayaan 2 orbiter images, identify from that which part of that larger picture is this image and identify the lat long. It was done through machine learning only, yes. They are all done on the ground. This one onboard implementation is this hazard detection and identification of the lat long.
I request Dr. Nake to please present the memento to the speaker of this session.
Thank you very much for a very exciting talk.
My pleasure, sir. Thank you, sir. Thank you.
We were so much excited that our laser additive manufacturing team has prepared a additive manufacturing picture of lander and rover. And it was presented to director of VSCC very recently.
Okay.
So that is a sort of excitement and at our center also.
Thank you, sir. Thank you.
The event was presented here.
Thank you, sir.
And we resonate with your gap area recommendations.
Thank you, sir. Thank you.
Thank you very much, sir. Thank you, sir. This and thank you all for being with us in this evening session of Engineers Conclave 2023. Thank you very much.
We'll give this.
Thank you, please.
This also